Welcome to APEC. It's April 12th, 2025, and I'm your moderator, Tim Ventura. Thank you to everyone for joining us on today's call, along with everybody watching us on YouTube. I am really excited. We have amazing presenters, an amazing cast and crew with us today. Everybody is pumped up about this. We're starting out with Gary Stephenson, who will be discussing high-frequency gravitational wave communications. Simon Holland is going to come on and discuss UAP and the Rendlesham forest incident. Jennifer Nielsen will present a new model for quantum gravity with navigable spacetime and tunable wormholes. And Daniel Davis has a pre-recorded presentation that we're going to be pushing out on many worlds' interpretation of quantum mechanics. So we've also got lots of lab updates. I believe Robert Francis Jr. is going to be joining us in addition to the usual suspects for those. And we're going to finish off the event with open discussion by conference attendees. So before we get started, I want to do a couple of quick updates. Today's event is using StreamYard. We are broadcasting through the Alt Propulsion YouTube channel. I think Jeremy Riss may also be mirroring that on his channel. And we are streaming out to several other social network sites as well. If you haven't subscribed, please do so now. If you go to our website at altpropulsion.com, you can sign up for our mailing list. That is probably the easiest way to do it. And that's altpropulsion.com. And then just put your name and email in. You will get an invite every time we have an upcoming conference. You can ask questions on the Alt Propulsion channel using the live chat feature on the right-hand side of the page. We will try and ask them to our presenters, depending on time constraints, and those do scroll up the page pretty fast, so sometimes we do miss them. You can also always view conference replays, details, and speaker info on our website, again, at altpropulsion.com. So again, thank you so much to everybody. I'm really excited. I'm going to bring Gary Stephenson right on. Gary, welcome, sir.
Thank you so much, Tim. It's good to be with you again.
Okay, and I am going to jump right into your presentation. Okay. So again, you're going to be talking about, thank you. I am so appreciative for this. This is something that you've been working on for quite a while. I think you presented this elsewhere, right, at Marcel Grossman?
Yeah, I haven't actually presented the details of this one. I think the May talk is going to be the Marcel Grossman one. This one was tied up with a non-disclosure agreement, but I was able to get my partners to cancel that agreement after we paused our funding. So thanks to my partners for that. This will be the first time I've been able to present this material.
Awesome. Okay, well, let me take myself out and take it away, sir.
All right, thank you, Tim. Yeah, so I'll be covering collaboration that's been going on for about a year and a half that addresses the quantum conversion of photons to gravitons and gravitons to photons. And I'll explain why that's important and what we're doing with that. And I'll also be presenting some technical references on how that can happen and how to build devices to make that happen. What's the problem that we're trying to solve? The problem we're trying to solve is non-line of sight communication. This is a situation where, for instance, if you're in a mine shaft or if you're in a submarine, it's very difficult to communicate with people or entities like that because they're underground. So how do we solve that? One way to solve that might be through non-line of sight communications using gravitational waves. So we started looking at this last year when a group came to me and said, "Hey, can you look at making gravitational waves with the method that Fontana outlined?" So I'll talk about Fontana's method for making gravitational waves, and I'll talk about how it was that this came to be, that we started researching this area. But it would obviously be beneficial for replacing satellite communications too, because we wouldn't need a whole fleet of LEO constellation satellites. You could do this with a very few emitters on the ground. There's a number of different ways to make gravitational waves. There's the ways that in-spiraling black holes make gravitational waves. That's through the stress energy tensor in Einstein's field equations. The coupling there is very poor. You need a lot of mass and energy changing to make a little teeny amount of gravitational waves. There's a coupling constant that has g over c to the fourth, and if it's a gravitational wave, it's g over c to the fifth. Between the wave that you get out versus the mass and energy changes you put in. So that's the classic case of making gravitational waves. There's also a quantum case where you're taking a couple of spin 1 transitions and you're making one spin 2 transition out of them. But you have to find a way to trick quantum mechanics to force that spin 2 transition, and then you get a different particle. Spin 1 transition, you get a photon. A spin 2 transition, you get a graviton, which is an elemental piece of gravitation. Fair warning, gravitons have never been measured at the elemental level. They probably never will be because their interaction length is so small. So you need an enormous amount of gravitons to be able to measure a gravitational wave. So this would be one potential way of making a very large number of gravitons. So it's been, I think, about 20 years now since Giorgio Fontana, an Italian researcher, had published on this. And he recognized that this was possible from an even earlier work that was done in the 60s about quantum transitions that might result in gravitons, spin 2 transitions. And so on the left, we'll see the quantum transitions that are allowed, and the ones in blue are photon transitions. And then the transitions that are allowed that are spin 2 transitions, and those are in the red. So you'll see some transitions are blue, some transitions are red. Some jump one spin state at a time. The gravitons will jump between two different spin levels at once. And so that's a way to graphically depict these transitions. The question is going to be, what's the quantum efficiency that we can achieve between jumping a couple of photons and then seeing that graviton fall back out? Foundational work here is the Halpern and Laurent. This was the 1964 work that Giorgio Fontana used to develop his ideas about how we might be able to make a gravitational laser, even perhaps. And so he had based it all on the emission strengths, gravitational radiation patterns for both photons and gravitons that were predicted in that 1964 work. It was largely ignored. However, independently, different research in 1982, Ford had published on the same system and gotten similar results, the gravitational radiation by quantum systems. And there he indicated that if you arrange the radiation, correctly, that there should be gravitational radiation happening from quantum transitions. So a couple experimental propositions have been put forward. Fontana in 2012 came up with a high temperature superconductor as a potential quantum source for gravitational waves. That was his high temp superconductor gazer or gravitational laser. And this had a purely quantum transition approach. And Tatasov was a different researcher who had a semi-classical mass oscillation approach where he was getting particles at the quantum level to oscillate very rapidly, and then that mass oscillation would in turn create a gravitational wave, doing those in superconducting junctions. So what I'll be presenting today will be the Fontana approach. We also looked at the Antonisov approach, but that is not as well documented, and so that's kind of a fallback position. This is just a screen snap, and it's probably an eye chart, but if you download this slide set, you'll be able to see, kind of on the left I put the cover page for the paper. On the right, it's an extraction out of Table 1. The Table 1 uses the equations, has all the equations in it for all of the shapes of the distributions of radiation, not only the photonic radiation in the RF spectrum, but also the gravitational radiation in the gravitational spectrum. And so it shows you the transitions and what transitions lead to what gravitational radiation patterns in great and gory detail. So I also have that reference available. I can send to Tim if anyone's interested in looking at the original reference. Same with the Ford reference. I've just extracted the cover page, and on the right, the power equation for how much gravitational power do you get out for power put into this. And so that's another reference that's available for those who want to inspect that reference. This is from Fontana, and I can also make this reference available to Tim. This is his 2007 paper. That one is publicly available. I'm not sure the 2012, because it's part of a book chapter, that the 2012 is publicly available unless you buy the whole book. I think that the book was by Robertson, was edited by Robertson, and it had a variety of different papers in. This was one of the papers that was included. And so this was the first paper to show that if you had a transition between a type 1 superconductor and a type 2 superconductor, that at that junction you could force photons in and gravitons out. And so that idea would be an S, they call it an S-wave junction in Josephson Junction. And his first interpretation about how to do that was with a bulk, we call it a bulk device, where you lay down a huge chunk of crystal, of high temperature superconducting crystal. Then you lay onto that a smaller layer of low temperature superconductor, and that gets that type 1, type 2 junction going so you can force those transitions. And he was recommending YBCO or bismuth copper oxide as the high temperature side, and on the low temperature side, like a magnesium, or you could even use lead. For our particular approach, we wanted to take a look at a thin film approach, and we wanted to do it with thin films that were easily obtainable in my collaborators' labs that I've been working with. So they recommended making some changes to the type 1 and the type 2 superconductors. And so we were going with different materials than what Fontana originally recommended. And that's purely because those are the materials that are more easily used in a thin film environment. So this would be a thin film device. This would be thin films that are deposited on a silicon wafer. So this would use the same technology as silicon wafers would use. And then the experimental configuration, because now we're talking about both sides, type 1 and type 2 would be lower temperature superconductors. This would be using test and probing technology that was developed for quantum computing. And so this really would not have been possible without the quantum computing infrastructure out there. So that's essentially why this hasn't been done before. Now, we need to make them oscillate if we're going to get a wave. And so one way to make them oscillate is to put them in AC mode. Josephson junctions have an AC effect, AC Josephson junction effect, which means if you apply a small voltage to an AC Josephson junction, it will start oscillating. So you're applying a small DC voltage and you're getting an AC effect out. And that's a very well described effect. It's an effect that I've reproduced here. I reproduced an MIT briefing on it on the right-hand side. And then on the left-hand side, I have a chart of various amateur frequency bands that would be available for use without a license that we could use in case there's EMI that occurs when we're doing this. That EMI would be emitting in the RF band. We want to be able to shield this experiment so we know for sure we're getting gravitational waves. But I am also concerned that these oscillations may have some electromagnetic interference side effects. So in case of that eventuality, I was looking at these microwave bands, these amateur bands, and I selected out of these amateur bands a 24 gigahertz for now for the original device layout, because I can get a lot of different devices on one wafer. It scales pretty well for one wafer on a standard size wafer, and they would all be in sync, in synchronization, so that we could have a wavefront that would multiply the effect and strengthen the effect and give us better odds of seeing some effect. And so that packaging is shown here. This is a silicon wafer that it's 150 millimeters, so that's a standard 6-inch wafer. The little round dots indicate little emitter pads. They would be connected in the pattern I'm showing there that are all quarter wave length apart. So they're quarter wave emitters, that they're a full wavelength apart. They have to be a full wavelength apart so that they're all emitting in synchronization. And so that's why I chose this particular layout, was to keep everything in terms of these quarter wave emitters all in synchronization with each other, because they're all a full wavelength apart. And so they're all in sync. I did remove you might ask, well, what's going on with the red X down below? My original interpretation of how to package this device was when we were still thinking about high temperature superconductors. And so I had an SMA. It's a standard microwave connector that is constantly used with microwave devices as an input and output port. Unfortunately, that would allow too much heat to be able to cool the device to low temperature superconducting. So we can't really use SMA connectors with cryogenic devices. And so we would be using a cryogenic probe station instead of connecting it to standard microwave devices. And that's where the quantum computing infrastructure comes into view here. And so when I was first approached with this idea, I was approached by Phase Helix. Dave Rossi and Kyle Gustin are two Canadians that were interested in developing this idea. And so they're the original funders of this idea. Unfortunately, they have a lot of other ideas in work. So they put this particular one on pause for now, which also, by the way, enabled me to be able to brief this to you today, because we also put the non-disclosure agreement aside since we've only made a certain amount of progress. Now, there are still some proprietary details that we haven't outlined here, but we did want to go over this and make it public in case there are other funding sources out there, or there are other people interested in doing the experiment themselves, that they could take off where we left off. And so I was the technical design lead, so I formed an LLC called Seculine Gravitics to encapsulate that intellectual property that was part of the design process of this, for instance, the antenna layout and so on. And then I have approached, there's a group that works at UC Davis in their microelectronics labs called Ravada Solutions, and we approached them. We actually had approached a number of different vendors for developing these devices. The real issue became the people that make these cryogenic Joseph Junction arrays are really busy working for people like Sandia Labs, Los Alamos Labs, the nuclear detection agencies, because they make great detectors in the gamma ray and in the X-ray bands. So they're in great demand, and also it came to light through conversations with Dave Rossi that there may also be other people wanting to work on Joseph Junction type communication equipment. For instance, Hal Puthoff's name came up as possibly working in this area. And so when we, for instance, approached Star Cryogenics with this notion, they said, "I'm sorry, but we're already committed to another design team." So Ravada Solutions had not committed yet with any other design teams, and they are willing to take on this problem. And so they have at their disposal the microelectronics development lab at UC Davis. And so they agreed to be our fabrication partners. In addition, they recommended that we go with the quantum computing kind of cryogenic testing beds that are common for quantum computing. And so that's when they brought in Form Factor, and Form Factor would be our testing house. Ravada Solutions isn't set up for testing. They're really a fab house. So they would fabricate the devices, and the devices would be tested at Form Factor in their cryogenic test facilities. So those are the partnerships we needed to form to get it done. I mentioned the UC Davis Center for Nanomicroengineering, and it's been great to work with them on working out the fabrication details and the sequence of events that we need to fab these devices up. We also had some advisors. Eric Davis we brought in as an advisor for a concept reviewer, and we also reached out to contact the original designer of these devices, Giorgio Fontana, to check our work to make sure we weren't completely off base and we hadn't missed something. He also did concept review for us, and I'm very grateful to both he and Eric Davis for that concept review process. And then we plan on, but we have not got to the test stage yet, engaging with Form Factor for going through how do we package this device for testability, and then how do we size it and scale it for their test jigs. So we want to work with them on developing test jigs and make sure that we're consistent with the kinds of wafer testing that they're doing already. And do we have to dice the wafer to make it smaller, depending upon the cryogenic needs of this particular device? So We are still planning on leveraging that quantum computing, but because research is on pause, we haven't really made much progress on this part of it. The real vision here will be, it's not just for GWCOM. It could be a test bed for testing all kinds of gravitational devices, gravitational materials. What would happen if we transmitted through different materials? Does it affect things gravitationally? So it'd be a wonderful materials testing bed. A receive-only array could potentially be useful in gravitational astronomy, where we're looking at a whole new spectrum it would be sensitive in a spectrum that so far we haven't been able to peer into. We've been only able to look at low-frequency gravitational waves. We haven't really been able to check out the sky in the high-frequency gravitational wave area. And also could be of interest to SETI, the search for extraterrestrial intelligence, because it could be that instead of using RF waves, there could be extraterrestrial or non-human intelligence using gravitational waves. So if we were going to look for something like that, this would be one potential technology to use for that. Finally, if we get to powers that are really useful, would there be a propulsion application where we would be able to somehow use these gravitational waves or rectify them with quadrupole rectification to create net propulsion? And so this all would work towards ushering in an age of gravitics. That is my last slide today, Tim. So I think we still have time for Q&A. Is that right?
Yeah, absolutely. Absolutely. So that was fast. We are rolling through them. So you know what? Let me bring the guys in here. So before anything else, you know what? Here, I'll take the slide deck down. Guys, let's give an enormous applause to Gary Stephenson.
Thank you, Jeremy, for bringing in an additional audience member.
Oh, look at that. Yeah, that's the little guy. Wait.
Hi, Mark. Jared?
Yeah.
Good to see you all.
Yeah, Gary, thank you. That is seriously awesome. Guys, do you have any questions for Gary?
Yeah, what would it take to move this project forward? Like, what kind of funding are you looking for? Are you planning to work on it at your lab?
Yeah, I don't have any lab equipment myself. I just do design consulting. So it would all have to occur at a microelectronics lab that's used to doing custom wafer processing. And so that's why I thought UC Davis was ideal, because they have already set up all this clean room lab space, but are doing a lot of wafer processing. And that's why I worked with Rivada to get it going in their wafer lab. Now, it's not to say they're the only wafer lab in town. There may be other wafer fab facilities that can do high temperature superconducting depositions. But it is certainly a specialty area. And because lab time is so expensive, it's a pricey, it's going to be not tens of thousands, probably going to be hundreds of thousands to finally get devices out of this. And then probably another in the tens or hundreds of thousands to get test time at these quantum computing facilities at form factor. Jared, go ahead.
Yeah, awesome presentation, by the way. One thing that I've seen in some of the other obscure UFO docs is talking about this transition, that for some reason there was a good amount of money spent on the propulsion side for trying to research specifically the transition zone for superconductors. I was just wondering, could that be something that could be useful for identifying and measuring high-frequency gravitational waves? Would be if a gravitational wave is passing through the lattice such that the lattice goes from a non-superconducting state to a superconducting state. Normally, you're going to use a squid or something, right? You're just going to, take the whole condensated stuff.
The squid's a related technology because it uses Josephson junctions, right? Yeah.
Yep. But I was just wondering, could there be something useful, some obscure useful thing hidden within observing the transition?
Like I haven't heard that before, in terms of that transition time. I know that is something we look for to make sure that they're in superconducting mode, because when we're testing these devices, we're dropping the temperature very slowly, and we're looking at the resistivity, and as soon as that drops away and the current goes way up, we know, okay, the transition's over. But really, these devices are really designed to be fully transitioned. They're going to be in full superconducting mode. So I haven't really explored that transition regime. But interesting point. I'll look into that.
Well, so one thing I would want to ask is, are there, I mean, like you were talking about hundreds of thousands of dollars to do kind of a full replication of it, but are there like scale or lesser replications that could be done on a budget, right? And that way you could kind of create a stepwise path to success.
Yeah, and we've looked at that. I mean, there may be ways of cutting back on or trying several cycles at once. For instance, when you're laying out a wafer, you maybe look at one design on one part of the wafer, but a completely different design on another part of the wafer. And that way you're doing one wafer run instead of multiple wafer runs, and you can cut down on cost that way. So, we could look at cutting back cycles. Right now, we've looked at like half a dozen different test variations and test cycles. But you get to a certain point where the ability to fabricating a device this complicated, and even one wafer is going to cost you like $10,000. So it's hard to scale all the way down below a certain minimum level. Yeah.
Yeah. Well, that's one of the challenges with this technology, and in a weird way. I mean, this is just my thought, but like, it's kind of, we're victims of our own success, right? Like, you guys are reaching the point where, as this evolves and as it becomes more complex, it becomes more and more difficult, right? And it's like, you could look like,
certainly when you're on the bleeding edge of technology, it's not cheap, right? It's not cheap to make silicon wafers. It's not cheap to test them in superconducting temperatures. It's an expensive proposition because it is on the edge of technology. Yeah. Especially given these materials are not commonly used.
Gary, there's somebody in the audience here, and I'm sure there's who spoke out and said that they would like to invest in this. Do you want to give over like contact information or something? So that
sure, yeah, I'll put a chat in the chat here. Seculine.
So people can reach out to you and talk about possible investments in this.
And I think this email is also on the cover sheet of the briefing.
Yeah, I would urge you to maybe change the @ symbol to put brackets around the @ right?
Oh, otherwise it gets hacked.
Yeah, I'm always super careful about that, even in YouTube chat.
Okay.
And you know what? If it's okay, let me bring Simon Holland in. Simon is going to be talking about Rendlesham.
Hi.
Simon, welcome.
Greetings, everybody. It's an honor and pleasure to be here.
I don't know if
I've sent you an email, Tim. I've sent you a film, a URL, if you can.
Oh yeah. No, I'm more than happy to. Let me check there. Okay, yeah, there it is. Yeah, and it's on YouTube. So Simon, did you have any questions for Gary? I don't know if you were able to catch Gary's presentation or not.
I was editing, Gary. I would love to know more about you, but I'm afraid I missed it.
No, that's fine. I think Tim, you're recording it, or someone is. Maybe Jeremy is.
Okay.
Yeah, and we're streaming it too. Yeah. And then one of the things that I'm doing is I'm trying to create video shorts. I'm trying to get all of this stuff out there. So I'm working on a new big secret project to promote a lot of this stuff. But it's a secret, so I can't tell anyone.
Anyone else before we jump to the next topic?
Okay, well, I think maybe that's everybody then. Okay, well, Gary, again, thank you so much. And then I have you on the hook to come back for our next conference as well.
Right. There we'll be talking about some different techniques for generating gravitational fields. So this is more on the DC field side than the AC field side.
Okay. Well, Gary, thank you again. Thank you again. It's truly a pleasure.
How can we get his email up on the screen?
Let me see. Which one do you want to do? The Seculine?
Yeah, I put it in studio, but it's seculine@gmail.com. So pretty easy.
Okay. Here, let me change that real quick. I'll just put brackets around it.
I put brackets around the @ symbol. I don't know if that's good enough.
Yeah, that should do it. Usually it just. So I think what I can do is that. So seculine@gmail.com, and then I'll put that up. There we go.
Perfect.
Great.
All right. Thank you, Tim.
Awesome. Awesome. Yeah. Super exciting stuff. Guys, I don't know. I'm spacing out here. Let's do it just in case. One more giant applause for Gary Stephenson.
Great.
Gary, thank you again. And I do anticipate seeing you at the SCU conference if you're there, and Tony Robertson as well.
Yes, we're planning on going. I know Nancy enjoyed it last year.
I'm going to bring the guys with me too. So
Cool. Great. Very good.
okay, so I am going to go next. Let me go to Simon. Simon Holland, Professor Simon, welcome to APEC.
This is great. Yeah. I've been meaning to join you guys forever. Of course, I know who you all are, and this is fantastic. Thank you for the invite, Tim.
Oh, absolutely. Well, it's an honor and true pleasure to have you with us today. So you've been investigating UAP in Rendlesham Forest, right. And I have kind of a folder full of slides, and then I also have a video. Do you want me to try and play the video?
Yeah. Well, I'm just going to give hi, everybody, a bit of an introduction. So, Rendlesham Forest, it's Britain's Roswell, is what people describe it as. It's my gateway drug into UFOs. I came from a media, BBC, PBS, Nova background, and we wouldn't touch a UFO story with your barge pole. But one of my YouTube viewers said I had to reach out and speak to this guy who's called Sergeant John Burroughs, retired US Air Force. And he was exposed to some highly strange, in the Jack Valet terms, at this place in Suffolk that I knew quite well. Suffolk's quite odd. And I did eventually, over COVID time, speak to John Burroughs. And what he said changed my life, because he described a UAP. It went round him. His colleagues saw a triangular craft. And the strangest thing was, sadly, he was injured by it, and his injuries were well known. He's currently being studied by Gary Noland and Kit Green, at the time the chief CIA medical officer, and they knew what he was exposed to, the frequencies of his damage. They knew exactly what it was. So he's of great interest, and that just got my interest. What actually happened there? And the very first time we spoke, this John Burroughs character and myself, John said that in this strange scrubby woodland between two NATO bases called Rendlesham Forest, they were doing physics experiments. And on the night of the encounter that everybody thinks is just a flying saucer, he says they were doing plasma directed energy weapon tests and laser tests. I went, I'm really interested. And I think now for 3 years I've been looking at this. John Burroughs definitely wants closure. He eventually got, after 15 years of denial of any claim through the VA, the Veterans Association, he eventually did get a settlement when the DOD admitted that something did happen, because Britain told them it did happen. It's quite well known in Britain. The MOD wrote about it and actually mentioned the people who were injured. So the DOD in the US couldn't deny it anymore. And in some ways, John Burroughs thinks that's disclosure, because, they settled a case for a US Air Force officer who was injured by a flying saucer, or a UAP or something. But what really happened, we don't know. It was obvious to me that there was meddling going on, that there was that the US and the UK in Britain, in a very specific place, and that's what I'm going to describe tonight, knew that there was something odd there and wanted to evoke something. And just this week, and this is what I've been working on, Ross Coulthard and I have been working with Jake Barber's organization, and they mentioned to us this device they've got, which they're called a dog whistle. Immediately, I heard that word, dog whistle. I have been avoiding using that term for 3 years because I was warned off it, because I think that the origin of the dog whistle that Jake Barber's organization is using right now dates back to the Rendlesham Forest incident and maybe before. We've all seen Close Encounters with the lights and the sound. the way of evoking UAP has been experimented with, and I think it did happen in Rendlesham Forest. So there's a lot more to the story than meets the eye. Most UAP, UFO researchers, YouTube channels talk about triangular flying saucers, but what the real question is why? Where is Rendlesham Forest, and when did it happen? So, well done, Tim. That was exactly the headline that splashed up over Britain. UFO lands in Suffolk, and it wasn't a UFO. And then we were told by the MOD it was the lighthouse, and then it was rabbits, and then it was the SAS raid. So there's lots of misinformation. But I'm a filmmaker. I'm not really a great speaker. So if Tim could possibly arrange to show the little URL YouTube film, which is an introduction to a new film that I'm making. What if it does work and you do get to see it? It's something called a rough cut. Literally, I rewound the tape and pressed play to Tim. So it's got black in it in places, and it's not polished, and it will be on YouTube later this week probably. But I thought you guys might like to see it because it's the real story of the dog whistle. So if there's any way you could play it, Tim, that would be great.
Yeah, actually, I'm just queuing that up now. So I have to stop.
All right. Well, you tell me. Right. Well, I mean, it's interesting. Let me just tell you a bit about Suffolk.
Okay, there we go.
Oh, there you got it. You got it. That's the first shot. It's about 5-6 minutes. You can play it, and then I'll answer questions.
So I'm gonna click play now. Then.
In the heart of Suffolk, England, where ancient history intertwines with the unknown, lies a story that defies belief. A story shrouded in secrecy, classified for over 40 years. On the one hand, a tale of human scientific ingenuity to build a device to contact non-human intelligence, but on the other hand, a mission with a great cost. A defense project with the ultimate goal of building a new way of waging war that, while under testing, injured loyal service personnel and opened a portal to the highly strange. It was the height of the Cold War, a time of paranoia and secrecy. But beyond the geopolitical tensions, something far stranger was unfolding in the shadows of the British countryside. Suffolk, with its rich tapestry of folklore and unexplained phenomenon, had long been a hotspot for UFO sightings and pagan rituals. Yet what happened here purposely opened Pandora's box to manifest in our reality a potentially deadly form of non-human intelligence. In a joint operation between the United States Air Force and the British military, a group of elite personnel gathered to initiate a highly classified project to make contact with extraterrestrial intelligence. We believed we were on the brink of a breakthrough. In Britain, we now had the technology and the will to reach beyond our world. It had to be tested. But what transpired was not a peaceful communication. Reports surfaced of bizarre lights in the sky and sudden, overwhelming energy manifestations that left several U.S. Air Force personnel badly injured. The Pentagon quickly classified the event as secret, ensuring that no information would reach the public. But why? What were they trying to hide? This incident raised more questions than answers. Was it a deliberate experiment? a testing ground for human interaction with non-human intelligence. Were the injured men and women guinea pigs in a bizarre project to weaponize UAP? Who put them in harm's way? Suffolk's history is steeped in the mysterious, ancient rituals and unexplained phenomenon. Rendlesham Forest was chosen for a reason. The energy in Suffolk has always drawn attention. It's a place where the veil between worlds is thin. For the first time, we expose the science of evoking the phenomenon, the motives behind the project, and the dangerous implications of contacting another dimension. The Suffolk encounter is a reminder of humanity's relentless pursuit of the unknown. What lies beyond our understanding? And at what cost do we seek the truth? To this day, the fact that this project in Rendlesham Forest was a deliberate attempt to contact another world still remains secret. The British Ministry of Defence publicly deny anything happened, blaming the strange lights in the sky as merely flashes from a local lighthouse. The US Department of Defense attempted to cover up the fact their US Air Force personnel were seriously injured by classifying their medical records and even denying some were even employed by the military. Many researchers have looked into this highly strange encounter in Rendlesham Forest. Their films and research concentrating on the strange triangular craft and the weird lights seen in the forest. But why did those strange events happen in Rendlesham Forest, a scrubby Forestry Commission woodland in rural Suffolk, but in reality surrounded by advanced physics laboratories? Orford Ness, Britain's advanced physics test site. Bawdsey Manor, Britain's base for Type 67 Scorpion continuous wave radar that produces plasma effects. And this place, Adastral Park, Britain's microwave and laser research lab. Today, I am going to bust those myths and give you the evidence so you can make your own mind up to what really might have happened. The evidence about a type of man-made device that can summon the phenomenon and even manifest solid, non-human craft. Over my research, I was warned not to mention one code word that would expose this secret project. But that secret code just emerged into the light, out of the shadows.
We've been collecting UAP data for more than 5 years with electromechanical signaling, which we call our dog whistle. Generally speaking, we see 3 to 5 different classes of UAP per day during operations. After we turn on the dog whistle, UAPs literally come to us day after day.
We have turned on our equipment that we've customized and created what we believe is a dog whistle, and UAPs show up. So through that process, we started a systematic cause and effect, if you will, experimentation. And we've arrived at some very custom capabilities that when we deploy these capabilities, we get different UAP responses. Every time we turn on this equipment and do the things we need to do for the right amount of time, we get a response.
Jake Barber's private UAP research and recovery company, Skywatcher, revealed they are using code-named dog whistle technology and psionic control to attract UAP to their research range. What is the nature of a man-made UAP dog whistle? How was it first discovered? What place was it first seen to be highly effective? And who built it? These are the questions I am seeking answers for. But is my quest personally dangerous? Well, the UK has just toughened up its Official Secret Act to potentially prosecute journalists who stumble upon classified information. So, I reached out to ex-MOD officer Nick Pope for his advice. You and I both know a lot more about what happened in Suffolk in 1980 than we're actually admitting. I'm actually a little worried because I actually know quite a lot more than a lot of people realize about the capabilities of bases in Suffolk. I've actually been quite shy from mentioning things like non-nuclear EMP devices and things like that because it seems to be that it's still quite sensitive. Would somebody on YouTube get into enormous trouble?
Okay, sorry, Simon. I paused it for just a sec. Was that all that you wanted me to share?
Yeah, that's a good place to start. Apart from, I got a response from the MOD after I talked to Nick. Nick advised me to talk to somebody, and their response was hysterical.
Because you're still editing. It went into the still editing part. I could kind of tell. Simon, that's amazing. That was like movie quality. That was movie quality film.
I did that in the last couple of hours. It's got a lot of stock shots and that needs to be better. But I mean, it's the story's good. I mean, the story is it's the real story. It's not 100%. I mean, I don't really know. I'm not part of the MOD or the DOD of what actually happened, but I've met a lot of people. I know people who work at those labs. I know what they were working on. And I know quite a lot about what happened before the event where equipment was set up to do something. There was certainly a evocation by humans in the Rendlesham area on purpose. What happened next, what they evoked and what actually occurred and why those, it definitely was highly strange. It wasn't just plasma and lasers. It was certainly something extremely exotic appeared. And the other thing, Tim, you'll be interested in, nobody knows this because nobody has dug into it, is that everybody thinks it's near Bentwaters, but in fact it's near the twin base, which is called Woodbridge, which was secretly Britain's biggest nuclear weapons store, and nobody knows that. It was right over the weapons store. There's a concept called forward bases, where if the US gets taken out and they have no way of retaliation, they put large country-killing nuke bombs in allied countries, including Britain. And because they're secret, Britain doesn't need to know, so British population didn't need to know, and they're dual key. That's the deal. And there's quite a few countries, I don't want to name them, who have forward nuclear weapons. There was a bunch of Woodbridge, they're no longer there. They've been moved to Scotland. But that concept was and underneath Woodbridge, which is one of the most interesting bases in Suffolk in England, was an awful lot of nuclear stuff. And this is where the UAPs appeared. So what happened? We don't know. But They were meddling with something.
Amazing. Well, so you gave me a bunch of slides, but you went through all those in the video.
Yeah. The slides were. I mean, I used. I made the movie instead of the slides, but I mean the slides are kind of interesting because if you don't know Suffolk, I mean it's about 100 miles northeast of London, and it's very close in a way, but it's also rural. There's nothing there apart from defence laboratories. It's quite near Cambridge. That place that I was briefly shown in a film called Martlesham Heath was pretending to be a telephone laboratory, but in fact it was the headquarters of SRI UK and Stanford Research and also Marconi, and where they were doing microwave and that word which I dropped in called non-nuclear EMP stuff. So I mean, and then Orford Ness was fantastic. I mean, Orford Ness was where Robert Watson Watt was given the stolen plans of Nikola Tesla's death Ray, and then went on to said it didn't work. It didn't, and then went on to make radio direction finding. And then Bordsey was the World War II spoils of war from German radar, which is a very different technology, was brought back to Bordsey and developed into this continuous wave radar, which has amazing effects, including ionization effects. Oh, and so it's effectively can be used as a directed energy weapon. And all that, there's a triangle, and in the middle of that triangle there's some scrubby woodland. It's called Rendlesham Forest. That's the real story, obviously.
Amazing.
You guys, do you know about the case? You got any specific questions?
And actually, if it's okay, and I'm not trying to interrupt your presentation, I was going to ask, did you want to speak more on this just to talk about it, or should we do kind of a Q&A and have the guys?
No, I don't. Yeah, I'm a filmmaker too. I mean, you saw a clip from the film. I've done an awful lot of films about it. I mean, I could talk for hours on it, but that's quite boring, really. I mean,
it's up to you. It's up to you. It's whatever works. I'd quite like to answer questions, really.
Okay. Anything.
Well, before anything else, we need to give an enormous applause to Mr. Simon Holland.
You're very welcome.
And Simon, let me apologize for the chaos. I had slides in the last minute video and all of that. It
was my chaos. I imposed it on you, Tim. Thank you.
That video is amazing. That is I was watching that and I'm like, oh my God, this is like movie quality. You're saying you put that together in like 2 hours?
Yeah, I thought I sent you the slides about 6 o'clock, which was about 3 hours ago, and I thought, I'll just make a film.
That was like movie quality. I mean, that was.
I've been working on the idea for a week, but 2 hours ago it was black pictures and audio only. It was me talking into this microphone, and I thought, I should put some pictures for Tim, and that was it.
Yeah, that was amazing. That was amazing. Well, let me open it up for the guys then, and again,
what do you want to know? I mean, hi.
Yeah, well, Jared, go for it.
Jared.
Simon, right off the bat, just phenomenal work there, especially the fact that you can put that together in 2 hours. Phenomenal work.
My
question. My question here, it's going to take about 30 seconds to a minute to set up my question, if I can. So for the Rendlesham Forest stuff, there was some questionable / suspicious information that came out about it from Peniston in the mid 2000 to 2010. He comes out and he's like, oh yeah, by the way, after I touched it, there was a download, and then a couple days later, I'm in a hotel room, and like I wake up in the bathroom, and I've written down like pages and pages of binary code, and then in 2010 or something, it finally gets decoded, right? So setting that up, the code that came out of that, the ASCII code that people decoded, had like this list of 7 GPS coordinates with the last one saying origin and year 8100 or something like that. It was really weird, random stuff. So this is where this gets really interesting. So 1980, it was December of 1980, but January 1981 when he writes down the message, supposedly. So apparently Pat Price back in 76 followed up by Atwater in 1982 under Project Stargate. They ended up doing some remote viewing of some underground alien bases. And they came up with these 4 GPS coordinates.
Oh.
So when you combine the 4 coordinates that they have with the 7 coordinates from Price, you get this map where some of these coordinates are laying in lines between the other ones. It almost seems like you could draw flight paths between all 11 of these locations. So I was wondering if you looked into very much the GPS coordinates that he had given.
Yeah, I'm slightly embarrassed to answer that question. My position, I've been very associated with John Burroughs, who, of course, didn't see a triangular craft. And all the witnesses saw something different. But in fact, you guys will know that one of the side effects of that type of high-frequency non-ionizing radiation and plasma effects is actually altering your perception. And I think that everybody saw different things. It doesn't mean that they aren't correct. It was only their personal reality. That's a kind of a cop-out for me. knowing John quite well and knowing when the ASCII binary code was revealed, that came out while they were filming a major documentary, and Jim kind of pulled out a couple of pages from the notebooks that nobody's ever mentioned before. And and of course the filmmakers loved it. But when we looked into it, Jared, you'll be able to understand this. This was December 1980, and the code, the binary code, why would aliens use binary code? But the binary code type, as far as I know, and you can correct me on this, hadn't actually been written. That type of ASCII code was a development of ASCII code which came out in the 1990s. So how on earth did he know about it? And it was after 1990 that he revealed it. So and then the other thing about the GPS coordinates is that Rendlesham is actually east of Greenwich, London, which is the zero meridian line. And Jim Penniston didn't know that, and wrote down a coordinate from the Rendlesham that he was given by the aliens in this modern ASCII code. And he wrote it down as if it was west, because he lived his entire life in Illinois and Wisconsin and everything, and he didn't realize it was actually should be a plus east number. So for me, I have a lot of problems with it, and and it's pointing towards star bases and the pyramids of Giza. I'm just going, get on with it, mate. It's fine, but it's not my story. The story is why did it happen? Sorry if that's a bit negative.
No, excellent critiques. Thank you very much for that.
All right. I'm a bit embarrassed to say that. I mean, and Jim is a great guy. And the other thing is that Jim often doesn't reveal that he also had a VA settlement due to injuries. All of them were injured. They had skin problems, they had eye problems, they had trauma, psychological trauma. And then John Burroughs specifically had this internal organ failure. He was 20. He was a security officer at Woodbridge specifically, although in Bentwaters and Woodbridge interchangeable for them. And he was a fit young 20-year-old as a dog handler, and he had his heart valve ripped open. And so it didn't shut properly. It was torn into filaments, and he was breathless and had to have major surgery. And that was Kit Green from CIA said that that's a definite internal kind of heating effect from high energy plasma, probably. So as you guys are all dealing with dangerous stuff, to avoid that kind of stuff,
Oh, Simon, absolutely amazing. Oh, actually, can I jump? I want to jump in really quick and do a super quick share. I want to share a book. I should share Simon's channel too in a sec.
That's okay.
So when you mentioned the forward nuclear bases, and that was something that wasn't known, that brings me to Robert Hastings' UFOs and Nukes.
Mm-hmm.
And so I'll just put that up there. I will drop a link in for that. This book is absolutely amazing. And he details this nuclear correlation, which is kind of what you were getting at, right?
I mean, I don't really like the nuclear correlation. I don't see why. Why would an ET come? But in this, I'm reporting the facts. In this case, it was definitely really something to do with Woodbridge. Bentwaters also had tactical nuclear weapons. It was a forward Air Force base. At one time, they had fighters with air-to-air missiles with tactical, small nuclear missiles. This was all in case the Soviet Union invaded Western Europe. But then later they changed. And that's all they had there. But Woodbridge had the serious stuff. If you go to Woodbridge, you can see where they kept the in a sandier way of having a safe way of storing large hydrogen bombs. They would have a store for the bombs, and then they would have a store for the core, and those core stores are still there. And that was part of this forward base, which is all moved to Scotland. But yeah, so yeah, there was a nuclear connection. People have reported at the incident that some of the effects they saw seemed to be hovering or shining lights down onto the sensitive area. I mean, Woodbridge was a hell of a tight base. They had triple fences with dogs between and shoot to kill. I mean, British people didn't know what was there, but if you wouldn't want to stray into Woodbridge. And one of the strange things that I've discovered is looking at how all these physics laboratories were powered. I really got down this road that the world's largest nuclear power station, which is called Sizewell A, was built in 1957, then operational in 1962. It's right next to Orford Ness, and they also had this place called Cobra Mist, which is a big weapon system with Marx generators. So they need a lot of power. But I contacted the electricity grid people and eventually spoke to the woman who runs it in that part of England. And she told me this great story. She said that Bentwaters has 33 kilovolt supply, and they use it for their radar and they use it for the hangar doors. She said, the strange thing is, little sleepy Woodbridge, there's nothing there. They have triple redundancy of 33 kilowatt supplies. I put them in, she said. I wonder why they need that. I was going, oh yeah, right. Yeah, so they had, real triple redundancy there. Woodbridge is the answer. It also is orientated in a way which is somehow weird. I've yet to get to the bottom of that. A lot of people have been telling me you should look at where it's pointing. I don't really understand why, but yeah. Thanks, Tim. So these are recent films that I've been working on. Earth Spin Generator. That was a good one. That was great. I love Michael Faraday, and I heard these guys at Princeton who have been proving and looking at the disconnection between Earth's gravitational field and could you use it to generate power here on Earth, and they have a small effect. So,
well, and I know that your channel, you were supported by Patreon. I'm going to drop a link in there, and Jeremy Riss is supported by donations on his channel as well. So I'll put up Alien Scientist in a few moments.
Sure.
So I wanted people to visit this and realize that they can help support your work through Patreon.
Only if you want to. It's entirely. I mean, YouTube is a nightmare. I mean, you get a couple of bucks for 1,000 views, but I mean, having 300 or 400 patrons sending maybe $2 to $3 a month is a seriously good way of actually funding your electricity bill as a filmmaker. It's fine. It's much better than the YouTube model, as you would know, Jeremy. Definitely.
Okay. Yeah. Again, Simon, thank you so much. It's absolutely amazing. So, Jared, I think you had another question. Did other folks have questions? Or
First off, I love how you were able to connect and triangulate the thing between those three SRI places. Like that is just I do have another aspect though of the craft itself. I was wondering whether you could critique that. So supposedly there was like hieroglyphic symbols on there that people have tried to decode 15 ways from Sunday. I was wondering, aside from the binary stuff, which sounds like it's bunk, the hieroglyphic stuff, is that also bunked? Is there maybe a little bit more credibility to give to those, or?
I stick to my point that Jim Penstone's reality is Jim Penstone's reality. I mean, John Burroughs is right next to him. He didn't see a craft. John Burroughs got wrapped in the phenomenon, and others, Ed, who was there, didn't see it. And then later, and it only stayed there for a short time. There definitely were triangular marks in the forest, and there were kind of broken branches and burn marks. I mean, it's possible that something was there. The other thing that again, people totally ignore. They're much more interested in the triangular craft. But what I know is that a few weeks just before the Rendlesham Forest incident, they had built a few months before, they'd built a C5, Galaxy C5 pad at Woodbridge at the secure end, and a team had flown in full of equipment from Wright-Patterson and a team of OSI, Office Special Investigations, to debrief people after the experiment. So that was what was really going on. And a guy I know who is a mechanic working on one of the A10s at Woodbridge, saw in the forest these lights being set up and equipment. And then I've also spoken to the other thing you need to know is that Woodbridge is also the base of space recovery. So Air Force has a recovery team that will bring back downed aircraft, but also anything from space, like satellite recovery. And that was Woodbridge. I mean, and they were there that night, and they were flying around in helicopters, dropping things into and out of the forest. And then while the event was actually happening, they got relocated. I got this from people. They were relocated to a RAF base nearby so their helicopters and their assets wouldn't be damaged, because they were actually on Woodbridge, and it was over Woodbridge that the event happened, and in the forest. So there's way more to it as a practical thing than people want to talk about. All the films, all the research, all the books talk about Jim's effing triangular craft, which might or might not be true. It's in his reality, it's true. It might have hieroglyphs, it might have ASCII code, it might, whatever. But that's not the story. The story is, why is it Woodbridge? Why is it Rendlesham? What was round there? What were SRI doing? What was the other thing is, it's 1980. It was the Cold War, and Britain had just got a new Prime Minister, Margaret Thatcher, and a Defense Secretary, Michael Heseltine, who were desperate to get American money. And they were saying, oh, we've got British physics. Come and look at it. We've got directed energy weapons. We've got advanced radar. Two things. We've got metamaterials. They do, and could we sell it to you? And so it was definitely a co-production between UK and the US. The UK closed down Eastern Radar, which is the big Cold War radar just north of Rendlesham Forest and Neatis Head, and told the guys there, when you see things on your scope that night, ignore it. I've spoken to the radar operator. I mean, so there was something going on. Members of the public never dialed 911, 911, or 999 as you do in Britain. That was ignored as well, because the whole thing was planned. Then what actually happened? What did they evoke? What actually happened, I think, is highly strange. I don't think what actually affected them was human technology. I think it was something really weird. But, and that's suddenly, again, as I said, this week, with Ross and I talking about this dog whistle thing, it seems like there is a way of calling stuff, maybe. But who knows? It's good subject.
Yeah, I'm skeptical as well, especially with the stories of the proximity of these other characters and their equipment. At that time, BAE was still Marconi Aerospace, as you recall. Yeah. And Marconi Aerospace, there's a Marconi scientist death conspiracy.
I know about it, yeah.
In 1980, 2 years after the Rendlesham Forest incident, a whole bunch of scientists start going missing and wind up dead in mysterious circumstances and stuff. So wonder if there's any connection there.
There is. Yeah, the Marconi scientist death is horrific. And they were all working at Ipswich and at Martlesham, which is right next to Rendlesham Forest. And they were working on something quite odd. I spoke to one of the widows, and she said just the weirdest thing. She said her husband was a scientist. He was actually a computer scientist, and he would come home at night and said, "They're getting me to work on the weirdest shit. I'm not going to do it." And, he was one of the people that supposedly committed suicide, but the suicides were rubbish. I mean, they were just really strange. My inside information is that they were knocked off. It was the Soviet Union, but I don't know. And also, Jeremy and everybody, it wasn't just British Marconi scientists. There was a whole bunch of people doing similar research in Europe as well who died at the same time. There was a wave of science deaths. Fascinating.
Yeah, it's there's so much is wheels within wheels. But the thing that gets me is, and again, I know that you're not a giant fan of the nuclear correlation idea, but
Well,
man, that jumps out. What got me about that was, for me, when I started researching it, like
yeah.
especially here in the United States, right? Because that was where Robert Hastings, I think, focused primarily. I mean, it wasn't just it wasn't just nuclear weapons storage. It was like nuclear processing, refining, the whole nine yards, as well as medical facilities. And then, as you know, over in France, right, they've had massive waves of
Yeah.
UFO encounters at their nuclear reactors. So, I mean, I'm not sure what it is, but for me, it's so when you mentioned the forward military deployment, right, the forward nuclear deployment, I was like, wow, that's, yet another one. So
Yeah, France has 55 nuclear reactors. The lights are on in my house because of them. Thank you, France.
Um, has anyone done research into the type of burns and sicknesses these people got? Like, what could have accounted for that?
Yeah, all right. Great question. So British MOD did this thing called the Condon Report, which was when Nick Pope retired and they closed down the UFO desk. They just stopped looking at reports, and so they hired this guy called Ron Haddo. I shouldn't tell you his name, an MOD officer who was a physics background, and he wrote this report. And in the report, Mark, there's a tech lookup table done in, I think, Canada. There's a Canadian reference in the 1970s where it's the exposure of humans to all levels of non-ionizing radiation, radio frequencies, radar, standing in front of a radar dish, and then way up. They must have done it with, I don't know how they got the information. And there's a correlation between internal, external, sunburn, eye burn, and a lot of concentration on psychological effects of how it makes you feel at different frequencies, which definitely seems to be what happens. People, in the classic 5 observables, I mean, it's the 6th observable which came out of these injuries is effects on humans. It's well known, say, for example, that blue shift frequencies that blue shift can damage skin and things like that, and that blue shift is maybe a sign of an extraterrestrial drive mechanism. Who knows? I mean, I'm just repeating stuff, but I mean, they know about the effects, and John Burroughs is like really of great interest. I mean, he got immediately contacted by this Dr. Kit Green from CIA and Gary Nolan, who are interested not only in his medical history, but also his current state. And they continually doing DNA testing with him. They're very interested in how it affected him, because he was, he went inside an effect, which was weird.
So we're talking non-ionizing. That would have to be ham radio, gigahertz, microwaves, and up to X-rays, roughly, where things start to get a little crazy. So high level.
That's what they say. Yeah. They. And I'm slightly confused. Maybe you guys can help me on my basic science here, because they also talk about plasma, but of course, plasma isn't ionized. Is ionized. I think they're meaning non-nuclear. They're talking about non-radioactive effects. I don't know.
Fire is plasma. It doesn't, just because basically plasma is anything that heats up to a point where it loses its electrons and becomes sort of like the fourth state of matter.
Yeah. I mean, I wonder if it's like microwave stimulated plasmas or something like that, right? And so maybe the microwaves are what's doing it. One thing that I've read is and you guys probably know more about this than me, but like the cranial cavity has a resonant frequency for microwaves, right? And so there are a few frequencies, and it's a little different for everybody because everybody's a little differently sized, but like apparently there are some frequencies of microwaves that resonate inside the brain and can cause a lot more damage than others.
Oh, I know all about that. Yes, I've experienced that firsthand.
I bet you do. Turn it off. Yeah.
I mean,
One of the Jim Panister things.
There's a reason why they call it a tinfoil hat conspiracy. This is actual tinfoil, by the way. It's not aluminum. And it does protect you from microwaves.
Wait, is that a tinfoil ball cap? Oh, that's nice.
Oh, that's very nice.
Yeah, it's a tinfoil, and it's actual tinfoil. It's not aluminum.
Okay.
Somebody sent us 20 SAKs, whatever that is, and is asking this question.
Yeah, that's a great question. I would love to know more about this black goo thing, because it ties in. The black goo supposedly was part of the Southern Atlantic conspiracy as well, where around the Falklands, where they were doing ionospheric nuclear testing in their atmosphere. And I don't know much more about what the goo was. All I do know, as I say, from Carl, S-E-K, thank you very much, was that the widow said that their husband was working on weird stuff. Could be anything.
Well, so I should preface this by saying, so Jeremy's channel is monetized. He has a donation box in place. Again, Alien Scientist. In fact, do I have it up? Yeah, let me put his website up real quick so you guys can see it. So donations, if anybody is making donations on his channel, they go to his channel. APEC itself is nonprofit. And we're non-monetized, so I'm happy to promote your guys' stuff. I'm happy to promote Jeremy's channel. Just be aware that like any donations or something like that go to him, go to his channel, and anything on Patreon, of course, right? That would go to you. So
sure.
Yeah, so Alien Scientist, I meant to put this up a few minutes ago. I was just waiting for a good opportunity, and I'm going to put the link in here as well. Jeremy, thank you for rebroadcasting APEC on Alien Scientist. The URL is right there, and again, I mean, he's been doing this work as well as you have, Simon, for years and years and years, right? And built a massive audience. So,
yeah, it's interesting. And you meet a lot of people. It's good stuff. Yeah, it's good. If only YouTube actually paid properly, it'd be better.
Can I ask
So, in terms of radiation protection, silver is the best, and we actually have silver-coated nylon hoodies that when the radiation gets high enough, we put those on, and we look like Darth Vader.
Fantastic.
See that, and that's crazy for the new millennium. Tinfoil hoodies, right? There you go. Tinfoil hat didn't do it.
I love it.
He's going to put one. I've worn those hoodies. They're surprisingly comfortable.
Oh, great.
Although it is kind of weird. He did a couple experiments where we all wore
great.
those when we visited, and it did feel like we were trapped in a druid rally. So,
oh yes.
Yeah, there's the
and it comes with a burqa too.
Oh, it's great.
Yeah, so if they were just wearing one of these at Rendlesham Forest, I think they would have been fine.
Oh, you'd be safe, mate. It would be perfect. You would not be affected. Yeah.
But I mean, being more serious, this is part of the long and complex kind of hidden history. And there is so much dirty laundry out there from the Cold War era, right? I think the JFK files reveal that, So I don't know. I mean, part of the 21st century is going to be figuring out exactly what the hell happened in the 20th century.
Of course. I mean, and Jeremy, I don't know if you've come across this. I mean, you get to the point where you're feeling like you're pushing real kind of slightly tough boundaries. I certainly have been warned off by various people saying that's probably not a good thing to talk about. Do you get that?
Oh yeah. I mean, my interview, I did an extended interview with Sal Pays, and he was just like, "You're gonna give stuff to the enemy, man. Be careful. Like, you don't want to be too loose-lipped about the technology, and really talking about technologies and stuff you shouldn't be, because you never know who's listening. Our enemies are listening. They're watching every step. I mean,
Sure.
It's got a
So
point, you know.
I haven't had warnings like that. I would say the thing that I've heard and the thing that I worry about is this new push into psionics and consciousness.
Yeah.
And this is just me, Tim, right? Like just
new. This is
speaking for
30
myself.
years old. The Stargate project and all that stuff is like 30 years old. This is not new, Tim. This is being recycled.
Well, it's
Yeah,
recycled, yeah. But the part that troubles me about it is I'm actually into consciousness stuff, but like when you mix those two, there's this part of me that's like, is this too much, too fast? Is this going to scare the crap out of the general public? And how do we make sense out of this? You know?
Yeah.
So I mean, that's just where, and I've been there for ever since the. I mean, it felt like we started down this road with David Grush. And the James Barber thing was like next level. And that was where I was like, man, I feel really uncomfortable just in general. Right. Like
when he said that he was hired to infiltrate Stephen Greer's group and take out whistleblowers and stuff, man, like what changed you? Mike Herrera's story changed your mind to go switch over to the good team now? Like, how do we know you're not part of the bad team still? I just, I'm very skeptical of all these people. I want proof. I want science. And, you know, I really feel like they have the technology to do this. All the experts that I've interviewed talk about ECCMs and their ability to fake all this stuff with spoofing technology. And it's not that hard to tell everyone you're summoning aliens and create this whole psionic narrative around that and then spoof people with you know, the fake technology that you're controlling behind the scenes. So that's what I think is going on. And I'd love to be proven wrong, but I don't think I will be.
Okay.
Well, so Simon, I should ask, are you coming to the United States in the next couple of years or so? Because we have conferences that we will drag you to.
I think if I went through JFK security with my iPad, they wouldn't let me in. I think that would be bad. I don't know. I mean, yeah, sure. My wife's from Hawaii, and we have family in the United States. And, you know, I worked there. I lived in Wisconsin for 10 years. So, yeah, no, I really miss it. But I think right now, I think it's kind of slightly difficult for a European citizen.
You'll be fine. You'll be fine.
You'll be fine.
When I fly with my camera gear, right? And I carry my camera gear on my back. And so my bag is full of like the camera and lenses and charging equipment and like God knows how much electronics. And the interesting thing about security theater in the United States is they never hassle me about it. I plunk down this job. I mean, like they'll have some guy with a laptop and they'll be going through it with a fine tooth comb. They were like, is this real or is it loaded with something? Like I plunk down my bag full of crap, half of it I don't even know what it is, and they're like, what is that? Like, it's a camera. Okay, have fun.
No, it's profiling. I worked at an airport, a private pilot, and I used to hang out and actually be the desk agent at a small airport. And we got trained by for security. And the thing that you really need to know as a flying passenger is when at the gate they ask you, "Did you pack your own bag?" That's a really leading question. That is the question, because don't look shifty. Say you did, because they immediately, you are given scores from your car is looked at before it approaches the airport. The number plate is searched. Parking, your demeanor on people are looking at you, how you're walking. The gate agents, as I was trained, are unbelievably good at spotting bad people, and then you are given a score. And then when you go through TSA, if you're pulled, it's because somebody in the chain from you getting off the train, parking your car at the gate through TSA has flagged you, and you'll get really. And Tim, you're fine. I mean, they're not interested in bits of technology. They're interested in bad people. I mean,
Yeah. Well, and for me, last year I finally did the TSA pre-check also for anybody who's flying. And that actually it helps a little bit. Although to be honest, the only difference, the line is like 5% faster and they don't ask you to take your belt off. And I'm so used to it. Like last time I went to the airport, I had my belt and my shoes off and they're like, "Aren't you pre-check?" And I'm like,
oh yeah.
Can I ask Simon a follow-up question on one of the things he said?
Jared. Yeah.
So you mentioned in Europe that there were scientists that were killed in addition to the Marconi scientists. I was wondering if you could elucidate on that anymore. Specifically, as far as I understand, the Marconi guys, it seemed like most of them were working in power, RF, electron control measures, countermeasures. I was wondering if any of the European scientists also fell in that same niche category, or if they maybe researched other things, or how somebody could follow up on the European scientists.
Yeah, I don't know what they were doing. Sorry. I mean, I know that there were people in France and Italy who also died mysterious deaths who weren't working for Marconi. So it was it makes sense that it was definitely a military physics project that they were all working on. As I say, my inside information is that it was pretty deliberate. So the coroner said that some of the suicides were farcical. You know, that a human couldn't do that to themselves. It was really nasty. I did a film.
A bunch of them happened in the same town.
Pardon?
A bunch of them happened in the same location. Like people were working for this location were all goaded to go travel miles and miles to this one town where they all mysteriously died.
I'll bring Gary back in.
Yeah, hi, Gary.
Extremely suspicious, Simon. Sorry to interrupt you.
No. And the psychological behavior. I really worried that whoever it was that has really a very strong way of influencing people's thought process. It seemed that they could have committed suicide if they somehow were persuaded. They were put into a mindset where they did kill themselves. And what technology would that be? It's like, don't turn that one on. I worry about that. I mean, we know that we can affect the human brain in nasty ways, and certainly the Soviet Union has done a lot of research into that, going back into the 50s, into that type of. They saw it as a weapon system, definitely. So what's happening now at Rendlesham? It's really interesting. It's now a business park. They closed down both the Cold War's ended, and the Bentwaters is now kind of where you park your big truck and you have a few antique dealers. And one of the things that I discovered is that there's a small film company who ran one of the hangars, and they were lifting up slabs underneath the hangar, and they found some of the biggest power interconnects that they'd ever seen, and then Woodbridge is totally unused. Apart from it's still retained by the Ministry of Defence, and they recently refurbished the runway. There's really weird things going on there. Woodbridge in World War II was a FIDO base, FIDO, where it was a lot of World War II had really bad weather, fog and smog, coal burning, and a lot of Allied airplanes, but young pilots found it hard to find rural airfields, so they all flew back into Woodbridge. And the FIDO system burnt gasoline down the runway, each side of the runway, and lifted the fog, and also made a lighting effect that they could see while crossing the North Sea. But it turns out that the FIDO base, the fuel for that came in underground tunnels and pipelines from Bentwaters, and those tunnels are still there. So you can actually walk underground from one air base to the other. And somebody said that there was a project looking at turning some of the pipes Oh well, this is probably rubbish. But they were saying that the pipes were kind of looking at the same kind of diameter as waveguides, and was it possible that they were utilizing the pipeworks as microwave waveguides? Who knows? Who knows? Well, thank you very much for watching my film. I will carry on editing, and it will come out. I'm hoping to get a statement from Jake's organization in it. Ross Coulthard and I are talking about it as well, because he's interested. He also, like me, knew the term dog whistle from years ago. It's not a Jake Barber's organization name. It's the concept of actually calling UFOs has been around for a long time. I mean, as I said, if you remember the colored lights and the music in Close Encounters, that was based on a man who developed laser surgery devices in the Midwest, and he was employed to actually put different EM frequencies in our visible spectrum in lasers, firing them up into the sky. And he also liked to use tonal sounds as well. And that goes back to the 1960s. So, you know, the idea of summoning or evoking the UAPs has been around for a long time. It's not new. Would you agree, Jeremy? Yeah. Good. Okay. Well, Simon, thank you so much. Thank you so much. I think we're kind of winding down on the Q&A. Again, an absolute pleasure and a true honor. Thank you for screening what you have of the new film for us. Thank you for walking us through Rendlesham Forest. This is amazing. I would love to have you back in the future when you have the time. You know, it's wonderful. Wonderful. All right. Well, it's past my bedtime. So okay. Yeah. Well, guys, before you go, let's put our hands together one more time and give a giant applause for Professor Simon Holland. Thank you very much. Thank you again. I genuinely and truly thank you so much. Yeah. It's a pleasure to be associated with you guys. It's excellent, and I think APEC's excellent. So keep up the good work, and we'll be in touch. So I'm leaving. Bye bye. Thanks again. Bye.
Tim, do we have time? I have a question for Gary Stephenson. Oh, maybe after.
Maybe we could come back to that. Actually, I was going to go to Jen Nielsen.
Go ahead. Go ahead.
Oops. And it looks actually, Jen, it looks like your connection is freezing a little bit.
Oh, well, if it is frozen, I have something to kill time.
Okay. Yeah. Well, yeah, I would say go for it.
Oh, okay.
And Jen, are you able to upload your PDF?
Hey Gary, awesome talk. I also like Simon's talk too, or video. That was amazing. If he had just edited that in a few hours, that's impressive. But so Gary, just a quick question: have you considered doing a quick Josephson Junction experiment with a manually constructed Josephson Junction instead of a integrated circuit fab design?
Yeah, we haven't pursued that yet because those are both devices that are more difficult to build.
There is a way. I actually spoke to Brian Josephson about this recently. There's a way to make it repeatable.
Okay.
If you have like a sprung surface with like niobium on one side, and there's ways. We can discuss it afterwards.
Yeah, I mean, Fontana originally, his original paper was for a bulk device such as you're speaking about. Yeah. Mm-hmm. But
we'll discuss it.
Been able to find out how to do them inexpensively.
Okay. Yeah, well, there's a way. There's these new cryo coolers from China that are for now still available, and they're just like $700. So you should grab one while you can.
Okay.
Yeah.
Wonderful.
Okay. You can stick some Josephson Junction stuff on the end of it. We have some 3D models for it already.
Yeah. Well, Michael, let me get to Jenny and see. Let me see if we can get that rolling. She's having some connection issues, but I'm going to take everybody back out. And so there we go. Okay. Well, Jennifer, welcome, ma'am. Welcome. So you have a presentation for us on, let me see, a novel quantum gravity framework within 6-dimensional space-time, proposed quantum system that is a bundle of space-time that conforms to a metric tensor system of general relativity, and the system is innately a quantum field. So this is heavy-duty material. So if it's okay, let me bring your presentation up. And do you want to take it away for us? And it looks like you're having some connection issues, but sorry, Jennifer, can you hear me? I'm not sure if the signal is coming through. Okay, so I'm going to take Jennifer out for a moment, and we'll see what's going on there. I do have a presentation. Why don't I do this? I'm going to go to Daniel Davis' presentation. That's the safest. Okay, and I will take my headphones out because that acts a little funny sometimes when I'm playing YouTube videos. Okay, so let me share this tab very quickly. Actually,
my theory.
oh, you're back. Okay.
Yeah.
Okay. Yeah, it cut out on us just for a moment, but yeah. Do you want to take it away and start presenting for us?
Oh my gosh. Soon. Yeah. But yeah. 1 second. Okay.
Yeah, you know what? That's okay. There's no rush. I have I think a half an hour presentation.
Okay.
Let me see. It's 40-minute presentation from Daniel Davis on many worlds theory. Do you want me to do that first?
I'm good to get going, or if you want to swap around, I've told some people 4 p.m. is the time for Central here. So
4 p.m. Central. So that's 2 p.m. my time. Okay.
Yeah. Is that?
Or we could just do open discussion for another 20 minutes. Why don't I do that?
That sounds great. That sounds perfect. Yeah, wonderful.
Perfect. Is it okay if I leave you in? I'll take the presentation down. I'll bring the gang back in here.
I could do a presentation for 20 minutes if you like. I already have it uploaded.
All right.
Go for it, Mark. And I see our gang is growing, as you can see.
Alrighty. So this is the presentation that I gave at Deep Tech Week that came to New York City. Basically an update from the lab, and we're showing off our latest and greatest. So anti-gravity with present technology. Explain to you guys why we call it anti-gravity in a moment. For all of you who followed our work in the past, there are some new things in here. It's not all just a repeat of everything. Now, if you notice the letters around anti-gravity with present technology, they're glowing this kind of gold color. Now, the reason why UFOs glow that orangey color is because when you ionize oxygen and nitrogen, that's the color you get. It's kind of like a yellowish gold. And at higher levels, it might have a little bit of tinge of red in it too. So one of the main problems with space travel is these two equations, these two little math things. E equals mc squared, energy and mass are equivalent. So if energy and mass are equivalent, then you can't exceed the speed of light, because they're equivalent at the speed of light as a ratio of the speed of light. So as you approach the speed of light, mass gets heavier, and therefore you need more energy in order to move it, and that eventually doesn't allow you to surpass the speed of light. And then you have the rocket equation on the bottom here, which is the delta V. The movement that you're going to go in one direction is equivalent to the velocity of stuff that you shoot out the other side, and divide by how much mass you're shooting out the other way and in what speed it's moving out. So if you shoot out delta V in that way, you're going to get delta V in this way. For every action, there's an opposite and equal reaction. So you want to get fast action in that way, and you move forward in the other direction. Now, what these two pieces of math that restrict our space travel have in common is this quirky little thing called mass. So we're going to dive into mass and try to solve that problem. So origins of mass. Now, I hate to break everyone's bubble, but the Higgs boson is maybe about 1% or less of where mass comes from. Most of it comes from strong nuclear binding energy. That's what holds protons and neutrons together inside the core of the atom, the strong force. Relativistic energy, like from moving at near relativistic speeds. I mean, if you were driving down the road, you could build up a little bit of kinetic energy that could convert into inertial mass, but at a very small level. So those are really negligible. And the gravitational inertial effects are proportional to all of those things put together, both the strong nuclear binding energy, the Higgs mechanism, and then the relativistic things as well. And to a lesser extent, probably kinetic or potential energy stored in the system. There are some propulsion systems that use the kinetic or the potential energy of the system for its relativistic mass in order to shift things around. So if we're going to be concentrating in on the that binding energy where 99% of it is stored, there's only one known way to manipulate it. This is not science fiction. This is science fact. This was discovered in 1953 by Albert Overhauser, and he discovered some other interesting effects that happened with it. Dynamic nuclear polarization, subatomic particle spin alteration, where you're orienting the spins of subatomic particles. Orienting electron spin is known as magnetism. When you have a magnetic field, when you have magnets like these, what they're actually doing is orienting the spins of any electrons that are free to be spun up. So it's not, they don't attract to my hand because all of the electrons in my fingers are actually bound to each other. They're being used to covalently bind things together. That's why a magnet is not attracted to my hand. However, for a piece of iron, let's say a piece of steel, there are many free electrons that allow the magnet to bond to it. But for subatomic particle spins, that would be dynamic nuclear polarization. So it's a deeper level of magnetism, but on a subatomic level. And the way this is achieved is we first go to the electrons because they're easy to manipulate using electromagnetism, and we orient them and we resonate with them. So we apply a magnetic field that makes them all resonate at a known value, which we can then perturb with a microwave source. And by pulsing this microwave source, we're able to energize them up, and they sort of spin flip. And then while they're spinning down, they transfer their orientation to the core, because the electrons and the protons are kind of like bound together through this hyperfine coupling, which holds them together. So by orienting the subatomic particles, we're now manipulating the strong force, which is where 99% of mass energy comes from. And by manipulating the strong force, or where the mass energy comes from, we're also able to alter the way the mass interacts with the universe. Another way to look at this is if mass and energy are equivalent, then subatomic particles are like electromagnetic energy that's spun in on itself. And when you have something rotating, you have like a gyroscope. So if a gyroscope is free to move along its plane and axes without any restriction, it can move like this. But if you try to change that orientation, you get a torque 90 degrees to it. Now, subatomic particles are not spinning nicely. They're not just like rotating around in a nice coherent manner. They're actually wobbling around in many different directions simultaneously. They're wobbling on all axes at all times. So when you were to move an object that's wobbling around like this and spinning at the speed of light simultaneously, what happens is you change the wobbles of the subatomic particles. So when you throw an object through space and impart in it, let's say 20 joules of energy, the total mass energy of the baseball is probably in the quadrillions of joules. But you just imparted 20 joules of energy. How did that coupling happen? It happened by the subatomic particle wobbles changing. So by orienting those wobbles, now the craft is free to move along its plane and its axes without any restriction, because you no longer have that coupling. just like a regular gyroscope. However, one thing you do lose out on is the ability to turn the craft. You can't do a barrel roll, which is why flying saucers have never been observed doing barrel rolls. In fact, many observations of flying saucers are when they slowly change their orientation before shooting off at a crazy speed. So we would, and there's another like 6 different theories to explain why dynamic nuclear polarization is key to this anti-gravity effect. So this is the original paper when dynamic nuclear polarization was discovered. It was right after World War II. We had all these gigahertz microwave equipment floating around from radar surplus from World War II, and the scientists started playing with it and noticed these resonant effects. Polarization of nuclei in metals, it's actually lower frequencies, lower field strengths are easier to achieve in metals, because to achieve these effects in metals, because you have a problem called the skin depth effect, where as you go to a higher frequency, the microwaves just bounce off the surface. They don't penetrate at all. So you want to go to a lower frequency to penetrate better and have a better coupling. And he was doing this actually, I think, sub-gigahertz, and he was getting pretty strong effects. But he noticed, and this was in his first paper on the subject, and since then I think there was only a couple scientific papers afterwards before he just went quiet on the subject. But he wrote that they're doing some math over here to figure out what the relaxation time of the dynamic nuclear polarization is. So this is the amount of time that that it takes for this oriented state to disappear, to run back to thermal equilibrium. Now, thermal, that's the key. The colder you make it, the less thermal agitators act upon the core of the atom, and the longer it has to maintain that state before reaching thermal equilibrium. So they were cooling down samples using liquid helium, and it would get the times would get longer and longer, but they were still 100 times faster than expected. And what he wrote over here, the shortest relaxation time that was found in this is a picture that's off screen, due to the spin current interaction, was inversely proportional to the absolute temperature. As you go colder, relaxation time gets longer. However, the observed relaxation time is smaller by a factor of 100 in the value given by theory. An important relaxation mechanism has been overlooked, so that the correct temperature dependence of T1 is yet unknown. I'm going to read that back to you. An important relaxation method has probably been overlooked. Now, what could that relaxation method possibly be? So years later, Frederick Elzevon came along with this theory, anti-gravity with present technology, and he theorized the answer was gravity. Gravity is acting upon the sample to do work on it, to bring it down from its oriented state, and you're maintaining its oriented state, then maintaining its oriented state is in fact anti-gravity. That's why we call it anti-gravity. It's not that we're not reversing gravity, we're fighting gravity, we're shielding gravity. We're shielding everything from gravity. And the way to achieve this is simple magnetic field, microwaves, modulators, and all that kind of equipment. The FM detector and the lock-in amplifier that he has over here, I don't believe it's necessary at all. I think he was just copying that out of another book. That's for spectroscopy. But most of the industry surrounding dynamic nuclear polarization is actually for detecting what's in the sample. What we're trying to do is make the entire craft the sample, and now we're weightless. But it's also great for figuring out what a sample is. If you have the magnetic field on the outside and the RF coming in, and you have a highly controlled environment, you're actually, through the SWR, the standing wave ratio, or the reflected power coming back, you're actually able to see when these resonances are hit. And because every atom has a different resonance point, you're able to know which atom you're dealing with over there. And this also increases NMR, nuclear magnetic resonance, signal to noise ratio, by making the atom itself more coherent, so that its ping back is stronger, for all those who know how NMR systems work. So that's his paper. Now, apparently They did run this experiment back in 1995 and got 80% weight loss before the company fell apart because of they had to give back the equipment, and they had disagreements between team members. So we tried doing it. This is some of the earlier versions back about like 4 or 5 years ago. Jeremy named this rig the EPR NMR laminar spintronic alignment rig. Now, that's pretty much what it is. It's although we're not doing any NMR in it. This little simple electromagnet that was made out of iron. We didn't have much money at the time. We did lots of shielding in order to protect the weight measurements, but we were able to see that something was happening. It looked promising enough to continue the research. Later, we got funding. We got this big ass electromagnet. This was a C-band for roughly 6 gigahertz setup using a klystron. I learned a lot about klystrons. Then we discovered that our magnetic field was not very homogeneous. We homogenized the field using a laser light in order to map it out, and a little Gauss meter. We mapped it out in Excel. We saw what the gradient is. We inferred from that an angle of what a corrective mirror would be, or corrective lens, and we machined out on our CNC machine one of these. Essentially, it's a magnetic lens. So we placed that on the plates of the electromagnet, and it corrected for that for those inhomogeneities in the field. Later, we upgraded the system. We got this Faraday cage, the Faraday cage was actually previous. Got a cooling system for the electromagnet, and started running varieties of various tests. Now, in one of the later tests, it was kind of, at this point, it was all being done by hand. I was turning a knob manually in order to see change the magnetic fields as we sweep through it, or changing everything manually. And it was like watching grass grow in slow motion. You have to sit there for the entire time that you were running the test, slowly turning knobs. So I worked with this guy out in Pakistan. He helped me program in to control everything via LabVIEW. And that's the system we have today. It's been constantly being upgraded. The first time we ran it, I turned everything up to a gazillion, cranked everything up to 11, ran the system, and went out of the lab for a couple of hours. When I came back, I saw lots of cool stuff showing up on the screen. After about a month of analysis by David Chester and Falk, we realized there was a very clear signal that something had actually happened in that first test with the LabVIEW data. We wrote a paper on it. You can see over here, this is investigating a purported connection between DNO, dynamic nuclear orientation, and mass. This was published at the Experimental Nuclear Magnetic Resonance Conference, or ENC conference, out in California last April. And what you're seeing as the experimental results is actually 3 runs superimposed on top of each other. So it's not just one run, it's 3 runs that were showing the exact same curvature happening simultaneously. And the result at the conference was, this is amazing. This is something that's never been tried before, and they were all very curious to hear what we would have to do next. So since then, the machine behind me is actually up and running right now. This is a piece of equipment we picked up from Toronto from George Hathaway, and it runs at a lower frequency, 3 gigahertz instead of the 9.88 gigahertz. It has the capability of going cryogenic and under vacuum while running this test. Magnetic field is oriented vertically in this case. And actually, this machine is running right now as I give my presentation. So this is another variation of the test, and we're running samples both on this and the X-band system. We can't do them simultaneously. It's the same computer running the LabVIEW. This is how the sample is placed in there. It's basically a transmission electron microscope control arm to move the sample up and down, left and right. You can move it around inside the chamber, all in vacuum. So one of the next things we're going to try is this paper that came out a couple of years ago out of Japan. What they discovered was triplet state electron pairs, or two electrons that are kind of dancing together. They're acting as one. Might be similar to Cooper pairs, I'm not sure. But there's a couple different ways of achieving this state. When you include them in your microwave pulsed setup, the coupling to the core increases exponentially. We're talking 250,000 times stronger. So that's definitely something we'd want to try. This is induced in the paper. It recommends using pentacene and a p-terphenol. P-terphenol is also known as mothballs. So we're like using this pentacene thing inside of p-terphenol in order to hit it with a really strong light pulse, and that creates the triplet pairs, which should increase your dynamic nuclear polarization. So this is one of the next things we're going to try in the experiment, and this is how far we've gotten with the system so far. So we made p-terphenol or mothball crystals using that the Brigman crystal growing machine over there on the left, and we got some interesting crystals out of it. They smell to high heaven. We also made a paint out of pentacene styrene. This was recommended by Michael Perrone, and I infused it with xenon. Now, the reason why xenon is important, so xenon is the heaviest of the noble gases. And xenon has an interesting property that it maintains dynamic nuclear polarization for a very long time. We're talking minutes to hours. And one of the reasons for that is probably because all of its electron bands are full. So it can't interact with anything, but it still has a very dense core. So all of that can just maintain the spin without any without anything perturbing it. Another thing we're going to try is having a magnetic field internal to the device, and I actually have a system for that. This is a prototype of this next system. This would be the microwaves would be fed in through here. Obviously, this is plastic, so this is not the actual device. But the microwaves being fed in from the side, and if we can make the entire device weigh less, it would be more obvious that we're actually seeing a real effect versus just a change in the magnetic properties of the sample, which would also be interesting, but not exactly what we're looking for. And these are other projects that we're working on. You guys have seen the Pletnev gravity impulse experiment. That's in the top center. On the left, we have our current version of the rotating electrostatic field generator that has also been presented here on APEC. Bottom center, we have standing waves, warp drive system. That I ran a couple videos on that, but we haven't actually presented it here on APEC. And on the right, we have our vacuum system where we're doing T.T. Brown style systems and running tests under vacuum. And also, we also have inertial propulsion systems that we're testing. These inertial propulsion, that's like Bryant St. Clair's sort of systems. There has been 4 gyroscope systems that have been built here at the lab. The first one is on the top left. That was using 4 of the pre-built gyroscopes from gyroscopes.com. And we just put them on a pan and tilt system. It was all remote controlled. That thing sort of wobbled around. It seemed to be moving. The next one we built here at the lab, everything was built from scratch. That one sort of wobbled around a bit. And then the final one on that table over there, that uses 4-inch rotors. Those gyroscopes are really nice. And that thing does wobble around a bit, does move a bit. And Jeremy Reese came to the lab and leveled out an area of the floor using self-leveling cement. So we were able to test that on a ping pong ball system. It does wobble around, but the amount of thrust created from these devices versus the amount of weight and torque being imposed on them by the systems is very inconsequential. We're talking less than 1%. I don't think it's possible to get to a VTOL, vertical takeoff and landing system using these, technologies. The binding energy of matter is simply not strong enough to overcome the amount of wobbles necessary in order to induce thrust in this system. On the top right, we have the gravity diode. That's from Ted Pittman. He came down here for a couple of months, and we worked on that together. That was a really complex system. He also did some presentations on APEC. And on the bottom, we have finally the mercury vortex entry, or the liquid metal vortex. Basically, we're rotating a liquid metal around, and it moves faster on one side because it's thinner on one side than it moves on the other. So half the amount of matter moves faster on one side than it does on the opposite side. And what this does is it creates asymmetric centrifugal force. So the equation for centrifugal force is the mass times the acceleration times the speed squared. Now there's also the radius, but the radius is equal for this entire system. So if you have the speed being double on one side than on the other, you'd end up with a net force. And I show you how the magnets are used to couple to that, and there's a strong motor in the center. And that's it for my presentation. So thank you guys for watching. That's our update for April 12th. And happy Passover, everyone.
Mark, thank you, man. That is awesome. You squeezed that in. We're 2 minutes over the top of the hour. That is amazing. And thank you for doing the update too. That's for folks who aren't following, the work that you're doing is absolutely amazing. And like what I was saying earlier, is getting more and more and more technically challenging, right? And so, it's like pushing that rock up the hill, but you're doing it every day. You're making amazing progress. So thank you, man.
Yeah, you should also plug the conference we're going to too.
Oh, the UAP hackathon. We'll have to. Let me come back to that later in open discussion. I want to bring Jennifer in. Jennifer, how are you doing?
I'm doing great, Tim. It's great to be here.
Okay, well, let me take Mark out. So again, you are doing a presentation. This is your first one at APEC. Thank you so much. It is truly, truly wonderful to have you with us today. You are getting into heavy duty physics. So I want to forewarn the audience, but this is amazing. This is one of the kind of stuff that we love here. And this is real physics. You've worked with a lot of PhDs on this, and you are like in PhD programs yourself. So.
Yes, I'm a PhD candidate, and I have a master's in mathematical physics and a master's in philosophy of science, which actually has turned out to be helpful because it helps me conceptualize things more clearly. But basically, my life's ambition was to try to understand how gravity and the quantum field connect to one another, and I feel like I finally have a grasp on that. And what actually dropped out when I started working with this funny little bundle called the complex Hopf vibration, what dropped out was a theory that can encompass the standard model, all four forces, including gravity. So my theory has gravity without a metric, which is kind of like saying, what? You have gravity without general relativity, but it's like it reduces to general relativity in the classical limit. So what I've got is a quantum theory of gravity that is also a unified field theory, because it puts all four forces together and onto one thing. Now, what is the thing? When I try to talk to people about this, the first thing that everyone asks is, what is a fiber bundle? What is the Hopf vibration? I've never seen this. What is this? Well, it's an object. It's a mathematical object. It's a beautiful mathematical object that has a lot in common with Madeline Langle's thing that she talked about, the tesseract. And, you might have seen Salvador Dali's tesseract cross. That's the shadow of a higher dimensional object as it would look shadowed to our dimension. Or maybe if you could a cross section through the 4D object, like a physical four dimensions. I'm not talking about time, like the fourth physical dimension. If you put a cross section through this higher dimensional object, instead of just getting like a 2D cut like we get here, you'd get a 3D cut and you'd be able to see the whole thing, at least the whole thing as it appears here. And it would appear as a 3D object instead of not being able to see it because we don't have access to the higher dimensions. So in my theory, you can put everything on this little spinning apple, but it's actually a big spinning apple called the Hopf vibration. So which Hopf vibration do I use? Well, as it turns out, I'm actually working on shells of the infinite dimensional diffeological Hopf vibration, which is also a complex Hopf vibration. So you could technically keep going out as far as you want in terms of dimensions, but I've determined that the floors of 7 and 9 top out what I want to look at right now. So I look at S1 to S7 to CP3, and I look at S1 to S9 to CP4. Now, early on, I was working with the S1 to S3 to CP1, but what's CP? That's complex projective space. So does anybody know what complex projective space is? I'm going to check the live chat, see if anyone's like talking about it. No. Well, complex projective space is the space of the imaginary numbers, but projected out in such a way that you can work with it as if it's a space that you can move in and that you can do things with. So in my Hopf vibration, complex projective space, although I put phases on it, so sometimes I call it phase space, is the base which the fibers of my Hopf vibration wrap around. So let's talk about what a Hopf vibration is before I get into the base too much more. So hold on, I'm going to share my screen. Share screen. Okay. Yeah, sure. I'll let you do that. It's asking for some permissions. Okay, sorry about that.
Sorry about that. So I've got your slideshow up. You want to? Okay.
I'm trying to share a video. Is what I'm trying to do now. Hold on.
Yes. Okay. Hang on.
So here we go. So every fiber bundle has a base space, which is like a disk if you're in the S3, but mine it'll be more like a sphere. The fibers are which circle around that thing, and then the total space is like a torus. So here's what in a torus, meaning the shape. If you're okay, so this is going awfully slow. I'm trying to speed this up. Oh, there we go. So these are the fibers wrapping around the base space, and what ends up happening.
Sorry, I don't want to cause trouble for you here. Okay, here we go. There's the video.
Yeah, so this is what the Hopf vibration looks like.
Okay,
it's basically a bundle of fibers wrapping around the base space, which is a disk or another shape, depending on what level of the system you're looking at. Because I think of the Hopf vibration as n-dimensional. Like it can go as far out as you want, and you can come in and you can go at least down to like the S0 fiber view where you're looking at just points. And so this is what it looks like. It has the in my case, the central base thing is CP4, which is complex projective space 4-dimensional. And that's just a 4-dimensional space that includes the complex number plane system. So if people have questions for me about that, we can talk about that later. Stop screen now. Now present.
Okay, and do you want me to put this one back up, or do you?
Yes.
Okay.
So yeah, thank you. Sorry for that little excursion, but so I've said that my theory is a quantum gravity. Why is it a quantum gravity? Well, there's a single topological field which also emerges as a 4-dimensional regular quantum field. Not regular because it includes gravity, but it's a normal field that's kind of vibrating on top of this topological structure. So the single field covers both gravity and quantum mechanics, which has not, to my knowledge, that's not really been done before, except in terms of string theory, and to some extent, there's a few other theories hanging around that have done some things similar, but this is the most complete view I've seen myself, which is why I'm presenting it here. So why is it a UFT? It's a unified field theory because a single field covers gravity, and the gut, meaning the standard model where you have the strong nuclear force, the weak nuclear force, and the E&M electromagnetic force, and those are all covered together. But in my theory, they're covered together with gravity, which hasn't been done. And I've provided a testable, like, falsifiable system to test whether we've really unified with gravity. So why is it a theory of everything contender? Well, because I've popped out the particle spectra and I've got constants popping out of the theory like the universal G, but I don't have time to get into that today. So this is just another explanation of, like, here's the rings that wrap around the base space, and then you get this thing that wraps around it when you have all these different series of circles. And the complex version is a little bit more spirally, but we won't have time to get into that either. So the unified field theory in 9D space-time is this thing. And it kind of has to be this thing because I have examined every bundle that known to man, and none of them would fit the standard model and gravity in, except the complex bundle at levels above 7D. So this is, if you're gonna use spaces to conceptualize what's going on here, and without gluing different spaces together in kind of artificial ways with cross products or whatever, this is the bundle to use. It works. You can get stuff to do stuff on it. So your bundle is S1. That means just the simple line fiber. That's like your little fiber optic cable. S9 is what the total thing, what they call the torus, but it's really more of this hyperdimensional reflection that we're looking at. It's a stereographic projection from the fifth dimension and above, because we're just looking at the 3D version of it. So we're looking at a 3D surface of a multi-dimensional object, and we're looking at just that slice of it, but it's actually kind of a sub-manifold of the same thing. It's not like we're looking at something that you cut out from it. You're looking at a layer of it like it's a doll. And this is like a doll within a doll within a doll. You know, we've seen those Russian dolls. This is the 3D layer of the Russian doll, and we get to see that. So the total space is just this 9-dimensional object, and it's in C5, which means it's in 5th dimensional complex ambient space. And the base space is the complex projective space, as we've said before. Okay, so it unifies gravity, the gauge bosons, the fermions, and the Higgs. These are all the standard model fields. So everything is derived topologically, and I don't resort to using Einstein's metric, because his metric is a way of looking at objects that aren't inherently gravitational on a gravitational playing field. And since I have an object that includes that playing field in its own topology, I don't need to resort to a metric, which I haven't seen anybody else do, except with perhaps with the exception of string theory, but string theory has so many parameters and it's at the Planck level, so I don't hardly count it as a successful unification. But anyway, everything is derived that way. But then there's this other caveat. In my system, I look at time in the complex phase space. I parameterize that, even though I'm using it to do gauge theory and gauge fields to some degree. I'm also using it as a parameter space. And these uses of CP4 are completely complementary. They don't conflict with one another. So you can use the same space over and over again as many times as you need, as long as what you're doing with it doesn't fight some other thing that you're doing with it. By parameterization, I mean to say that all of these things that I'm parameterizing on there are actually part of the system as a whole. I just am using that complex space as a tracking system to keep track of all the aspects of time that are revealed by my system. So what do I mean by that? Well, since this is an object that's infinite dimensional, it can contain all the possibilities that you want to account for if you set it up that way. And so you can get a pseudo Hilbert space out of it. So you can get all the different quantum possibilities and probabilities, and they're all sort of real in the master fiber system. When I say sort of real, I mean like they're interfering with each other, and what's dropping out is this from our perspective, from where we are. But everything's out there, and we're just in the part that happen to interfere constructively or destructively, depending on how you look at it, to make our world. And so I'm going to start getting into time here. Time is relational and complexified. So this is just the S1. That's what we just, the little circles. You can get the hypercharge just off of those little circles. That's U1Y for people who do gauge theory. Role of the total space, S9, it unifies all the fields topologically. It embeds all these things, and it reduces to 4D physics pretty easily. That's a 4D slice. I prefer the sub-bundle, but I'll talk about that later. So the base space is an 8D real manifold encoding physical parameters, and it's also the foundation for the gauge groups. And again, these uses don't cancel one another. They can coexist. I've had some questions about that, but like there's nothing that prevents you from using the same whiteboard for two purposes. Although the gauge groups are like the shape of the whiteboard, and the parameter space is what I'm writing on the whiteboard, if that makes sense when I use this space. So altogether, I call this the time-space bundle because time is prioritized in some degree over space. It encodes quantum fields and gravitational phenomena. And you can map it to a metric tensor if you want to compare across with GR. So there are three metaphysics of time. If you've read St. Augustine, you know that he talks about, from God's view, all time is one and everything is happening at once, and he sees the whole unfolding. So that's eternalism. That's the block universe. My system includes eternalism. And the reason for that is that general relativity is built on the assumption of eternalism, because if not, why is it that you can see the same series of events unfold in different time orderings if all of those orderings haven't already happened yet on some level? And now I'm not going to get into the free will thing, because we don't know how people make choices, if we do make choices. But if we do, all the different possibilities are out there, as in the quantum system. I think someone was on about many worlds. It would be kind of like that. And we're just kind of selecting our way through choices in a hyper block of different possibilities. So it's not just a block. It's a block and a block and a block and a block, like one of Borges' libraries that just expands like hyperlinks forever in all directions. That's the hyper block, which is how I conceive of what space-time really looks like, at least if you're God. And then the evolving block universe says, well, the block is set up as we move through it. Like I create a block, like after I've gone to get milk from the fridge, there's a world line of me going to get milk in the fridge, and you can see me at every snapshot. That's the evolving block, because it doesn't include me going back to bed or whatever. It just gets to the point where time is now, or when I'm setting up my slides, all that's recorded, but now here I am here, and that's evolving and open. That's the evolving block. And then presentism is the idea that now is all there really is, and that everything else is just kind of illusory and disappears. But it's kind of an antithesis of the eternalism way. It's like in eternalism, everything's there, but here it's just ephemeral, and for a second, for a split millisecond, there's now, and it's gone before you realize it. But what if all of these views are true? What if we think about time incorrectly in general? That it's not that it hasn't all happened yet. Maybe at some level, everything's going at once. But maybe on another level, we're choosing the particular flow through the block. Like there's a hyperblock of stuff, and we're surfing through it, making choices or doing the particular stuff. If you just think that it's all random, like randomly we do this selection of events, and we make this selection of decisions, and then we have our own like evolving block. So in my system, we have an evolving block, which is dominated by T, regular old time, as it pushes through the block, which is a hyperblock. And I also have something called cyclic time. So cyclic time, what is cyclic time? It's the idea that time, under some extraordinary circumstances, can circle back on itself. Now, this sounds weird, and it is weird, but you see situations like as in time crystals where things behave this way. And Kurt Gödel actually argued to Einstein that general relativity has to admit this possibility. So quantum systems exhibit both transcausal and cyclic time properties. And we've had a really hard time dealing with this because we're not used to thinking about time that way. And so if you've seen the outcome of the double slit experiment, and if you've seen the outcome of the delayed choice experiment, once you get to the delayed choice, you realize that a decision made at the end of some journey can impact what's available to do at the beginning of the journey. And that's completely counter to our intuition. So we come up with all these ways of thinking about, like, well, maybe the whole system somehow knows all of this, but how can it know something that's going to happen later? But maybe it does, because maybe the times are interfering with each other. Like, I'm sitting here, but I'm actually in an interference pattern with myself 5 minutes ago, with myself 10 minutes from now, and that's all interfering transcausally to create me here. Like, I'm not just me now, I'm me across the whole thing. And I change the whole thing every time I move a certain way or I make a certain choice, but I'm still me across the whole thing. I'm not just me sitting here. I'm really a wave function extending in time and in space. And so are you. We all are. And that's what quantum theory really tells you, is that we're not localized objects. We are just the peak of a Gaussian curve. And for us, that's a very heavy peak, and there's not much chance that I'm going to appear on Mount Everest or in Tibet or in India or whatever. That's not likely. But there's a very, very vanishingly small chance that I could do that. And there's a part of me that's everywhere, because there's a part of my system that does not decohere, that doesn't interfere. And that part, because if I wouldn't even be here without that part exists across all time and space, and we're all like that. And so if you think about that, like, because your brain, it's an EM field, and EM fields are all ultimately quantum fields. So you have some element of a coherent quantum field in here, in your brain, in your heart, really bigger than that. And that isn't limited by time and space. Now, you can't send signals with it. You can't use it to be like, Mom, get me a rock star at the grocery store today. You can't do that. But there may be a way to share states with others, with other systems, other times, other places, because maybe everything is entangled at some level. Now, I don't have a lot of time to get all romantic and talk about entanglement, but I think entanglement's cool. And everything at some level is entangled because we were all one at the time of the Big Bang. And so so we're getting into time is weird in quantum mechanics. How do we talk about time being weird in quantum mechanics? Well, we create a world system where we can accommodate that view. We can accommodate what's actually happening. So I use complexified hyperblock time on CP4. But also in the whole system, but CP4 is my parameters. It's composed of infinite quantum world lines. They initially static. Yeah, you kind of can view it as like this static block, but there is a direction of flow through that static block, which we'll talk about in a bit. Torsion within the field drives temporal evolution. So like there's a twist here. If you look at that, you see how those fibers in the hop kind of bend and twirl. Like there's a certain bias towards a certain way of moving in that thing. And that's what drives time forward mostly. And so you can also derive torsion via Einstein-Cartan theory, which is extendable to 9D pretty easily. You can capture the bundle's topology, and that topology there, as you look at it, that's just a 3D shadow, but it's close still, even in 9D. You can unify the fields on that thing. Okay. So topological derivation from S9 and CP4. So S9 is just the master egg that I've been looking at, like this eggs within eggs within eggs. I'm just looking at this part of the fiber bundle that holds everything I want. S7 is so close, I could work in S7 just as easily, but I prefer working with CP4 because it handles 3D space without resorting to strange trackers. They're like 2D trackers to track 3D, and it's like, I don't want to deal with that. So the total space is S9. It embeds all fields. All of physics is on this thing. I've pulled out the regular Lagrangian and canonical equations. They roll out of here. You can get basically whatever you want, is what I've discovered, which is a little bit scary. It's like in Zelda when you have the Triforce. What do I wish for? What do I do? So you get the gauge groups from topology. These are just kind of like ways of thinking about the bundle from different angles, which is how you get the gauge groups. So from the S1 fiber, you get the photon and the Z boson, and you get hypercharge, which is necessary for deriving E&M. You also get the W bosons from SU2, and you get the gluons from SU3. And these things are all part of the topology, the shape of this bundle. I'm not like gluing them on or embedding them somehow or trying to force them into the bundle. They're already there. And so I've been amazed how many theories of everything try to glue things together somewhat like, well, here's this thing, and we'll try to connect it here, and we'll try to, like, they're building something, but the universe just exists as it is. I just want to find a picture of it. I want to see what it really looks like. And that's how I felt when I found this thing. It's like, there's the universe. I am looking at the universe. I get a little bit excited. So the hyperblock bundle is a quantum framework. It serves as a topological alternative to Hilbert space. You can do quantum calculations just on this bundle as it stands right now. You don't have to really do anything to it. You don't have to glue Hilbert space to it. You can pull a pseudo Hilbert space out of it. Now, I think that in the n-dimensional version, the infinite dimensional version, I'll be able to find regular old Hilbert space, but this analog works just perfectly fine. And it also has some features that regular quantum doesn't have, like being able to track coherence in a different way through time as well as space. And yeah, I'm excited about it. So you can recover the SM physics, the standard model, that means the particles and spectra. You can support gauge invariance topology. I don't know, though that's not really, I don't like the way I said that, but what I mean is that the gauge field invariance is topologically generated. So it unifies quantum and gravitational phenomena into one thing. So that's quantum gravity right there. And it works. We're good. Okay, let's see what's going on in the chat. Okay, yeah. Oh yeah, I love, Gary asked me a question. Yes, I love Julian Barbour. He was extremely influential on my thinking about this and about my thinking about different kinds of time. I also read Lee Smolin's stuff. He worked with Barbour, but he believes time is just the evolving chain, and we're just one. Like for him, time would just be the points on S0 of the S1 fiber. And so, but what's funny is, like, I think that view is true, but I think it's complementary, not in conflict with Julian's there's no time or time is one or whatever view. These theories are just different ways of looking at the same animal, like the blind men and the elephant. Yeah, the Wheeler-DeWitt. I've actually overcome the Wheeler-DeWitt problem with this theory. I haven't put that in my main document yet because my main document is becoming like this massive Bible now. And it's like, I didn't want to write a Bible. I just wanted to write this thing, but it is this big. And so it keeps growing, but yeah. Okay. So I noticed when I was working in my theory that I could work in a variety of dimensions. So, and when you get down to, like, I started in S3, so S1 to S3 to CP1, that's where I started. And I noticed that I could glue on things that I wanted to work with, but I didn't want to have to glue on. Thank you, Gary. I'll put your email in the chat or figure out a way to get a hold of me, and I will send that to you. I'm going to update. I'm also going to keep updating this. It's on Phil Papers. My Phil Papers has my theory. Yeah.
And Jennifer, I can bring for Q&A, I can bring Gary in and you guys can chat too.
Oh, that sounds great. Yeah, that's great. Yeah, I just got excited when I saw mention. Okay.
Oh yeah, no worries. Yeah, when you're done with your presentation, just let me know. All
right, well, that's wonderful. Okay, so yeah, and I can keep going for a while here, so I might go slightly over, but so S1, S9, CP4, that's where I'm working now because I can deal with all the kinds of time I want to look at. I have topological time as an arrow driver. I have regular time, which is just the output of topological time. I have complex time, which is just time on the whole system going all at once. But I also have cyclic time, which is just another way of looking at the block from a cyclical perspective. So that's a lot of times. And so I wanted to have a system that would allow me the dimensional space to deal with all those kinds of time and so that 9D version gave me a parameter space that could account for that plus 3D without having to resort to a 2D tracker. And then that was like just confusing and I didn't want to have to deal with it. So that's S7. I don't know if I have do I have S7 on here? I think I do, but that there's a typo. This should be 7D here, and this should be S7 there. I don't know what happened to an earlier version was right, but when you tell an AI to modify your tables, you're always in trouble. They might do something strange. But what I really loved working in was S3 cross. Why is that S5? This thing is driving me nuts. Okay, well, we're going to have to use a different dimensional table because I need to make some changes to it. But anyway, but I was working with a 5D S3 cross C tau, which is just complex time as a block, as a product space with S3, which is the surface, the 4-dimensional shadow, excluding 0 on our world. And so 0 is excluded, but everything else is isomorphic to our world, and you can kind of on the surface of it, and you can follow the surface of this 4D object here. So I was looking at all these different views of the same big bundle, the same big infinite bundle. And so I've concluded that I really wanted to work with S7 or S9, and I don't know why those aren't rendering right. I shouldn't have asked. I should have just edited it with Paintbrush and not relied on Grok. Okay. So here I'm just talking TT-UFT, that's my topological transcausal unified field theory, can be viewed as shells of the infinite diffeological, that just, it's like differential, but topological differential, Hopf vibration. So that thing is S1 to infinity of CP to infinity. And meaning complex projective space, my parameter space, but it's also just a space of complex rotations. So our world, which is a 4D object submerged in this 9-dimensional space, is this S1 to S9 to complex projective space to the 4th power. And here I just want to talk about some ways of thinking about it. I've always seen world lines as this little thing that kids play with. Like when you push the block, you're at the dentist's office and you're 3 years old and you're bored and you just start pushing this block along this wire. That's particles which are just like these dense condensations in the field, and they just or it kind of counter condensations, because it's actually where the field interferes with itself to cancel, and then what's left is the thing. So it rolls around through these world lines, makes choices, takes twists and turns, and it kind of looks like part of the Hopf vibration. So I included it there. It's just it's a way of thinking about it. Another way of thinking about it is like that slinky in Donnie Darko, if you like the movie Donnie Darko, anybody. But anyway, that slinky and how it connects across different parts of space, like a wormhole, but also like a slinky. That's kind of the way, because you can unfold it, it's compact. Then you look at it and it's like, oh, there's other stuff in here. That's kind of how the Hopf vibration. And it's kind of like Russian dolls, and I included this picture of the complex plane because I liked the fact that there's a spiral in there, and I'm trying to explore that factor right now. So this is a good view of the infinite shells. I should have just used this as my dimensional map. So here's S1 to S9 to CP4. That's what I work in, the 5th shell mostly. Then there's the 4th shell. I worked there a long time, and it's a good shell. I worked in the 3rd shell a long time too. So when you might read, if you read my blurb, I'm talking about some 6-dimensional thing, and I was talking about using CP. I was talking about using one of the CPs that has 6 parameter spaces in it, a 6 parameter. I'm trying to think of the way, but the 6 parameter spaces. That's fine. And so I was using that for a long time, but I moved up to get more stuff into it. And it's the same thing. It's just a different shell of the same thing. So it's like there are these domes, and they're limited, finite-like, but maybe expand. They can expand as far as you need them to, but they're finite-like in that they can be covered by finite coverings, is how they talk about it in topology. But it's like a series of these domes encased in other domes. So there's this nesting tower, and each finite dimensional, like finite is kind of the wrong word, but sort of finite dimensional bundle, like each compact bundle, we could call it, is a realization of the universal bundle over that level of projection. And so it's like everything is a stereographic projection from infinity at some level. So we're all just like little shadows of infinity. So higher shells like CP4, CP to the 4th, is a full UFT with all quantum gauge and gravitational degrees of freedom. Lower shells like CP1 are like an early universe with reduced symmetries or internal spin-like bundles, so you can get the spinors off of that thing, which makes me think maybe spinors happen sooner than other things, but I haven't really gotten into the cosmology that deep yet. So the tower describes how richer spacetimes emerge from lower dimensional cores, but something important to remember is that it's not like you get here and like, oh, I'm here and there's nothing above me influencing me. Torsions and spins and various kinds of behaviors from above the higher dimensions also impact, they vibrate with and interact with lower levels. So like I said, like we're not just 4D, we're 9D, but the part of us that we see as physical is 4D, but it's just a 4D emergent thing on the 9D. So I've got electromagnetism and hypercharge. I've got the weak nuclear force. I've got the strong nuclear force. This is my gravity action from the topology of the field. It's good. I'm going to go over to an email from Jack because Jack Sarfati, he's my mentor in physics world. He said that I need to focus on this thing, and I didn't have time to put it into this presentation beforehand because I just came up with a way to slide it right before. So I'm going to share screen to, where's my Zoom? There we go. So the U1 twist, when you get U1 from the S1 fiber, yields a connection, one form A with curvature F equals dA, encoding local phase winding. Okay, this is a Chern class of 1 for people who know what I'm talking about. And then the torsion, and this thing imparts torsion. And then they call this the torsion 2 form I discovered, and so I'll call it that. Where E to the A is the frame and W to AB is the spin connection. So this action that results here is constructed to couple with local geometry, the topological twist, and the internal structure or helicity via this thing. And that combination ensures the torsion is sourced from a topological twist. So this is that twist thing. It's not arbitrary. It's part of the topological structure. So then you can start working towards getting the Einstein field equations and equations for torsion. So the curvature formulation of the field equation, you start here, and then you just keep deriving and deriving and deriving. And I'm not going to just bore you guys with this, but if you know what I'm talking about, you'll be able to follow along. So to relate the space-time curvature, you introduce this thing. You define an effective action that includes an Einstein-Hilbert-like term, that thing. Varying this with respect to e to the A gives the gravitational field equation. And this thing doesn't require a metric, but here's Einstein. If you look at it closely, 8 pi is in there. And then the variation with respect to the spin connection. So that's a compatibility condition between the frame, curvature, and internal spin structure. I'm not going to try to say all these weird symbols. Variation with regard to the frame. So that's kind of, did I include that already? I should have included it before the spin connection, but oh well. And then curvature formulation, and then you get this. And in the classical limit, in the classical limit, it does reduce to the regular Einstein field equation, which made me really happy. And that's what has been happening to me when I've used this thing. All of physics is just falling out of it like it's a hat with cards in it, and they're just all over the place. And it just is like, yes, 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 good feelings, good feelings. Okay, so all physics is derived from the topology. I should probably say not all physics, but like all of it is like either in the topology or vibrating on the topology like a standing wave on top of a generator. Gravity is in 9D, but it reduces to GR in 4D. So you can look at it as if you look at it as like a very minute chop of itself, yeah, it works like Einstein said it did. But it's sort of like saying that Newton really understood general relativity because he had a slice of it. So Einstein was the same way. He just had a slice of reality. I'm sure I'm just looking at a slice too, but it's a big slice, man. It's such a big slice. I'm so happy. So then you get the 5D complex time, T minus I tau, 4D Euclidean universe and imaginary time block. So that's my S cross C tau. That's my, so it should be S3 because it's like, it should not be S5. It should be S3. So it's S3 because there's 3 dimensions there. And then there's a product space with C tau. And then that C tau has 2 more dimensions. So it really should be 3. I'm going to go through and edit these things. 4D S3 cross R, that's just regular 3D space plus time, like glued to time. And you can use that to do general relativity too. I prefer Euclidean relativity where time is seen as like a physical dimension because I don't like treating time as just a parameter. I think it's a topological part of the fabric, which everyone says time, it's the space-time fabric. But then if you look at GR, time is treated more like a parameter sort of stuck on there. It's not treated as an Euclidean dimension, and you have to treat it as a Euclidean dimension to make a lot of progress, in my opinion. Lorentzian space is just sort of a limit on that, and it limits our view. So where are the fields? The topological field in S9 emerges in 4D is gravity, but it's still gravity up there. It's just a different level of it. The gauge bosons are encoded in complex projective space to the fourth via U1, SU2, and SU3. So I derived those things. You can check my work. You can read my paper. This is my paper, by the way. Well, no, I'm not going to look at the paper until I'm done. What time is it? It's 4:41. Okay, so Jack for the Q&A. Yeah, he will dominate the conversation. Oh my gosh, yeah, that would be great. I'd love to have. When is the Q&A? It was supposed to begin. Jack, tough. Yes, Jack is a tough mentor, but he's actually a really. He's very caring under that combative, difficult. What's the word? Cantankerous? He's not really cantankerous. He's a yeah.
Yeah. Well, no, Jack is absolutely wonderful, and he has contributed so much to the community and to the conference.
Yes.
So, but yeah, he has a lot to say, and he will steamroll you. So
yeah, I owe so much to him because Nick Herbert added me to the big email list that Jack is on, and I was only like 17 when I got on it. I was like, yay, this is so fun. But yeah, I learned so much. And also it's kind of like listening to Coast AM or George Norrie, because such strange things happen on that email.
Yeah, and I mean, we've had Jack on in the past, and I definitely want to have him back on. Typically, what I try and do is give him like enough space, because he always has so much to say and so much.
He does. So. He has so much. So this is this thing called wonder, which is just basically torsion impacting particles but I don't really call them particle fields, whatever you want, as they turn, and there's a shear aspect to it too. I have to get out of this building, but this room, and if I only have it reserved until 5. So, but I can stay on after that. So that's helical torque. This is the expression for it. Tau is this. So you define, and tau also is complex time, imaginary part at some point too. So don't get confused by too many taus. Because I did once, I'm like, why is that there? Okay. So you define. So now you have to now that you have that. Let's think about it, because the turning isn't just in space, it's also in the time block, because everything's moving through that block time, everything's cycling through that time. So you have to account for that. And then, so there's the tau 1 is the block, tau 2 is just another view of the block, which is the cyclical view of the block. And then times this factor, and that's tau wonder, which is my twist torque operator. So through block time, through cyclic time, like I said before, you twist through 2 temporal modes. So block time is the real part of K, and then cyclic time, imaginary part of K. Oh yeah, I see why it's whatever. It's a strange way of saying it, but they're both kind of imaginary times. Okay, so the real part of this complex time controls the magnitude of the twist. For cyclic time, the imaginary part controls fiber phase rotation. No need to get into it. So the arrow of time in our world, it really has a bias in a certain direction. It's not perfectly circular, but the arrow of time drives time forward or down, through the up to the down. And then that's from the higher dimensions to the lower dimensions. And that's how we get, so that when you're dealing with gravity, when you're engaging with gravity, you're going to feel that, and everything is to enough extent so that we're kind of dragged forward through time. We're not just going forward, we're being dragged. It's not our fault. So here's the topological field equation. I don't have time to derive this, but you can get it. So you start with a 90, you move down from there, you take a slice out of it, a chunk. This is a 5D slice, but it's kind of a 4D slice because it's 4 real and 1 imaginary, and that's this. So you see the 8 pi g, that's just like Einstein, but then I have more stuff in here than just t. Okay, then part 2, tau, is it capital tau? Comparison to other UFT contenders. So I have a 4D space-time. No, I don't. That's Penrose. Okay, so Penrose has a 4D space-time. I have a 9D time-space. He uses conformal complex analytic geometry. See, he's doing something similar. He's gluing CP3, the third dimensional complex projective space to S4, which is the 4 sphere. So that's a surface of a 5D object. I think it's not the bundle I like because it doesn't do what I want it to do. It's not a UFT, but you get a lot of interesting things still when you do this. And his thinking, Penrose inspired me a lot. Almost like Julian Barbour and Penrose, my major like thought generator people. And here's Lee CZ8, and I'm just like, I mean, this guy had the gall to call it 248 dimension theory extraordinarily simple or whatever he called it. I was just like, okay. But no, it's a very cool theory. And I was inspired by the fact that he just went and did that and was like, look, I did it. I really thought that was cool. But I don't think it's it, because I think it has limitations very similar to string theory and that there's not much testable. You have to adjust parameters to get around the fact that some of it doesn't match reality and whatnot. But it's a cool thing. It's a beautiful thing. You should check it out. Weinstein's doing something very similar to me. He loves the hot vibration. Yay. But he's using it. From what I can tell, he's gluing different parts of the standard model together using vibrations. And I just think that and he also has a metric. So his object isn't inherently gravitational. He's just taking the non-gravitational thing and plunking it on gravity and calling it unified. Now, I was tempted to do that early on. I did that for a while. And I was like, this isn't really a UFT. And so I kept trying to find an object that would contain gravity. So versus loop quantum gravity. Loop quantum gravity is kind of like a limited thing that can do some things, but not everything that, like, it can't predict new particles. It didn't derive the standard model. It's limited in scope. It's cool, but it's not a UFT. It tried, but no cigar. Then string theory. Basically, string theory is great, but it has so many parameters and it's in the Planck level and we'll never get there and we'll never be able to test it. So even though it's beautiful and even though it's cool and even though maybe it would work, I just don't care. I was just like, I can't touch it. I can't move with it. I can't test it. I can't build something with it. So I'm just like, so done. We're so done. Sorry, string theory. We're so done. I want to sing the Katy Perry song. You're so. I won't go there. So exotic aerospace applications. I haven't actually read this book, but I liked the picture because it's kind of what I'm envisioning. And then here's a wormhole simulation. If you go to the wormhole Wikipedia page, there's a citation for this thing, and I meant to plug that in, but I threw it in at the last second. Anyway, you know about this. This is just for people who don't remember what I said before. And you can reduce to lower dimensions, which is cool because that means that upper dimensions. So what if we want to put a cat through a wormhole? What if we want to put a cat through a wormhole? So you put it in a sphere, a containment sphere, like we've got this graphene airfield sphere, which is part of a bigger box. Your goal is to transport it through 9D spacetime. Why? Why do you say? Well, because my wormholes are really good wormholes. And you can open them up for like a fraction of what you'd think. Like, I think that you could probably do it with a AA battery, maybe a AAA. So space, but the energy isn't the limiting factor. It's just putting together things in the right configuration. So we think about space plus time, real and imaginary time on our 3D view, glued to the time. Like, I just glue it there because it works. So the tools are plasma, lasers, the gauge fields, which are just the fields that we have in space, plus torsion. And torsion is just this property of matter in space in my theory. So the space-time you're tearing through is this metric. So I'm using metric gravity because wormholes are described there. So I just plunk my theory onto the gravitational sheet because that's just the easiest way to work with it. I could do it by rederiving wormholes in my theory, but I just didn't have time. So the throat radius is this. Because it's small, it's only like 0.3 meters. It's not huge. It's not huge by any means. And the temporal phase, you have a temporal phase like of the and a spatial curve. So like these are aspects of time that you're working with when you deal with this. So this is the action in the fields. You have gravitational curvature. You have torsion. You have that A connection factor, which is the twist of our bundle. And these things all combine to being able to, you could derive, what I'm basically saying here is that this is what's doing the work on the wormhole, and you could derive what you want off of it, but I just didn't. I used Einstein because it works. It worked for that. It worked for that purpose. Okay, then, and that means that I have to go back and do these equations again with the field equations rather than making order of magnitude guesstimates based on outcomes of easier solutions. But anyway, so you have this thing, you put the cat in it, you inject argon into the outer chamber around it. The cat breathes normal air, gas is neutral, trace amount, safe for cat, Then you pulse a laser. It's a 10 to the 6 megawatt laser. No, 1 megawatt laser through to the chamber windows, and the low energy is due to, so like it takes only 10 to the 3 joules. That's like under a AAA battery, I think, just under. The low energy is due to the it's like a lot less. So the low energy is due to the S1 twist and torsion effects, which amplify space-time distortions efficiently to form the wormhole throat. So it targets the outer chamber. You ionize the plasma. The plasma fills up around the sphere outside of the cat's little doohickey. It's glowing outside the cat's shield, and graphene absorbs the energy so the cat doesn't get it. The plasma twists S to the 9 into a topological defect. This is the temporal warp. We warp with this factor, and then the torsion field is this thing, which will help us. And spinor coherence keeps the wormhole open for 10 to the negative 3 seconds. Now that's very, like, that's just, you can keep it open beyond that, but it'll keep it open right there for that long. Good to know. So the cat will cross in proper time, and external observers see it kind of jump into this circular void. It's not really a void. It's like looks like a crystal ball kind of. Okay, and then like you can do all these things. You open the throat. You tune on this, the Ka, which is spatial. You tune on Ky, which is temporal. These are aspects of wonder that you can tune the wormhole with. Yeah, you can select where you're going to go, into the past, or into the future, or into your backyard, or into LA, or if you want to go to New York, or if you want to go to Paris, you can tune it based on your location relative to that location, and pick where you're going to go. So you send the cat through, it works. No exotic matter, no problem. Classical wormholes need negative energy and exotic matter. This uses topology, torsion, and gauge fields. It's like, in my universe, the space-time is kind of already like wormholes, because it's like an origami structure that's kind of folded in on itself. So it's all there. The material to go through is right there. You just have to poke through it using the right kind of coherent stuff. So you don't force a wormhole to open. You just kind of nudge it like, hey, and find that level of the system you're in. So you need a little bit of juice, but it's like so little juice that juice is not the limiting problem. It's just like, how do I get coherent plasma? What do I do? So how to tune the exit. So you have proper time, the gauge field, the S1 phase, the hop invariant. You adjust these things using rotary photon injectors and coil precision. And that's complicated, but like you can build a device that will tune this. So the cat just doesn't notice anything. Yeah, you could send a person. It wouldn't be that hard. And then I also have an anti-gravity lift. I'm not going to go through the math for this either. But you can see, like, it doesn't take much energy at all to do any of this stuff. Energy is not a problem. And then now we're going to get to Sarfati's tic-tac propulsion concept. So I wanted to check out whether my theory validates him. And yes, it does. It does. It does. In fact, I think my theory might make some aspects of his system easier to look at. Might just overcomplicate it. He has so many new variables to look at. So Sarfati says that metamaterials with dissipative phase shifts allow redshift ahead and expansion blue shift behind the craft, folding space. Well, see, my space-time is already folded. You just have to find the folds. So he has Einstein's field equation here worked out, where cosine is greater than 0 and less than 0 switches from attractive gravity redshift to repulsive anti-gravity blue shift. Yeah, I mean, that would work. It works. And you got to remember, my field equations aren't very different from Einstein's. They are, but they're not. And then Jack says that the tic-tac is controlled by a conscious AI. In my system, that AI would be utilizing the twist factors on time and space that I've talked about earlier. A controlled propulsion you would construct the crafts hull with metamaterials. You'd pump electromagnetic energy into the metamaterial. But see, in my system, the wonder torque would modulate the local space-time geometry, creating a warp bubble. And DAC has something similar, but what's cool is mine is much more easily controllable, so the AI won't have to juggle as much stuff. It'll be able to not so much juggle as much stuff. They'll be juggling more stuff with me, sadly. But it will be able to access things without having to figure out how to access them. If it was relying on general relativity, it would take longer. So my transcausal dynamics verifies Jack's low power approach because my system is naturally low power. But my system uses a quantum control system to adjust wonder parameters, tuning the warp field, the shape and direction. So I might be closer to being able to program the AI. Maybe. We'll see. Now there's an experiment you can do to test my theory. It's probably cheap. There are a few more expensive versions of this, but we want to validate this. So, hey, somebody help me validate it so we can build wormholes and do cool things. So the hypothesis is that inertial game states, that's what I call quantum states that are in inertial systems, exhibit standard torque, like just the normal angular momentum of a quantum system. I call it standard torque. That's a little bit weird, but yeah. Accelerated place states, those are systems that are under gravity and they're accelerating. And so they're dealing with gravity in a more direct way. They reveal wonder torque, which has this which arrives from this phase, and then SU3 contributions and transcausal effects. So those things all are something that are revealed by engagement with wonder torque. So the goal is direct, distinct polarization and interference signatures to test S9's topological structure. So get a polarization sensitive interferometer, and then you need to accelerate it, and then see what happens. You'll see without wonder, you'll have a certain set of measurements. With wonder, you'll have, and I had a more straightforward graph of this at one point, but so you'll get different measurements, and I can predict exact differences. Okay, we've actually got to the end of the thing, and it's 5. That's impressive. So this work was made possible by funding from my students at the Adventure School of Kansas. I would not be able to do any of this without them. And I'd like to thank the participants of my think tank, the Jenny's Think Tank and Holistic Comedy Bar from 2010 to 2015. I'd like to thank the participants in Science by Number with Jess and Jen, that should be on here. I'd like to thank John Ralston, Nicholas Geis, George Musk, all these people. And Deepak Chopra, Nick Herbert, and Jack Sarfati. I really want to thank Jack Sarfati because I would have given up probably without his encouragement. And I want to thank my brother for asking great questions, my dad for believing in me, my mom who gave me this book by Fred Allen Wolf and that other one by Tobin that was co-authored by Sarfati when I was 7 because I was asking all these questions. And for Lou, who he has a good intuitive grasp, so I say here he already knew. So yeah, and I dedicate my work to the memory of my mom who died of cancer 2 years ago. Her music, she's a composer, it rings out across the manifold forever, and for me that caused everything. So Newton said he stood on the shoulders of giants, but I think we're all greater standing together. In seraphim vestiges amblulo. I walk in the footsteps of angels. All of you are angels. We are all in this together. We can make progress working together. Okay, so that's the end of presentation. I'm going to ask any questions, but I also need to get out of this. And then I have like how to propagate. Yeah, I have how to propagate renormalization here, but I don't think we're going to get that far. Hi, Tim.
Well, yeah. Hey, Jennifer, thank you so much. I want to leave the cats up for a minute. Those are I love the cats. Okay,
my friend now sent me this. He's like, you should use this.
I'm going to bring everybody back in. So before anything else, in true APEC tradition, I think that's everybody that we have here. Let's give Jennifer Lorraine Nielsen a giant applause. A giant applause.
Thank you. I was so humbled. Thank you.
Oh yeah. Well, and so now that you've done APEC once, you've got to come again and again and again.
Yes. Yes.
Mark,
we will do this.
Mark, you're dressed up.
It's Passover.
Oh, that is true. Okay. It is. It is Passover.
Happy Passover, Mark.
Happy Passover. Happy Lent.
And
Respectful Passover.
so I wanted to ask you, Jenny, about you said that spin might be connected to time. What do you think about diamagnetism?
I think diamagnetism is very cool, and that because there is a connection in my system between gravity and E&M, because it's just one big thing, you might be able to find some interactions there. I haven't specifically worked with diamagnetism much, but I remember thinking, something is going on here when I did.
So what you're looking at here is a coil made out of oriented bismuth.
Ooh.
We cast bismuth, and as it was cooling, we ran 50 amps of DC current through it.
Ooh.
So, and then we're going to pulse it and see what happens with time.
There's some overlap with what I talked about there, pulsing the laser. Yeah.
These are rubidium clocks. I have a couple of them. Some of them are going to stay on top, and some are going to be outside of the field.
Oh, this is awesome.
Yeah, so we actually have a way of testing this. This was dreamed up by Jeremiah, and I think Lulu was involved in some of this conversation as well. That's an interesting.
That is very interesting. That is very interesting. And the coil might actually. What made you decide to coil it quite like that?
It was. I'm not really sure why. I'm not really sure why we decided to do it this way.
I got to get out of this room. I'll be right back. I just got to move a little bit and get out of here because they're closing my little library that I've decided to do this in because it's so quiet. All right, hold on. I'll be right back. Nobody worry. I'll give me like 3 minutes.
So it's held down with hot glue. It's extremely fragile. It can't hold its own weight.
Yeah, I mean, to me, it makes sense because you're trying to do kind of a big coil, and it looks like you've got to kind of pour it, right? So you're going to have to do something that's kind of that dimension.
You could do other dimensions. It would just be a lot harder to remove it from the mold, and you might just have to leave it in the mold. This was a coil that we could actually get out of the mold. I think it's around 7 turns, and as far as I know, it's the only attempt at making bismuth wire or bismuth coil that's ever been done. So it doesn't look pretty. If we did it again, it would probably come out a little bit nicer.
I'm still here. I'm just walking.
Okay. Mark, I dropped your email in there for Jennifer, and then the other part, maybe I shouldn't reveal this while we're live casting. Mark and I are negotiating about flight schedules, and we're going to loop Jared and Tony into this for the SU conference.
Great.
We have an invitation from Tony Robertson to visit. I know I'm kind of going off topic, but we have an invitation from Tony Robertson to visit his lab. And Tony he is like a pivotal character going back years. So we might be able to visit Friday, and then I'm thinking about just staying an extra day and spending the day with him on Monday. Oh, and Gary has to take off. Okay.
Oh,
Gary,
really
thank you again. And I look forward to seeing you next month and the month after that in Huntsville. So
yeah, Gary, an alternative. Yeah, I'll just.
We'll be in touch.
Okay.
All right. See you, Gary.
Okay. Awesome. Okay. Well, Jenny, thank you again.
Oh, well, thank you guys. I really appreciate it. This has been a great opportunity to talk to people who are creative and who are interested in some of the same stuff I am, because really the reason I was so interested in unified field theory is I really wanted to understand time. And I think that has something to do with the whole propulsion thing. Now, I have equations for anti-gravity. Hey!
Rubidium, a miniature rubidium clock. Yeah. I mean, it all has to come down to experiments at some point. So.
Yeah, it does. And so I want to go about refining my experiments with more details so that maybe we could actually realize something. Maybe if I talk to an engineer, someone more practical than me.
That's what we are. We're the engineers.
Yes, I know.
And Jennifer, actually, if it's okay, I want to do a really quick screen share, and I'm going to unveil this. I had kind of a surprise yesterday. And so here, let me share the screen really quick. So a fellow named Chad Wanless, who lives in, I think he's in Saskatchewan, Canada, he contacted me out of the blue. He's a MUFON experiencer, but he's been working with a PhD electrical engineer. And he kind of independently came up with this idea of Alcubierre drive deformations. And he has been calculating these out. And so we did a podcast yesterday, and I had no idea what to expect when I went into it. But
this looks really cool.
Yeah, the reason I wanted to show this to you was when I looked at what he was doing, he's using Aguadilla as well as a few other sightings. For instance, let me see. He's got lots and lots of evidence, and he's making some new predictions, which is really interesting. I'm looking for.
That is so.
Oh, come on. Okay, I'm not going to be able to find it, but
there it is. There's real stuff. Like that's nothing hokey pokey.
Yeah. So what he was showing was, in the case of these old photos, these are two photos by different photographers that are taken quite some time apart. He was able to map out the irregularities in the craft to the Alcubierre deformations, and he's doing a lot of computer-aided stuff. I wanted to see what your thoughts might be on this, because when I saw this, I was like, to me, this reinforces what Jack has been saying.
No, that's my initial feeling too. Like that's very interesting that the photos map, and I could put on my skeptic hat and say, well, these things smear when they're developing or whatever. But no, I think we need to take it seriously.
Yeah, I will paste a link in for this. He had a lot from different sightings, and he could probably do even more.
Oh, wow.
And then the other thing, he made a couple of new predictions. The most interesting one was he was saying if you are compressing time-space rapidly, you may get cloud formations. And he cited the new Skywatcher video as an example of that. This video this is from their thing earlier this week, right? So this is like brand new.
Yeah.
So this could be JPEG compression, right? That's entirely possible. But he was saying if you get vapor clouds, especially forming in front of the craft, that could be a side effect of Alcubierre drives.
No, that makes sense.
Here's another example. He had 2 or 3 of these. Again, he's saying the vapor cloud is in front of the craft. He's saying it's not a reflection, it's a cloud, right?
Interesting.
And then he did make one further prediction. I'll stop sharing now. He made one further prediction that I did not get a photo of. And that is, he was saying, because the Alcubierre metric you're changing the metric of space-time, you should be able to calibrate radar to differentiate between a UFO and an aircraft. And so not only would you get a blip on radar, you would get a blip, and hopefully you'd be able to tell if it's one of ours or not. So
that is so cool.
I just thought I'd put that out there. I'm just a lowly conference promoter. I'm not at your level of physics.
So Jennifer, I have one not serious question and one much more serious question. So if wormholes are such a low energy effect, is that where my keys go when I can't find them?
Oh my gosh, maybe. I think it would be more likely just like bouncing into another reality, because there's a small chance you would every now and then. That's why I just like, it's on Jupiter right now. But actually, since it's so low energy, one of the things I was talking to someone about, I was like, well, why aren't they everywhere? If it only takes this much energy. But the quantum coherence required and the plasma and the exact configuration you need and various things are so odd that they won't happen that often. But I think in early universe conditions,
so low energy but not low entropy.
Not low. Not low. Your information.
So one question, actually kind of related. So how do you plan to determine the difference between? So there's a bunch of other models, kind of going from there's like a chaotic deterministic approach to quantum mechanics.
Yeah.
How would you differentiate between high dimensional projection and a
more chaotic
nonlinear behavior?
Well, they're probably just complementary things because, right, like the quantum system itself, beyond behaving as an attractor naturally, the quantum system doesn't have a lot of entropy or or thermodynamics going on within its coherent wave function. Now, when you get into mixed states, yeah, you start seeing those kinds of thermodynamic nonlinear interactions going on. But in the quantum system itself, it's just this thing sitting out in this weird space that we don't understand called Hilbert space. So, like, I think that it's about so when I'm talking about the quantum system, I'm talking about the quantum system. Now, I can bring in coherence. I do. I have my own quantum system right now that actually uses coherence, and I get around certain problems with like the polydensity matrices and things like that. But I don't know why I call them poly, but the reduced density matrices. But so I'm doing quantum that has coherence accounted for in the way the system is written, matrices. But anyway, sorry, digression. But so even though I cover that, I'm most interested in the system when it's coherent. So when it's coherent, you won't have nearly as much of that nonlinear bouncing, interacting chaos going on. You just have the system. Does that make sense?
Well, so are you familiar with nonlinear controls problems at all? The Russians did a lot of literature on this.
Yeah, a bit.
So, so you can get a nonlinear chaotic system to behave. You can get it to become coherent.
Oh, yeah. No, that's true, too. Yes. Because there's this ordering factor that comes out of the more chaotic. Well, basically, the more you shake things up, the more things come together in intriguing ways. Yes.
Yeah, kind of like the Prigogine effect.
Okay, that's amplifying the quantum. That's amplifying coherent aspects of the system.
But it's also you could think of it as a nonlinear controls problem.
Yeah.
That stabilizes some coherent state.
Yes, it does. It does it by kicking it up because it's already there. There's always some part of the system that's coherent already. So you just have to figure out a way to connect with it and amp it up. And that's what those nonlinear systems are doing, for lack of a better way of putting it right now in 3 seconds.
Well, I'm very excited to talk with you more about these things.
Thank you. I'm excited to talk to you guys.
Yeah, excellent work. Excellent work.
Well, let's come back to, if it's okay, let's come back to Gary's questions. So let me see. Gary was asking if, Jenny, have you studied the work of Jose Vargas, such as in teleparallel Finslerian fiber bundles?
You know, I the name rings a bell, but I do not believe I've gotten into it at all. So, okay. I mean, I've heard about it, but I haven't known. He also, I'm curious now. I'm going to look at it, and I'll come back and tell you what I think.
Yeah, he was also asking, let me see, about Barber's emergent time. Yeah, Wheeler DeWitt.
Yeah. Well, what is about emergent time? What's about emergent time?
Let me see. He's just asking whether you've studied Barber's emergent time and its relationship with the solutions to Wheeler DeWitt equation, the wave function.
Yes, I have. Yeah, he was very instrumental, and so that he motivated some of this way of thinking, but he also kind of just resonated with thoughts I had been having. So I read Julian Barbour in like 2007, I think. Yeah, it impacted me a lot. But the Wheeler DeWitt thing is a problem. Like when you get to quantum field theory and you look at it a certain way, you get to time as a static clock, and there's no way to have dynamics anymore. And it's like, what do I do now? And so like what I've done is I've recovered dynamics in the block. So that's how I resolve the Wheeler DeWitt problem, is that, well, let's bring in other ways of thinking about time. And then you can recover a dynamics in the complex time view of things if you bring in the topology of this particular system. So
now, if I could ask this, and this is just me, but so do you have any insights, I guess, from your model? Like, how could we take this more towards an engineering level, right? Because like for instance, with Mark, where he's doing hands-on, how do we bridge that gap? Because
if you want to
build stuff.
My slides are pretty just basic idea, but if you read my paper, although I think I need to look at what my graph says right now, because I was approximating some data and it might not be the best table of results, but I think if you have a tabletop interferometer, an accelerometer, and some lasers or some kind of light that you can have polarization on, lasers are the easiest, I think that you could test my theory. I don't think that it's going to be a particularly hard thing to test. Now, you'd need a boson-Einstein condensate to test one of the elements of the twist torque, but the rest of it could be tested just with a tabletop interferometer and an accelerometer and some lasers is what I think. It's almost to the back where you start. I know it's dense, guys. I'm sorry. If you want, I could write up just an experimental precis just about my ideas for how to test it, which are pretty.
Well, and I can post this. So what I do is on the page at Alt Propulsion down at the bottom,
Yes.
I always try and post the slides and materials. I put those in Google
Good.
Drives. But I did share this for folks, and if they're watching, again, it's on YouTube, and we're streaming in HD now. So
Awesome.
what they can do is, if they're feeling really motivated, they could pause and kind of go through that way. So
That's so exciting. All right.
I'm not sure how many slides you have. Let me see.
There's about 60.
Oh, there's okay. So
Yeah,
I'll stop for now.
I was very surprised I got to the end because I was like, it was like at the end, I was like, am I going to say that equation? No, I won't say it out loud. It's just that thing hanging out. But yeah, well, thank you guys for the opportunity to talk to you about this stuff. And I look forward to being part of one of these lab groups. I don't feel prepared today since it's light on theory, heavy on perspiration, and engineering insight. So, but I'll come back with that, and maybe I'll do a lab. Next time.
Yeah.
When is the next time? It's May.
Yeah, but just send me an email. In May,
I'll flesh out my
or June, one of the two
concepts, and I'll propose an experiment in that group and see what.
Yeah, that would be awesome. That would be really awesome. And then we kind of make the rubber meet the road, right? That would help to validate the theory and help to move forward the experimental work too.
And possibly we can build a wormhole, guys.
Okay. Well, I guess that was.
Yeah, I have some questions as well, if you don't mind.
You don't mind?
Jennifer, were you able to listen to my talk right before yours?
Yeah, some of it. I got into mine, and then my Wi-Fi stopped working, and it was like, what? So yeah, I missed a lot of it. I'm so sorry.
Yeah, I saw you on your phone there dealing with stuff. So basically, we're trying to manipulate the strong force using electromagnetism through this process called dynamic nuclear polarization.
Oh, I did hear this. I caught this. Yes, I was able to.
Does that tie into your theory at all?
Repeat one more time, just to make sure I understand.
You were using the hyperfine coupling to orient the strong force in the core of the atom, making matter coherent.
Possibly, yes. That could possibly have something to do with it. I'd have to see what you're exactly doing and then run it by my stuff. But it sounds like the orienting to get coherence sounds like my thing, because in my thing, the orientation of a system does impact on coherence in my system, which I don't see that often. Where did you get this idea?
From Frederick Alzafon.
Oh, interesting. Who's this?
So he's a guy who he came up with this theory after having a sighting of a UFO. The entire family saw it. Then his son found a book in it was Ufology by James Campbell, and on page 104 there was an encounter with the UFO with an AWACS plane that was recording these pulses coming off of it at microwave range, like millisecond pulses. The dad, who was a physicist, went to a technical library trying to figure out what would have been causing that. And this book by C.D. Jeffries, Dynamic Nuclear Orientation, which describes this effect, fell off the shelf in front of him onto the floor. Kind of like an interstellar kind of experience. He picked it up.
That's so cool. Yeah, I've had experiences like that. And, it's funny because I sometimes wondered, my parents saw a wedding cake shaped UFO, and I was such a little kid that I remember seeing something zipping around, but it just didn't stand out as that big of a deal to me. But it was like a wedding cake shaped light in the sky that zipped around and stuff. And I wonder sometimes how much that impacted me.
So the story's not over. So he filed a patent for this idea. And simultaneously published a paper, Anti-Gravity with Present Technology. And the patent was denied on national security grounds. The paper was already published.
Oh, wow.
And it also, the reason why they're calling it anti-gravity is because dynamic nuclear orientation was discovered back in the 50s. Yeah. But they realized there was there was a discrepancy between the calculated amount of the spin down time should have been about 100 times longer at cryogenic temperatures than it actually was.
Yeah.
So Albert Overhauser, who discovered this effect, wrote that there's something acting upon the sample other than the known processes to disrupt it. So if gravity is acting upon the sample to disrupt its nuclear spin orientation, subatomic nuclear spin orientation, and you're maintaining that nuclear spin orientation, that would be anti-gravity.
Yes. All right. Yes. And I think that's an avenue that we need to look at in more detail. So guys, Tim, you can share my email with any of these people, these wonderful people, Michael, Jeremy, Jared, Robert, Mark, and Gary. Please do. And we can all talk, and I'll be back for the lab next time.
There's also open mic.
Wonderful. Well, before you leave, again, one more giant applause for Jennifer Lorraine Nielsen. Thank you. Thank you so much for presenting. Thank you so much.
Thank you for having me. It's been
and I would love to have you back.
I will. Don't worry. It's happening.
Okay. Oops. Okay. So guys, next up, I do have, let me see, A Brief History of Many Worlds by Daniel Davis. Let me take my earphones out because these act funny when I play videos. So if you guys are cool with that, I do that, and then we can do lab updates. I think that's about 40 minutes long. Okay. Well, let me do that then. I'm gonna share screen. Daniel likes to make everything perfect, so that is why. And in fact, this is the second version of it he uploaded. But he is like one of our resident experts. He is so awesome with this stuff. So what I'm going to do is, and I guess just let me know in private chat if you don't hear this, because I'll hear it either way. So
make it full screen, Tim.
So today we're going to be talking about the history of the many worlds interpretation of quantum mechanics. So without getting too nitty-gritty on the math of quantum mechanics, we're going to go into its foundations. So where does the many worlds interpretation come from? Well, in order to understand that, first we need to go back to the foundations of quantum mechanics. So we're going to look at 1927, okay, with the Solvay conference. It's a confluence of all the greatest minds of the time. We're coming to debate on what the meaning of this new emerging field of physics was. So what were they debating? Well, this guy named Erwin Schrödinger, right, came down from the mountain with his glorious equation one day in the 1920s, and it made everybody start scratching their heads and wondering, what does it mean? What's going on here? It seems to be a good bookkeeping mechanism for doing calculations and explaining things like the photoelectric effect and other such things that are going on. So what's the Schrödinger equation, right? So it comes down from the mountain, and we have our I by h bar a d, it's a g, d by dt, psi over the wave function equals e of psi equals the energy of the wave function. Okay. Now this is literally Greek to me, right? So what is this mean? In a overly simplified nutshell, you start out with your system, you start out with your wave, and then as it spreads out over time, you can divide the energy into different nodes. And you can put them inside an energy well, and then this will give you your basic quantum harmonic oscillator. And you can do all kinds of cool shut up and calculate things with it. The issue that came about with this, and this was the whole original inspiration for Schrodinger's cat, right? He nowadays Schrodinger's cat thought experiment is kind of shown as a weird. It's used for various reasons, but Schrodinger's original reason for doing it was try to show the absurdity of his equation and how it must be wrong, right? And then this is kind of the whole point of the Solvay conference, is to figure out what we do with what we think is wrong here. So we're just going to start with our well here. And we got our two different energy levels. It's really badly drawn, but it is okay, because this is a qualitative talk, right? And in here, let's see, we'll make this red, so hopefully you guys can see it. And then you got your two different energy states, right? So in here, it's going to be A plus B, and it spreads out into A and B. You have your superposition of two states that spreads out into two entangled states, right? The issue is that we know from experimentation, or at least we thought, is that whenever we look at the experiment, whenever we make an observation, do an observation with an apparatus, do something, right? So we flip a coin. I got a coin right here. Say it's it's tails. So to say it's B. So A goes away, and we only know that B is left over. The question is, what happens with A, right? We know it has to go somewhere, because we don't see it. You don't just magically turn into a superposition of two cats when we perform the experiment. We only ever see one cat, right? Okay. Now, this leads to like quantization mechanisms, where then you're doing the Born rule, and then you're renormalizing so you can get the total energy of the system to still add up to 1. Getting ahead of myself, that's not really important for tonight. The point is where they settled on the Solvay conference is you had two major camps. You had Bohr and Heisenberg versus Schrödinger and Einstein in their debates, and basically what Bohr was saying is that, you say you have your system here that spreads out. It starts as 1, and then it spreads out into 2, but we only observe the 1, so we just erase it magically by hand because we don't observe it, and then we just kind of perform the operation again. On down the line. And thus is the weird jumpiness of quantum mechanics. Don't ask too much what's happening behind the scenes. Don't think about what's going on. In the words of Feynman, just shut up and calculate. That wasn't good enough for Einstein and Schrödinger. They wanted to know what was really going on behind the scenes. And the issue is at the time they didn't have a satisfactory answer for the rest of the crowd, which is why the Bohr-Heisenberg and then eventually the von Neumann-Dirac, which is based on the Bohr-Heisenberg interpretation, becomes the Copenhagen interpretation, which is what people are still taught when they're being introduced in quantum mechanics today in university. And it's usually not until you start doing work in foundations, even if you go to do work in the foundations, will you ever start to touch anything that has to do with many worlds. So again, what does this have to do with many worlds? Well, again, like I said, this is in 1927 that this original Solvay conference happens. And, then after the war happens, stuff goes to nuclear physics, and then you have general, and it just kind of goes off to the side. Because Copenhagen is a pretty good bookkeeping tool. The thing is, you still had Einstein and Schrödinger and others were still asking on the side, what's actually going on? And in 1952, was it 51 or 52? I have it right here. Yeah, 52. So in 1952, Schrödinger was in Dublin. at this point. And he is giving a lecture, which we have the transcript of here, titled The Meaning of Wave Mechanics by Erwin Schrödinger. And he goes into essentially what we just talked about, is where essentially you have. He also goes into a little bit about de Broglie and de Broglie's pilot wave, but we're not gonna talk too much about that today. But he goes into the essentially the why Copenhagen and other interpretations are unsatisfactory. So Schrödinger says right here, the situation calls for a revision of the current interpretation, which revels in computing transition probabilities from level to level and disregards the fact that the wave equation, with few exceptions, if any, indicates nothing of the sort, but leads to the reacting systems into a state composed of a wide spread of energy eigenstates. To assume that the system actually leaps to just one of them, which is selected by playing dice, as it were, is not only gratuitous, but as was pointed out above, contradicts in most cases even the current interpretation. And he essentially goes on to there saying that he is going to leave the future of what to do with that work to other individuals. But again, this is that the system spreads out into a state composed of a wide spread of energy eigenstates. To assume that it actually leaps to just one of them, he thinks is absurd. So right here, this is what David Deutsch, who will become important later, is often called the proto many worlds theory, and it's also been explored by later individuals who I do have the copies of the papers of here. So what Schrödinger started to come up to the opinion of later in his life is that maybe the cat really does spread out into both the state of both dead and alive, even though we don't see them. But he leaves the work to future. So Schrödinger himself was obviously already pondering this before Everett comes up with the many worlds interpretation. So now is where we want to start talking about Everett. Right, because remember that Schrödinger and Einstein actually at this time where they were still talking to each other. They were having correspondence back and forth and letters, and they would still discuss, the foundations of quantum mechanics from time to time. So it is entirely possible that Schrödinger had conveyed this sentiment that he was starting to believe to Einstein. There's a few year period where it could have happened. So now this brings us to Hugh Everett III. Now, who is Hugh Everett III? He is the one that is often credited with formulating the many worlds interpretation, even though he didn't coin the word. We'll still get into that later. Everett was going to school at Princeton for physics, and he was studying under a particular John Archibald Wheeler, ended up being his advisor. And I believe it was in 1954. Because remember, they're all at Princeton here, which is the same place that Einstein's at. Einstein gives one final little-known lecture about quantum mechanics and just his views in general. And he gives it to a small room of Wheeler's students. Among them is Hugh Everett. And it is after this late 1954 little last lecture from Einstein to Everett that Everett starts to become inspired. And he starts to really think about the problems of quantum mechanics. And he starts to think about all the same issues that Schrödinger was talking about in his on the meaning of wave mechanics from 1952, a couple years earlier. Whether or not he knew specifically of that, or Einstein had just conveyed some sentiment to him that obviously influenced him to go down this path, Everett started writing a series of mini papers, which, again, this with the history of all this we do have tracked here. And in his series of mini papers, starting in 1955, objective versus subjective probability, the quantitative measure of correlation, and probability in wave mechanics, all in 1955. These would eventually coalesce in his 1956 long thesis, The Theory of the Universal Wave Function. Now, what he's saying here is literally just he fleshes out mathematically what Schrödinger proposes in 52, that what does the system look like if we do just accept that the other eigenstates are possible? And it comes with this weird branching effect. So again, we had the eigenstates here a couple times before, and so if we branched these, or if we trace these out, they'll start to tree like that. And so these will be these three, and those two will be those two, and that one will be that one. And he says that everything will have a life tree. That he also uses the analogy of splitting amoebas. And after 56, and even in 57, he goes around and he starts pitching this to other ideas. Wheeler does. Wheeler even brings this to the 1957 Chapel Hill Conference. Everett was invited. He was not able to attend for other reasons. But at the 57 Chapel Hill Conference, Wheeler does introduce and advocate this early many worlds version. Now, it wasn't called Many Worlds yet at the time, but he catches the attention of Bryce DeWitt. And then he ends up going and he sends Bryce DeWitt a copy of some of Everett's work. And then DeWitt gives a rebuttal. And then Everett just writes right back to DeWitt. DeWitt's initial rebuttal was, I simply do not split. I don't feel myself splitting. And that's a pretty good objection that a logical individual might have. But he was impressed with Everett's reply. And what was Everett's reply? Everett replied with, he kind of invoked Copernicus in the sense of, like, do you feel the motion of the Earth around the sun? Well, no, you don't feel it, but yet it still happens. So DeWitt became converted after that, and he became one of the first champions of many worlds. And he ends up allowing a shortened version of Everett's thesis, because at this time Wheeler had also given the long version to Bohr, and then Bohr wanted it. He had some objections to it because Bohr is Bohr, and Wheeler was very loyal to Bohr, and so he suggested that Everett shorten the long thesis down, cut out the information theory part of it, cut some more of the parts out of it, and kind of just strip it down towards core roots. And then that's what they end up publishing in the 57 Physics Review Journal, alongside with the Chapel Hill proceedings. Alongside with the short thesis, which is called The Relative State Formulation of Quantum Mechanics, Wheeler also gives a companion paper alongside with it. And I have a copy of that here too. And in that, Wheeler says, no escape seems possible from this relative state formulation if one wants to have a complete mathematical model of quantum mechanics that is internal to an isolated system. Apart from Everett's concept of relative states, no self-consistent system of ideas is at hand to explain what one shall mean by quantizing a closed system, like the universe of general relativity. And it was actually the inspiration from Everett in his, because remember the long thesis that that Wheeler got to see, but wasn't initially published, was titled "The Theory of the Universal Wave Function." Okay, and so then this became Wheeler's influence to start thinking about the wave function for the whole universe. And then from that, eventually, Wheeler and DeWitt would go on to even to invent the Wheeler-DeWitt equation. And then from here, the canonical quantum gravity program around the Wheeler-DeWitt equation and the foundations of quantum mechanics and the many worlds interpretation start to diverge. And they're being brought back together now, but we'll get there. I'm getting ahead of myself. So what happens after this? What happens with Everett after he publishes his paper? He gives up on academia and he goes and he works for the Pentagon and the Defense Department, doing consultant work, game theory. He helped come up with the concept of mutually assured destruction. There's a documentation for the book, and I got some other sources for that too. Interesting guy. The many worlds theory didn't really go anywhere, though, until the 60s, when DeWitt publishes a couple articles in some magazines about it. And then he finally, in 1973, gets Everett to put out his original long thesis under the new title, which DeWitt came up with, "The Many Worlds Interpretation of Quantum Mechanics." And that's where the terminology starts to come from there. And that's the origins of the many worlds. But we're not done. Yeah, that's where it comes from. But where did it go from here? Everett was... Some say he was jaded by academia. Others says he was prioritizing his defense work. Nobody really knows. But in 1977... Okay, so backing up from this, though Wheeler did initially endorse Everett's many worlds interpretation, he then distanced himself from it for about a decade or so, as he explored other ideas. But he came back around to it. And in 1977, he invited Everett down to Texas to give a lecture to his students, similar to how how he got Einstein to give a lecture to his students at Princeton back then. But again, this is now in Texas, and he's having Everett give the lecture. And among them is a particular individual named David Deutsch, who becomes an important figure in this story. And he becomes another one of the more modern champions of many worlds, and he is still alive today. Deutsch and Everett hit it off very well. They get lunch together. And though Everett never came back to academia, it has been argued that Deutsch is possibly the closest thing that Everett has had to a spiritual successor in terms of carrying on the work, or direct successor. And so he goes on and he develops it, and then it really becomes the basis of quantum computation. Deutsch has said for years that quantum computers can only work in the many worlds interpretation, and that the many worlds interpretation is not an interpretation. To call it an interpretation would be like calling dinosaurs an interpretation of fossils. Things don't really gain a lot of ground from here, though. Deutsch does his thing, and he still continues the work, and he goes and he helps him, he develops some things. And then finally in 2001, Wheeler and Max Tegmark, who ends up becoming another champion for many worlds, they end up co-authoring a paper in 2001 titled 100 Years of Quantum, where, in a nutshell, they go over the history of quantum mechanics and where it's at now, and they essentially come to the conclusion that they believed that it is time to update the textbooks to reflect a favor for the many worlds interpretation over Copenhagen. And that is pretty clear evidence that, especially by the end, though Wheeler may have distanced himself from many worlds, he ended up coming to embrace it, again, by the end. which brings us around to Tegmark. Tegmark ends up incorporating the many worlds interpretation as the level 3 multiverse, and his multiverse hierarchy as the 4 levels of the multiverse, which can that could be its own talk. So then after that, the next kind of big modern champion for many worlds that comes out of that is ends up being Sean Carroll, who's a very well known and prominent physicist today. He kind of revives the many worlds interpretation in the modern light, and he unifies it with other approaches to the quantum gravity problem that have been explored more recently, like the entropic gravity issue. And he has papers on how through the area entropy law, you can get general relativity to pop out as an emergent property of a many worlds version of quantum mechanics in a very natural sense, where you don't have to go through any quantization schemes or mechanisms to begin with. And so that's very, very promising for the program. Beyond that, more recently, you've had Dr. Barak Shoshani continue the work of David Deutsch on the quantum physics of time travel, and go and prove rigorously and mathematically in a series of papers starting in 2019 up until I believe he's still working on and publishing more, where he comes to the conclusion that any form of time travel can only work within a many worlds universe, because eventually Novikov's conjecture no longer can solve every paradox, and you need to account for other timelines, which is a many worlds thing. And he goes and he proves it very quite rigorously, and that's something that we can provide some of the documentation and stuff of. And then most recently, you've had Maya Banowitz going and asking what happens if we take the Schrodinger equation, or Everett's principle of quantum universality. Again, the whole idea is that the universe just obeys the Schrodinger equation, full stop, no collapse, no erasing other universes. But that's it's usually done in the non-relativistic limit with the time-dependent Schrodinger equation. So we asked what happens if you apply Everett's framework to a relativistic version of the Schrodinger equation, like Dirac or Wheeler-DeWitt. And from there, you end up getting into the holography of time, and it comes up in a very nice and neat theory of everything that ends up more or less predicting that you can traverse these many worlds by using things that resemble what we would today call a warp drive.
Okay, Dan here, post-edit. New place, say me. So this is the crucial point in which we must kind of take a moment back to sit and reconcile everything that we just there's a lot packed in here into everything that we just kind of put into this last few minutes. But it's this idea that general relativity can be emergent through quantum entanglement entropy through any robust quantum system. Now, again, it's not just Sean Carroll that showed this. It's been Ryu and Takiyanagi, Eric Verlinde, Sarfati and Rodal have been working on this too. I mean, it's starting to become a pretty robust feature of this emergent gravity via the area entropy proportionality laws that it shows us that any object within general relativity is itself a semi-classical emergent approximation. It's a semi-classical approximation of some larger entanglement structure, of some quantum system. And this aligns perfectly, again, with Everett's whole quantum first program, the idea of quantum universality. Now, I know some of you are playing with the idea that maybe general relativity should be more fundamental and that maybe we can get quantum mechanics from that. And that might be valid, and that might be a sort of top-down approach of getting to this sort of same thing, and we can talk about that in the future. But what we really need to digest this. And so one of the things that comes out of this is in part the ER equals EPR thing, the idea that entanglement can be explained by wormholes, or vice versa, that wormhole are entanglement. And so we start to look at this, and we can almost view wormholes and warp drives as part of the same coin, okay? They're two sides of the same coin. We can think of warp drives as slower than light wormholes, and less than instantaneous wormholes, and we can think of wormholes as instantaneous warp drives. It's a pretty equivalent way of thinking about it, and what they both are at their core are very clever takes on quantum entanglement. So there's going to be other ways that we can start to view this system, and we might be able to find equivalent areas of mathematics that we can start to probe and maybe find better models that we can go and use this for, right? This is where the many worlds starts to become relevant to the idea of propulsion, because I know that's something I'm sure many of you are wondering to yourselves right now. What does many worlds, the idea of a multiverse, have to do with propulsion here at the APEC conference? And again, going off the work of Shoshani, which I have here, Shoshani and Deutsch, as well as others, including Sarfati, who I can probably throw in a screenshot of the text, has said that the new quantum theory is like a many worlds 3.0, and so everyone's kind of coming onto this multiversal idea. Now the thing is, what does this mean for the ship? What does this mean for navigation when we finally build the thing, right? So we can use this in one part to build the thing using quantum computers. Actually, that's a good digression right there. So the whole thing with David Deutsch, so the whole quantum computation thing, the Willow chip, and the very popular article that came around with that, saying that this new Willow chip is proof of David Deutsch's claim to the multiverse. It's a bit of a misnomer. Really, what David Deutsch has said all along is that the idea that quantum or quantum computation works at all is proof of the reality of the quantum wave function, of the quantum multiverse, of these many worlds, right? And so what it boils down to here is when we finally build these craft and do the thing, it's not just a faster than light spaceship. It is an entanglement drive for the multiverse itself. It is a multiversal vehicle. And so we have to be very careful that when we finally do build one of these things, that we have to account for those other timelines so we don't lose all our investment that we go and put into this thing, or else it'll literally be lost to time, right? So, a very important paper from someone named Dr. Yuri Eroshenko, which can be found here in the beautiful temporal compendium, which I'm sure many of you should have a digital copy of at this point. If not, I can help you. Is this paper called Escape from a Black Hole with a Spherical Warp Drive. Right here. Now, what is this paper? And I can throw it up so you guys can look at it on the screen here with me as I read it off. But what they go and they introduce is they described how the passage of a spherical warp drive through the event horizon of a black hole from inside to out, right? So if we're looking back earlier in volume 2. At the paper, branches of the black hole wave function need not contain firewalls. Carroll introduces the idea that there may be certain mechanisms that might allow someone to exit a black hole or transfer from one location on its wave function to another, which again, in volume 2 of the compendium here, it goes into semi-rigorous detail as to why it is at least very analogous to think of the universe as a black hole. Volume 3 will expand on that. So, you can use a warp drive to escape from these black holes, to escape from one branch of the universe to another. And they go and introduce the WD equals EPR conjecture as an extension of the ER equals EPR conjecture. This plays on the whole idea that I just explained a second ago about how warp drives and wormholes should be seen as two sides of the same coin, in some respects at least. Now, this all just enforces the idea that as when we start to think of these things as macroscopic quantum coherent structures, what's really going on, and Pius has talked about this a little bit, Sarfati has talked about this a little bit, and to play on the ideas of David Deutsch, the skins of these craft at the highest levels, when we start to build them, they start to... You need to have a very high level of computation in order to build one of these things, right? In order to do all the calculations on how to manipulate the warp bubble, in order to actively traverse to where you want to go, right? Because again, this isn't just a simple one-dimensional Cuvier-style warp geometry. This is a fluid, dynamical thing that has to steer and change. It has to be a dynamical entity, and so that's going to take a lot of computation in order for the computer to be able to run it. It's you can think of it as the world's most advanced fly-by-wire system. Now, when we start thinking of the quantum computation side of this, when we're doing these at a faster than light trajectory, or at least relative from an external point of view, what's really going, because remember, locally inside the ship, you're not breaking the speed of light. Really, what's going on is that you can think of it as the surface of the ship, the skin, where the warp bubble, so to speak, is itself. It's becoming entangled with the boundary state of the universe, and then there are reasons for this that have to do with holography that are expanded on in Volume 3 of the Compendium. So just bear with me here. As you become entangled with the boundary state of the universe, this static boundary in time where everything is encoded, and you perform a phase rotation on it, which is what time like a trajectory turns out being akin to. When you have something like a warp drive, you can tilt your light cone in this phase rotation to other parts of the multiverse that you don't normally overlap with, a form of time travel within the multiverse. And so from a certain point of view, you can think of it as this, the ship itself becomes quantum entangled with the rest of the universe, and it's sort of like an entanglement elevator, and you can drop yourself wherever you want in the multiverse if you have precise enough calculations and a good enough navigable. And again, it becomes a very complex engineering issue from here, but that's just it. This is an engineering issue. This is not this is no longer a physics issue at this point. We have the physics here. I have volumes and volumes of books, pages and pages, and I have more down there where it slowly traces the history of this in academia with all human physics, about how these don't break the laws of physics at all. They obey them perfectly, and it ends up coalescing in what is probably the ultimate pinnacle of a human technology at this point. Or at any point, really. Now, where do we go from here, right? We need people to start looking at all this stuff, because this isn't a complete picture. This is a mosaic that says we can go and we can push the boundary forward, and there is enough here that warrants more investigation, right? So we need more research into more complex warp bubbles. We need people doing research into some of Andrew's stuff about seeing what's really going on at a gravitational side there, because there's always some kind of conversion from EM to gravity. There has to be, right? We don't fully understand it yet, depending on whose model you're using. There's some people that think they do, and that's, part of the whole debate in itself. But there is a path forward here. And the implications that come with it are enough where we have to start reconsidering our notions of time and what's going on with these craft when they are doing the thing. And going forward, I mean, that's something we're really going to have to take into consideration here. We are probably getting a little shorter on time here. I could go into another few tangents on stuff that are semi-related, but a lot of it is starting to get more speculative. We need help. We need help in researchers. We need people to start kind of help review some of these processes and ideas and refine them and come up with them more. We need to start working together a bit more instead of arguing over whose idea might be right. There's too much overlap here for us to be ignoring. So I think I will slice this into the post edit, which should put us close to 45 minutes. And that will probably be enough multiversal rambling for tonight for you guys. So you guys have a good night. I'm sorry I could not be there in person to answer questions, but we'll figure out something to do from here. Yeah. Thanks. Have a good night.
Okay, we are back. Let me see. And yeah, we took this. Okay. Well, so yeah, that was, I asked him to put that together and he graciously accepted, I think like 2 months ago. That was when Google made that announcement about many worlds, but I think that also applies to propulsion. He tried to tie it in with that too. So there's a lot of really interesting physics paths. So Mark, you said that Deep Prasad might be joining us. We could do lab.
1 minute. He said 1 minute. Yeah. Do lab updates, or we can do that first. Yeah.
Okay. Well, let's do Deep first. Let's have him do that, and then
he's not here yet, so maybe just give him a couple more minutes and do lab updates first. Yeah. Drew, are you ready?
Yeah. Can y'all hear me?
Okay. Yeah. Drew, go for it, man.
Oh, okay. Just got back from pizza, so just firing up the system now, and I got to tell you, as much as I love building warp drive engines, just building the surfaces is becoming a lot of fun. This is the vapor deposition system, and let me see if I can flip around. Give me 1 sec. I just figured out how to move the cameras. That was not me, by the way, guys. Okay, so that is the vapor deposition system. I've been working with it a lot lately, and it's very difficult to do two things at once.
There's Deep right there.
So that is the vapor deposition system actually working. That is plasma being generated by the magnetron, inverted magnetron head. And that is live. We are currently nuking material. And I thought I'd just kind of show off a little bit about what it looks like. So this is a real typical piece of polymer that starts out, with nothing on it. And then after a few minutes of magic and some coolness, can vapor deposit different metals on there and in different orientations, different crystalline structures, different combinations of metals. So that's just a real typical setup. The control panel is just really cool. Shows the pressure in the chamber, shows the pressure in the well of the turbo. These are in that's 7 millitorr, or it's 7 millitorr. And this is the pressure in the backing pump. And again, the whole setup is just, the whole goal is to be able to put any material, metallic or semiconductor, that I want on any kind of polymer or ceramic to make any kind of meta surface that I feel appropriate. So that's pretty much what's been going on. Oh, this is really rare. I got just a sec. It's almost never happened. The vacuum chamber is empty. The test chamber. Again, that's the vacuum chamber. Going in. This is the Faraday shield that's around the load sensor, load cell. If you don't have your load cell in a Faraday shield, then your data is just skewed. So anybody that's testing without a Faraday shield around their load cell is lying to themselves. And this is just the way the system all goes together. The test article generally hangs right here. And then it's connected to the load cell. And then the magic ensues. So that's pretty much all that's going on down here in sunny Florida, where it's freezing outside. It dipped into the 60s again tonight. So, any questions?
Drew, that is awesome, man. That is totally awesome.
When are you going to space?
Curiously enough, I had a very, very interesting visitor here last Saturday who represents somebody who just so happens to own their own space program. So, sooner rather than later, it's the dream. Of course, those people that ripped off our patent are up there right now. And they obviously haven't turned the thing on because they're still losing altitude. But who knows? Maybe sooner rather than later.
We're rooting for you.
Thank you. Actually, Mark, your unit. Look, I have a sign.
I like it.
It's my sign.
Oops.
That's the toy that's going to be headed to you soon, Mark.
Is that running in air or is it?
Yeah, I just put a puff of air on it. That's what it'll look like.
Sweet, I love it. Can't wait to run that in a vacuum chamber and see what it does.
Yeah, that's the dream of the future. That's the Tomorrowland toy.
That's amazing.
That's way into the future. Oh. No, thank you. So that's it. Any other questions? And if not, I'll sign off, and y'all can get back to cool stuff.
Oh yeah, we're going to talk about this upcoming hackathon. You should check this out.
Yeah.
Tim, you want to do a screen share and show the website?
Yeah, absolutely.
Mark, why don't you do that and I'll put it up. I don't have the URL offhand, but Deep is here. Deep, welcome, man.
Hey,
Deep, you have the URL. Maybe you could share it.
Yeah, absolutely. Happy to
drop the URL, drop it in private chat, and I'll put it up.
Sure, sounds good. And great to see you, Tim. Long time no see, brother. Hell yeah.
Yeah. Well, and I will see you. So Deep, I want to bring my, I'll ask now. I want to bring my super duper camera set up. Can I bring my camera and get lots and lots of photos and maybe some spot interviews?
Yes, you can, my friend. That would be an honor, actually. Thanks so much.
Sweet. Yeah. No, dude, I'm all about that. Trying to capture history. That's my thing.
Oh,
and anything, and this goes for like all the conferences and stuff. Like anything I shoot, if it has value, it's yours. I just kind of, it's out there.
That is, really wonderful and very much like pro open source mentality, which is what we're going to be, trying to imbue in this hackathon. Not trying, we will be. So.
Okay. Well, yeah, I've got a camera. I've got 2 terabytes worth of hard drives.
Nice.
I'm bringing actually, Mark. This is Mark's fault. Mark started this, and then I think Jared is tagging along with this too. So,
yeah, it's you know what? For that, Mark, we are in great debt to you, my friend. I appreciate that that you're bringing along the crew. I think this is going to be, in addition to APEC, really we're going to try to be as complementary as possible and pull in the deep tech crowd and the tech community and SF, the same kinds of brains, right, who And Marker, I'm not sure who's sharing, but I'm down to share my screen actually if you guys want. It's probably easier.
Yeah. No, go for it, man. Go for it. Let me see.
Awesome.
Yeah. Do you know how to? So this is StreamYard. You probably used it before.
I've probably used it a long time ago actually, but let me give this a shot.
Yeah. So I'm going to, let me see. I'm going to do stop screen. So then if you click the present button and share screen, there we go. Okay. And that's yours, sir.
Right on. Awesome. Right on. So thanks so much, Tim. I appreciate it, brother. I guess let me just take a step back a second and give everybody a 60-second overview on the whole purpose of this hackathon and what the motivation was. So first of all, I think it's worth just like, I know that we're super technical here, but for anybody who might be watching who doesn't know what a hackathon is, the simplest way to think about a hackathon is the same way the DoD tried to rebrand or has been rebranding UFOs and rebranding it to UAP. A hackathon is really just a programming competition or a technology competition. It's nothing more, fancy than that, really. And so within that context, the purpose of this particular technology competition is to facilitate the development of as many hardware and software protocols as possible that will accelerate the discovery of UFO and UAP across the board. So all the way from the epistemology to the phenomenology to the actual tangible anti-gravity and advanced physics and exotic physics that UAP represents. What we want to do is sort of take the same technical and intellectual capital that powers Silicon Valley, right? Which is effectively a multi-trillion-dollar industry. Not effectively, it is, and which makes it basically a nation state, right? It's the GDP of like California, for example, is higher than like most countries in the world. And that's in large part due to the tech economy, and the tech economy, which is like Airbnb, Apple, OpenAI these days, Anthropic, and these advanced AI labs, and these advanced tech companies. Meta and so on, they are powered by humans, of course, in the end of the day, right? And that kind of talent that's concentrated in the Bay Area. And so the San Francisco UAP Hackathon is aiming to sort of create this coherent laser of intellectual capital and burst it and focus it purely on the UAP problem. So and feel free to interrupt me, at any point, literally anybody. Y'all are awesome, smart people. So, happy to answer any questions. But it's going to be on the USS Hornet. We rented that out for the weekend. Picked it because of its symbolic power. Thank you, my friend. I think some of the best money ever spent, potentially. It's also very important for giving people empathy. Oh, whoops. Let me just go back up a little bit. But it's also really important for giving people effectively empathy of like what they can expect and what people go through, such as like U.S. Navy pilots and USAF and so on and so forth, when they're seeing a UAP out in the distance or out at sea. So that being said, we want to really drive the sort of stake through the heart of the problem or the beast. We don't want to make the same mistake as other organizations in the past. I say this as diplomatically as possible. I think because of stigmatization and weaponization of guilt, shame, and fear against scientists who were looking into this subject, whether it's free energy or 0 point energy or anti-gravity and so on and so forth. Whether it's due to that or some other reason, scientific efforts in the past, technological efforts in the past, have often been subject to tampering or watering their message down. But we're not going to do that. We're not going to hide. we want to acknowledge first and foremost that this is literally possibly the most existentially relevant problem that people could be working on, which is, are we alone in the universe or not? And can we prove and disprove it? And can we find technologies along the way, regardless of the truth as we pursue it? So with that in mind, we have 6 tracks here. We have the material science track. And I don't want to get into like anything like too like contentious or whatever. I saw your tweet, Mark, as well, about some of the data or whatever. So I do appreciate that. That's hilarious. But basically, the material science track is to expose the computational chemistry and synthesis and fabrication and characterization problems that occur and show up, and the anomalies that show up when looking at alleged crash recovery materials from different UAP crashes. We've made available, I've made available through my past company and the IP that we developed. We're going to be open sourcing a number of agents as well as data and models around neural networks for density functional theory that you can use to predict electro-optical properties such as charge density and local density of states given a crystal structure. So that's really exciting. What I'm hoping to see people do here is take the AI for density functional theory and molecular dynamics works that I've been working on for many years. Take some of the stuff that we've released through my company GenMat for this, and then also combine it with Gary's data and or Jared's data and or whoever else's data is going to be contributed to this network. And so the idea is to be able to take the best of what everyone has to offer, whether it's really proprietary, AFM data or APT data, or whether it's really powerful machine learning models and weights that might have taken tens of thousands of dollars or many millions of dollars to finally create. So the idea is to really let the hacker community first learn trial by fire computational chemistry, AI for material science problems, which are already very well established, very deep field, and especially these days. And then also get exposed to the anomalous aspects of UAPs as it relates to material science. And then third, set up an open source and decentralized reverse engineering AI for material science pipeline. So this should be a tool. Ideally, we have multiple tools that come out of this that are really easy to use, that are totally LLM generated, agentic and agent driven, where you can literally take existing compositions or crystal structures, take their characterizations, and then feed that to these agents and these models that we want our participants to further develop, take what we've already built and keep building on it, really. So the idea there is any single person here, as we experiment in our own labs, we might have some sort of particular material we want to inverse design, maybe has some thermal capacity, some electrical properties or optical properties or structural properties. And we don't know exactly what chemical composition, crystal structure, allotrope, or symmetry group might be the one that's best for it. This is the kinds of tools that we're gonna try to further develop. So yeah, does anyone have any questions for this track before I jump on to the next one?
So I do have a quick question here.
Yeah, please.
Let's see. So how should I? Oftentimes the challenge with materials analysis is just the equipment up front and like getting access to it. One of the things I think at a hackathon that could be done is just figuring out how to write drivers for a bunch of these big pieces of equipment. I wonder if it's possible to just have a bunch of equipment that would be useful for analysis just sitting there, and
That's
then
a great idea.
drivers for it. So it's like open source drivers to connect and extract data and analyze it, maybe, or yeah, because
Yeah,
that's a big thing. Like you got aside, like if you're not a specialist, the only thing you can really do is use like what's that thing called that people use in the lab? LabVIEW.
fair enough. Right.
So it would be really useful to have a whole bunch of drivers to connect with this sort of equipment.
That's brilliant. I really like that. Yeah, I like that a lot. A lot
So,
of
but
yeah,
that's half of it. So the question would be then,
yeah.
would it be possible to have a bunch of equipment there present at the hackathon for people to try interfacing with?
That I think it might be, with 6 days coming up, it might be too short notice. But let me think about that though, because I do have a lot of friends with some really advanced material science labs in the area who might be, willing to, yeah, lend a few like devices, equipments,
Yeah.
and so
And
on.
I'm sure their labs would be happy to have the capability to interface directly with the equipment.
Yeah, 100%. It's a good
Yeah.
point.
Okay. Well, yeah. Show us the next one, Deep.
Yeah, absolutely. So the next one, Tim, is biologics. So this is basically going to be looking at, we're talking to the scientists who are deeply involved in the Peruvian Nazca mummies, and all the controversy around that. We want to use this as a way to sort of, again, trial by fire, show people the true anomalous extent of the subject. 5-6 years ago, when I was looking at this data, when this first study first came out, these mummies and so on and so forth, and Steve Mera was looking at it, right? He made those documentaries on it and stuff like that. And first he said they're real, then he said they're fake. I was sure that this will be, kind of like a story of the past. 4 or 5 clinics back then, forensics clinics, had looked at this thing, but since then, dozens and dozens of clinics and forensic specialists and anthropologists have taken tissue samples, analyzed different aspects of these bodies, if you will. And so, what I'm interested in with this track is, and what we're interested in general, the leadership in general, is just how do we create anomaly detection algorithms for gene sequences? How do we prove or disprove whether something's a hoax or not? So that we, whenever we have another alien mummy, like example or event, there's a whole bunch of tools around gene sequencing, forensics, tissue samples analysis, and so on and so forth. Kind of similar, Jeremy's smiling, but kind of similar to what you were just proposing, Michael, earlier as well. So yeah, so that's the alien mummy track. Awesome. Now we have the psionics track, and the psionics track, and you can tell this is easily by far the most out there hackathon probably ever thrown in San Francisco. I'd be willing to bet, just because we're like 3 controversial subjects in right now, like so with psionics though, we still want to ground it to reality, and so the way that we're going to do that is we're going to be looking at machine brain-computer interfaces and looking at statistical anomalies. And once again, going back to this anomaly detection sort of approach or ethos, we're going to be looking at, can we clearly create distributions and models that detect when somebody has successfully affected psychokinetically some sort of electronic device, beyond ways that conventional quantum mechanics would be able to account for. So, for
Like
example,
Ingo Swann with the magnetometer from Sci-Spies, right?
perfectly, exactly, Jeremy. That would be the ideal case. And so there's, my hypothesis is that there's interesting quantum computing related experiments we can do, where we can basically instantiate like IBM or Rigetti quantum computing devices, and then basically we sample from the devices. We choose at random, what the rotations of the unitary gates are for the circuits, or maybe we can design the ansatz. It really doesn't matter. And what we ask ourselves and see is, and maybe we model off with like Bell's inequalities or something, or like the CHSH inequalities, and we ask ourselves, okay, once we apply these circuits, we apply these inequalities, can we actually violate them further than what should be even statistically possible using psychic phenomenon? That would be the idea. The next track is propulsion. So this is
one question before we proceed. Are we going to have a CE5 meditation event on the Hornet to try to psionically,
Dude, how can we not? We absolutely will. Saturday night, I think the boys will all be outside, and we'll have some fun there.
Aren't you bringing in Skywatchers?
I am, yeah, you got it. So I already asked about if they're down to do like a summoning thing. It's not that simple, or like we probably won't be able to do that with them. Like they'll be there, but like they won't have all the equipment. They're summoners and stuff like that. But
well, and again, Deep, I would love to get photos. I would love to get photos.
Dude,
of as much of this as possible, man.
The better cameras, the better for everybody. So
I've got the best they make for a reason, because this is making history. So,
dude, amen to that. Yes.
Deep, one more thing. Whiteboards.
Yes.
Whiteboards for every table.
Good idea, actually. That we will source like 5 to 10 whiteboards, probably. That's a good point. Huh. True. Nice. I like that. Thanks, Mark. That's a very practical piece of feedback. Awesome. So yeah, if there isn't anything else on the psionics, the next one is right up everybody's alley here, which is propulsion systems. And so here it's going to be, unless y'all are able to bring hardware, this will mostly be a computational physics play, because most people will be like not really able to like access like really advanced like hardware, propulsion hardware right then and there. But the idea is to develop a few things. One is, can we develop propulsion signatures to detect and track hypersonic and supersonic objects? And so this is super relevant for both a national security, defense, and UAP perspective. And so the idea there is, can we have somebody working on modeling the plasma growth on the surface of a hypersonic projectile, like a scramjet, for example, air-breathing scramjet, glide missile, where you want to model as the plasma sheath grows. What you want to do is you want to model literally picosecond by picosecond at the nanometer scale, right? Can you model how the plasma grows? Because it's going to be a function of the chemistry of the coating of the hypersonic glide weapon itself, combined with the ionized oxygen, of course, the atmosphere. The atmosphere composition, chemical composition, is going to be different depending on where it is in the world that the hypersonic, projectile, whether it's a weapon or a UAP, is being dropped, right, or currently existing in. If there is a hypersonic drill, to look for, the chemical composition or atmospheric composition in Africa, quite literally, is different than in India, which is different than in Canada. And that might seem to be trivial in terms of chemistry or chemical difference. But when you look at modeling plasma growth and plasma growth gas phases computationally, it's one of the most complex computational problems ever. And the reason why is because plasma growth has a very high permutational surface or combinatorial surface area. And it's a function of the quantum chemistry, the underlying quantum chemical rules that exist between the coupling of the coating of the paint and the ionized gas itself. So it's the geometry of the surface, plus the chemical composition, plus the structure, plus post-molecular dynamics, really high excited, very, very high energetic quantum states. And the higher energy quantum state that you have, the more complex quantum computing, quantum phenomena, algorithms that you need to model it. So all that's to say, there's a whole bunch to do here. If you guys have any particular modeling problems, Jared, please, go for it.
Yeah, I got a question on this one. So it sounds like for the propulsion segment, you want to do hypersonics modeling. You don't want to do UFO modeling, because
I do want to do that as well. Yeah.
But the reason why I say that is
we have hypersonic signatures.
Well, that's what I was just going to say, was because the lack of sonic boom, the low Hole temperatures. There's a couple of observables about the UAP that suggest that they are acting very dissimilar from everything we understand about hypersonics.
Absolutely. Yeah, indeed. And I would argue that's certainly true for just like classical and quantum mechanics. These objects seem to defy both, unfortunately, paradigms of physics. And so, yeah, I'm glad you asked that. But yeah, it's not the only focus, like the hypersonic plasma growth modeling, or hypersonic Newtonian bodies, right? Like, it's not that's not just the only focus of this mission. It's there because we want to have a proper ground truth or baseline for calibrating these hypersonic detection systems. So it's just the better we have a ground truth, right, or easier way to classify a hypersonic weapon versus a UAP, the faster we can determine whether it was an anomaly or not. So that's really the thinking there. Yeah. But yeah, absolutely, I agree. They're clever. God knows what kind of weird space-time metric engineering these things are doing. So that's the other aspect of the track, is that we're going to be really, really open to seeing if people can like build these computational modeling tools of physics, combine it with these really powerful AI agents, and see if we can simulate new physics or propose new physics theorems, as well as go back to like Maxwell's equations and recover the quaternion structures, look at within the quaternion structures, look at whether there are scalar waves that can be recovered, algorithmically, rather than like being rediscovered or proposed by like Bearden, for example. So that would be the other play here, is basically use super advanced AI to go back to the oldest physics and find any secrets that we might have missed and verify.
So is this purely theoretical, or are we going to be talking about actual hardware solutions?
Well, we wanted actual real hardware for this stuff, but yeah, we are also going to be welcoming like any advanced propulsion system designs. We have a few people coming who are really good at like nuclear propulsion, nuclear engineering, for example. We have people that we've invited from Caltech who like specialize in like antimatter and quantum electrodynamics, and just like kind of across the board, quantum gravity as well. Not the string theory kind, the quantum gravity in the lab, like the Lennon Susskind kind, the kind that we were talking about earlier, Mark, as well. So that's the kind of like final piece. The thing I'm kind of like, I want more is actual physical things for people to tinker with, because for the sensors and detection side, which is a track that Skywatchers is sponsoring, that's not really fully on this website or integrated completely yet. Like we haven't put Skywatchers logo and all that. But in that case, we're gonna be having like actual kits, right? Like we've ordered a whole bunch of hardware, gimbal systems, actuators, servo motors, and stuff like that. And so, we don't really have an equivalent for the propulsion track for this year. Next year, though, I have a few ideas from like ion propulsion, like setting up like basic like systems or stations like that. I don't know. There's a few ideas. I think you guys would have way more, frankly, suggestions there. So, open to hearing anything.
Is there going to be any like where to present? I mean, there's obviously you have presenters scheduled and stuff, but I mean,
yeah. So presentations will happen on the USS Hornet, and then right after that, we'll have like a mini little after party, like gathering, chill kind of event, or whatever. But yeah, it'll happen. Yeah, on the Hornet in the center of the ship.
Awesome. Is there power available, like AC?
Yeah, absolutely. Let me know if there's any particular requirements you have, Mark, and I'll coordinate with the logistics, with ship logistics.
Yeah, because we could get a couple. I could bring a couple presentations with me if things moving around.
Oh, sick! Yeah. Well, again, it's a stationary ship. Like, I wish we could actually have been able to charter it, but it'll be still if that's what you mean. But it's stable ground.
No, I mean things like moving around on the table.
Gotcha. Okay. Understood. Gotcha. Yeah, no, that would be exciting, man. Like having real exhibitions. Yeah, yeah, we also have like awesome guys like Jesse coming as well, right? So, he'll be able to like go check out some of your stuff too, and people like that as well. I think a lot of tech people will be very inspired, in my opinion, by what they see, because you guys are real builders, and there's a huge building culture here in San Francisco. In my opinion, we've deviated from our roots in Silicon Valley, where it was literally spawned by Bell fucking Labs and the integrated circuit. And we're out here like writing fucking code at every other hackathon. So that's why like it would be great to have like
Bell Labs started over here in Jersey, buddy. My phone has the area code 201, which is the #1 area code in the world.
Oh, dude, that's amazing.
Yeah, there's no 101 because that would confuse with a country code. 201 is area code #1 in the world. 202 is Washington, D.C.
Dude,
that's because of Bell Labs right here.
You're even in the Hawthorne area. Like you're like in a very symbiotic, like metaphorically. But like, yeah, I really should have said like Fairchild and so on and so forth, semiconductor. But the point is that it was built on the backs of like the work in hardware, right, in silicon, and like being able to like push those boundaries. And so, yeah, I think it's super important that we revive that energy. So I think, yeah, you guys will be able to inspire like all these hackers, and hopefully vice versa. Some of the stuff they can do with software and with AI is quite literally like magic, to be honest. And that's what I saw it with my own eyes working on AI for material science. I still continue to and you guys will also see like, as we open source and as I make some of these agents available. So it's going to be, really cool. Awesome. So the next track, last two tracks are Civilization Simulation. This is, again, way more AI agentic driven. This is especially going to be important for people who are interested in, especially the AI community today. There's a whole growing group of people who are increasingly concerned about AI safety and what it means to build a super intelligence that could potentially be smarter than, 1,000 times smarter than any human. And so the ethical and safety concerns there, all that spans from not being able to predict what super intelligent emergent phenomenon might actually look like, what those societies may look like. So this is more theoretical, not total opposite of the experimentalist in this group for the time being. I will say it starts becoming more real as disclosure and the disclosure agenda furthers. The reason why it will become more real is because we don't yet fully understand the nature of weapons and physical interactions of NHI as it relates to humans. Once we do, we'll be able to use those as parsimonious variables and parameters for more advanced models. But being able to quantify the possible physical interactions and if superintelligence can have on us requires understanding the physics that they understand that we don't. So, just random side note. And then finally, and I think this will be relevant we believe this will be relevant for really the whole community, is the on-chain UAP detection and truth management system. So basically consider this, right? We have so many different UAP efforts all around the world, all these different hardware stacks and sensor stacks that we're currently depending on. And a lot of it is like apples to oranges. What the Galileo project might be using for their infrared sensors or their at-home kits or detection or ground-based surveillance systems may be different. The whole setup might be completely different than what Skywatchers uses. And therefore comparing two orange, let's say, spheres or orbs may be challenging, right? So how do you standardize the hardware and software being used for UAP detection, tracking, and safe and peaceful recovery? By safe and peaceful, we mean, not shooting them down, but, getting them to land instead on their own will. So we have a couple awesome speakers, speaker lineup. We have Gary Nolan, super excited. Gary's donating some of this data. I do want to understand and clarify that at some point. Doesn't have to be on air, and so on. So But yeah, he's been super cooperative. It sounds like there's a lot of uh, talk around the purities of these materials and samples. So definitely want to hear and learn more about that from your guys' point of view as well. As I mentioned, Jesse's coming, which is gonna be super sick. We'll be recording a couple cool podcasts for American Alchemy there, and I think if you guys like bring your demos or like bring whatever you end up thinking is cool, right? Whether it's that sort of like that Tesla coil plasma generation, like little propulsion system that you had, right? Whether it's that or whatever whatever you're feeling. I think it'd be super sick to get that on American Alchemy, and I'm sure Jesse would be happy to have you guys show that. And then Eric is gonna be dope. That should be interesting. And then we have Peter Skafish, one of the founders of Soul Foundation, Danny Sheehan, and then we have another person. I haven't added him to the website yet, but Jeff Nicatelli will also be coming, who was the key eyewitness to the Vandenberg Red Square UFO incident. So he witnessed this floating red object for a little while. So so that's it. I'm super pumped. It's gonna be 3 days.
Awesome.
Be sick.
Well, Deep, let me jump in. So the first thing that jumps out at me is, I think it is so awesome that you were pushing forward in terms of innovation, right? And trying to break down stigma and move the technology forward and really focusing on that. The other thing that I think the selling point for this, right, for anybody watching now is this is going to have a lot of heavyweights at it. So for people who are interested in networking, this is a great place to meet people who are in the know and making change happen, right? So your change makers are going to be there. And so folks want to attend this. They're going to learn about kind of the cutting edge and actually beyond the cutting edge in terms of UFO hacking. But they're also going to meet amazing people. And like you said, this is on the USS Hornet. So this is kind of a national defense monument, right? So
you got it. Absolutely.
I am super excited. I'm super excited
to have you here, Tim. And the rest of the crew that shows up. It's gonna be great.
Well, and again, my big thing, and the guys can attest to this. For me, it's like I love capturing history, and what you are doing is history in the making. So it's just like, I just want to try and soak up some stuff, and so I'll just kind of basically try and blend in with the shadows and take lots of photos. But
dude, you don't have to blend in, man. You're doing so much important stuff. APEC, as I bring it up with my tech friends here in San Francisco, again, some of these guys are very close to many billion-dollar companies, right? They're all excited. It's not like there's no appetite or no interest or curiosity. They just don't know this stuff exists, that APEC even is a thing, that people do anti-gravity research, like realistically, not just theoretically. So
I could bring the APEC posters. I got them here.
Bro, good. Yeah, that would be awesome. You're welcome to brand whatever you like. It's my hackathon, like whatever. You can do whatever you like. Yeah, that's perfect, Jerry.
Yeah, no,
we'll bring one for you.
It's exciting stuff, and my hope is, and I'm sure you're going to have other folks there with cameras. Jesse is going to be there with a professional, because Jesse does absolutely amazing professional quality podcasts, right? So so I'm definitely probably not going to be the only person there, but I would love to have like more media just to help record and document, as well as, God forbid, what if you do next year? You're going to need some promo materials.
So. No, 100%. And we will. And we're going to do it bigger and better every year. I mean, the suggestion that Michael had earlier, that was fantastic, right? About just like having like really advanced chemical characterization and equipment there.
One of the other things, and Deep, I think I mentioned this to you when we talked, right? Because we met in Austin briefly. Like you are new school. And new school is so valuable, because the old school UAP UFO community was very focused on let's track, let's identify, let's try to understand, right? And which is kind of that has its place, but the new school is about I mean, like you've got this split, like Mike Gold and Lester Nair, right? And they're getting seriously involved with congressional action. And then the stuff that the guys in this conference are doing, as well as the hackathon, like you're like, okay, let's dig in, let's build this, right? That's Mark's phrase. Let's build it.
Let's build it.
So,
I love it. And that is the hacker and Silicon Valley way too. It's all about building. That's the spirit and ethos that we imbue. So it's gonna be really great to merge these two worlds deeply.
oh yeah, absolutely. And there are people, like you said, there are tons of people out there. I've been following Jared around for the last like year at this point. He has got so many tests on Art's parts. It's amazing.
Oh, dude, that's awesome. Yeah, right on.
I mean, between him and the other guys, not just that sample, but yeah, he's got hundreds of SEM photos.
Jared, are you coming? Okay, dude.
We're all going to be like crunched into this tiny Airbnb within walking distance. We might have to borrow a blanket or two from you.
I blankets, towels, napkins, whatever you need.
I signed up a couple of days ago, and then Mark says, "Hey, I think I'm going to go to that." And then we're like, "Oh, we should get Jeremy to go to that." And Tim's like, "Hey, I'm going to go to that." So before you know it grew really quick. So now we're like, "Okay, Airbnb."
That's so great, guys. I'm really honored and super pleased, dude. Like, thank you so much. That's fucking epic. And we're gonna have a great time the whole 3 days. It's gonna be lots of learning, lots of fun, and we'll accelerate everything we're doing here, right? Because it's no longer just us. Like, we're no longer alone. We're about to increase the family team size by like 200 people. It's gonna be great.
Yeah, no, I'm so pumped. And I'm like, me, I'm super low ego. So it's like my hope is to be able to support what you guys are doing. If I can do that, then I'll feel like I did something that mattered,
Oh, absolutely. No, I have no doubt you will, Tim. Both from the APEC perspective and the photo perspective, like it's all going to be out there in the zeitgeist. As gentlemen.
Very cool.
Okay. Yeah, if everyone is good and anyone else has any questions.
I have a question. So what are there going to be prizes or something? Like what exactly happens? We put together a presentation on propulsion and then it gets judged or something like that? What's happening with that?
Yeah, you got it. So we have different prizes for different tracks based on the sponsors. On the propulsion detection and tracking, we have a 5K prize allocated for it. But also on top of that though, the winning team for the sensor part of that track, that winner gets to go with Skywatcher and actually test their kit. So arguably that's worth more than money, really, because that's exclusive access that money can't buy. So that will be the winner for whoever's working on the hardware sensor kits. So again, I'm setting up a bunch of these actuators and connecting to Raspberry Pis over the next several days to try to make it easier for the hackers, so that it's mostly a firmware software problem. But yeah, whoever wins that will get that 5K prize for the gravity side. There's more sponsors that I'm talking to who are potentially interested. So this could change. There could be way more prizes as time continues. But how
do we enter for that prize? Is there like a official entry form, or is there like how does that happen to get in the running for those prizes and stuff?
Yeah, dude, I would say just show up and in the beginning, what we're going to do is we're going to have a registration for like different teams, right? I don't know if you saw, but like you should have been able to like when you registered, there should have been an option for like what track you're interested in. If you didn't get that, when you show up, whether it's the Friday or Saturday morning, right before the hackathon starts, just come find me or like tell anyone. I'll make sure they all know who you guys are. So, just let them know that you're registering, I guess, for the propulsion track, because that's the 5K prize. And then from there, we're gonna be announcing what the actual problem is. It's gonna be like a leveling playing field. Like your expertise will help you, and having a system and setup will help a lot actually, because you can show what you're thinking through your designs. But we want to make it so that if some random Caltech genius that we're inviting has some crazy, propulsion design, they have a chance at least at winning the 5K, and it's not like They're totally screwed. So that's the, I guess decision making I have to figure out if that makes sense. But we're gonna have judges though. I'm gonna be impartial. Like I'm gonna just find judges too. It's not really fully up to me.
Can we make Tim a judge? He kind of does this for a living.
Who?
Tim Ventura should be a judge.
Yeah, well, there might be a compliment. Well, maybe Tim and I and a couple other people, so that way we're getting like a totally balanced view of things. Actually,
Yeah, I mean, if you want, I'm happy to help out. You know,
I'm a pretty judgmental guy, and I'm not afraid to be honest.
Yeah, that's hilarious.
but
Fair
yeah.
enough. I see that. Mark's dying.
My blood ran cold when he said that. I'm like,
Oh,
no.
Yeah, that's pretty funny.
Dude, you're like Judge Dredd, Jeremy.
Yeah. Well, yeah, you could be a judge, but then I don't think you could also participate in the prize, right? Like,
I just vote for myself, right?
Exactly.
Yeah. No, it's interesting. I just saw that again. I did an interview with a fellow who used some Skywatcher photos, and one of the things that I was wondering was what kind of cameras they have. And the reason I ask is like the stuff that I use wouldn't be long enough range, but like Mark has like telescope equipment, and it sounds like that. Like it would be so cool if they were able to use like hardcore telescope and get super high res photos. And if they're shooting in the daytime, they should be able to.
That is their, yeah. So I think they have a few astrobiography, astrophotography cameras. And so in addition to like the standard, like some of these like really powerful DSLR cameras that they were mentioning, but yeah. So they were saying, leaning more towards that though, the astrophotography side. So
I would push back on any photography stuff because I think we're already reached the limit of what photography can show us about this craft. And it would probably be more useful to have a wideband spectrum analyzer with a Yagi antenna, wideband Yagi, to be able to figure out what RF signatures they're putting out at what frequencies and get that kind of data that is probably more telling towards the propulsion system.
Well, that's a good point. And the passive radar also. The fellow I talked to yesterday, his PhD physicist is building. So now there are 4 or 5 people who are engaged in building those, right? And I think that's really interesting. You know,
absolutely. In fact, I agree with both of you guys there. I think the intention, and as you'll see in the mission project track as well, is the intent is essentially to use the photography as like one of many sensor fusion sort of data points. Detect the object across both infrared and optical, and then lock in on it using a gimbal system, triangulate, right, and then zoom in, have radar and passive radar and active radar and everything from there. So it's about detect, track, lock, and then
the gimbal is super important. I mean, like one of the things that
we bought a bunch of gimbals for this hackathon actually for people.
It is so difficult to do. I mean, like last time I was at Mark's, he was showing me. I was at Saturn or Jupiter through the telescope, and that's like a planet. It's not really moving, right? It's just like there in space. And even with that, getting the telescope to lock on it, right? It was like it kept swinging back and forth, in and out. And when you're trying to get like a UFO, I mean, it's all over the place. So having a gimbal system is like, that's also giant.
Yeah, there's people that can take telescopes, and they have to have the right kind of telescope mount, where they can actually videotape and track the ISS as it passes over.
Wow, that makes sense. And so if you have a UFO with an unpredictable trajectory, you may not have the calibration in time. Is that what you're saying?
Yeah, so these things, they kind of know the path. So, but it does, they do have like a fast loop where it's, following if it goes out, it goes back in.
Gotcha.
It has to, but it has to have a high sample rate. So something like that, where something is like jittery,
right.
You're going to have to have different, you might have one thing that's zooming in, but another camera that's like a bigger, wider field. Then you want to look at multispectral solutions. Because like Mark is saying, a lot of the visual stuff has been done, so I would imagine you would want other parts of the wavelength, so that gets more expensive.
Indeed. Yeah. Yeah. Totally agreed. And then eventually, hyperspectral is really the dream, to have like a fully hyperspectral sensor fusion, hyperspectral cross infrared imaging, all the way from like short, medium, and long wave infrared, like hundreds and hundreds of bands at any distance. Then we can track
Well,
UAP.
Deep, I think you should chase after the things that have been covered up. And part of Project Blue Book, one of their top sightings that was supposed to be in the report that was taken out was that AWACS plane that had a close encounter with the UFO, where they were reading off the microwave spectrum, where there was a massive spike at around 3 gigahertz. So if we're able to get that part of the spectrum in, I think it'll be very useful. Equipment that can do wideband gigahertz spectrum analysis is pretty expensive. We're talking about $10,000 for a small one. So, yeah, there is.
Yeah,
and you would want like battery powered, obviously, if you're going to be taking it to the field, and then you'd want to have like a switch to go between several antennas, because there's no antenna that can get the entire band.
You could probably use phased arrays with this. Like I would phased array technology.
Phased arrays are great for specific frequency. For one specific frequency. If you want to have a wideband receiver, you need to have like a Yagi with several points on it, and it won't. You would have to switch between antennas. There's no real way to do it super wideband.
I see. Gotcha. Cool.
Yes. So Deep, there are problems like that talking to this group you'll discover, and what I would suggest is that that be something that you bring in, is like what Mark is saying, of what people suggest we do for like next year's challenges, because this is the kind of thing where it's an engineering challenge, but there is like software defined radio type solutions. There's people that are now hacking, like, okay, you could kind of hack radar the similar type of way, but you got to be very careful, right? You don't want the FCC on you and certain things. So but understanding these problems, that's a big thing you might want to have discussions on.
Right on. Those are very wise words, Curtis. I appreciate that. One thing that's always in the back of my mind is working with the U.S. government and DOGE and so forth, if needed, to just figure out like how do you maybe reduce and strip away certain regulations that are slowing down inventors and tinkerers, because I think there's a lot of room for us to run, and we need to onshore supply chains. Well said.
Yeah. Well, so on that note, why don't we wrap things up? Deep, thank you so much for giving us an overview of that, man. That is so awesome.
My pleasure, my friend. Thank you so much for having me. You guys
absolutely,
as always.
Okay. Well, so guys, let's get back to lab stuff. The person that I should go to next is, yes, he has his hand up, Robert Francis Jr., who has been patiently waiting. I'm trying to make you solo layout. Wait, there we go. Solo layout. Okay. And do you have a file that you're uploading? Yeah, you do.
Yep. Okay. Update on my inertia reduction magnet freefall experiments. Just a preliminary, my inspiration for conducting magnet freefall experiments: Lockheed Martin senior scientist Boyd Bushman. Boyd Bushman, in an interview in the documentary From Here to Andromeda, stated that he had conducted magnet freefall experiments from the 5th story of a Lockheed building that showed 2 repulsively coupled magnets fell slower than a control object and always hit the ground last. It was not made clear from this interview what was the cause: an effective increase in gravitational mass or a decrease in inertial mass. No one on the internet who has conducted magnet freefall experiments had determined which is taking place. I wanted to find out. And then my second inspiration is the Alien Reproduction Vehicle, also known as the Fluxliner. I've discussed the Alien Reproduction Vehicle in my episode 1 of my own YouTube channel. In this regard, it corresponds to its electromagnetic coil
that's around the circumference of the craft. UFOs are assumed to have some sort of inertial reduction technology to enable their high acceleration rates while not crushing their occupants with excessive g-forces. If a magnetic field can alter inertia or gravity, it would be useful for a spacecraft like the ARV to have, and would partially explain the existence of the coil on the ARV. All right, here's my Mark 10 freefall magnet freefall experiment. This particular line chart refers to a magnet, two of them attractively coupled, falling in the direction of their north to south pole. I used two IMUs inside the freefall device to give some redundancy. The max acceleration on one of them was 11.67. The other one was 11.93. Average acceleration was 10.80 and 10.93. And then you can see the standard deviations of 0.386 and 0.451. The ANOVA value, the p-value, was less than 2e to the negative 16th. The magnets were 2 inches in, there were two of them. They're N42 magnets, 2 inches in outer diameter, 1/4 inch inner diameter, and 1 inch thick. The drop height was 1.95 meters, and the filter applied was a Mahoney filter. Oh, and I also, the drop method was computer, and I also calibrated generating the offsets and scaling values used for calibrating the accelerometers. Now you can see for the control object, the error bars are much more tighter. They're very close to 9.8 meters per second squared, as you would expect from a control object. For two repulsively coupled magnets, repulsively coupled at their south poles with the north poles on the outside, also approximately 9.8 meters per second squared. Nothing to write home about. The same with the south-north coupled to north-south, so the north poles are coupled together and the south poles are on the outside, also around 9.8 meters per second squared. The south-north was a little bit different. Its average acceleration was still 9.95 up to 9.99 on the other IMU. The max acceleration achieved in spots was 10.26 and 10.27. Still nothing like the north-south one. Experimental methodology. You can see on the far right, that's the wooden tower device I constructed. The image to the left of that, that's the electronics panel using several breadboards stuck to a piece of MDF, and they contain Arduino Nanos, one an Arduino Nano 33 BLE Rev 2, and the other one was an Arduino Nano ESP32. There is a solenoid coil at the top of the device, which magnetically coupled to a steel washer on the back of the freefall object. When the coil is turned off, the object drops. The drop device has a removable MDF board with two breadboards stuck to it. The main reason for making it removable so I could easily detach it, take it over to my computer and bug test it and figure out any problems, you know, just by bringing the small board with the breadboard stuck to it to my computer. The Nano 33 BLE Rev 2 and the drop device controls the solenoid. It's connected to the IR sensor beams at the bottom. It has a buzzer for audio notifications of a successful beam break. It is connected to a micro SD card to store IMU accelerometer data to it. And it is connected via a pin to the Arduino Nano ESP32, which communicates with a smartphone for video recording. Using Bluetooth, the drop device communicates with the freefall object. By pressing the red button, that turns on the solenoid coil. The green button starts video recording, starts a stopwatch timer, tells the IMUs and the free fall object to start recording, and turns off the solenoid coil. When the IR beam is broken, the timer stops, the buzzer activates, the IMU data is transferred from the free fall Arduino to the drop device Arduino, and the IMU data is written as a CSV spreadsheet to the micro SD card. Problems encountered in the experiment. The washer not releasing from the solenoid coil after the same amount of time on every drop. This is likely due to the free fall object magnets partially magnetizing the washer, and it was more of a problem with the two attractively coupled magnet objects, the north-south to north-south and south-north to south-north, due to their stronger magnetic field. Tilting and tumbling due to one side of the washer, and solenoid magnetically sticking after object release, and IR beam breaking not occurring at the tip of the free fall object. There are 3 beams, but depending on how the object falls, the tip of the object can pass the IRR beams before a beam break is detected. Conclusion. Next month, I hope to have a completed next step in proving inertia reduction technology. I am designing and building a rotational inertia device, which attaches 2 north-south magnet objects to the periphery of it originally was going to be an aluminum disc. Now I believe it'll just be an aluminum strip about 1 inch wide and maybe 1/8 to 1/4 of an inch thick, and rotates that strip at fixed RPMs in the direction of the magnet object's north to south pole. Then I flip the magnets so the disc is rotating in the direction of the magnet object's south to north pole at the same RPMs. By connecting a current sensor in between the power supply and the stepper motor driver board that controls the motor, if inertia reduction is taking place, then less current will be used when the magnet objects are moving in the direction of the north to south pole versus their south to north pole. I now have a complete experiment replication guide on my website to replicate the Mark 10 experiment in its entirety that was presented in this presentation. It can be found at the following address: robertfrancisjr.com/mark-10. And we need more than just one person, more than just myself conducting these experiments and putting out the data. We need experiments to be replicated and for additional data to be put out if it's ever gonna, the technology and the science is ever gonna break out into the mainstream. Thanks for watching.
Awesome. Robert,
Thank you.
Man. Thank you so much. Thank you. And thank you for your patience too.
Oh, that's okay. It's okay. Thank you.
Yeah.
Just happy to be here.
Definitely. So Curtis, did you have an update for us? I think you were the last person who hasn't done one. If you have one,
yes,
I'd love to. And thank you for your patience as well.
No problem.
It's chaos as usual around here, although we're doing pretty good.
Yeah. So what do I do? Hit present and.
Yeah. Let me see. There we go. Add to stage. Okay.
Okay. All right. So let me make that bigger. Okay. So lab update. A lot of things have been going on. We have done okay, so there's 2 labs. There's the Cal State Fullerton lab, and of course Michelle Broyles over in Colorado. She's she's been working with Jim for a while now. She's one of the main team members, and she has her own independent lab where she does stuff. So with the help of Jim, so Jim's been taking some time to do some power scaling, where he's upping the voltage and testing different voltages. Now on the left there's I think there was a goof up. It says stress, but basically it's amplitude. It's looking like the device, of course, as we scale up the voltage, we get more of a response, which is expected in the theory. So that's what we've been doing lately in the calcium Fullerton lab in the vacuum chamber with the torsion balance. For the 16 disc stack, we need to arrange a transformer for that, because the transformer that we use, there's a step-up transformer that goes between the power amplifier after the signal generator, and it goes between the power amplifier and the device itself. So the device is a capacitive element. The step-up transformer makes it like an LC circuit, right? And so it has some resonance. So the step-up transformer has to be, the windings have to be the proper ratio for the capacitive, the reactive capacitance that's in the circuit. So even though we had a 16 disc stack and we were optimistic about it, we put it on there. But of course, we're using the winding for the 8 disc stack. So we're still arranging that new step-up transformer. And once that happens, then we'll have a true test of the 16 disc stack. And of course, we're expecting the 16 disc stack, because it's higher power, that we get more result. Now the 16 disc stack does trip our amplifier. It has a trip light device that protects it from sucking too much juice and burning out. So we're hoping that this putting the right transformer in will allow us to have more energy density in there and have higher thrusts. So that's still in the works. So the linear experiments, I should go to this one. This is the magnetic rail. We're still waiting for the magnetic rail that we ordered. It hasn't come in yet. And we're going to be using this magnetic rail in the vacuum when that comes in. But we're also going to be, this is a picture from Michelle in her lab. And you can see there's an air bearing, a single air bearing with this, it has a, I think it's a carbon fiber rod, and to make it light. And then down here, it's you can see the device in there. It's in a capsule, and then there's end caps so that it doesn't interact with the air and push on the air, as is apt to do. So we're going to be building a device like this, or set up like this, in Fullerton as well. And we're also still perfecting the supports. What we're finding is that putting the supports on the brass only helps, because the aluminum cap really moves around. So here's a recent run that Jim did. This was a 2-second sweep over a pretty narrow frequency, and you can see that we're able to get reliably repetitive motion from the device. And you can see here that there is, when you see the red and the green go opposite directions, and the blue trace that doesn't move much, the green is the actual device, the red is the torsion balance, and the blue is sort of the balanced center of mass of the entire system. So you can see when the blue doesn't change much, that means there's not much push going on. And you can see here that there's times where, the blue tracks, right? There's no stick slip happening here. And you can see that the device is pushing, and then there's a little delay because it's pushing over springs, and the center of mass moves. So you can see that we're able to reliably get that motion happening over and over. But again, we're on the torsion balance. So we're looking forward to the linear experiment. Now Michelle, with her linear experiment, she is able to do this. This is actually a video, and I'd like to play this, but I'm not sure. It looks like it didn't upload. So can I share my screen instead? Let's see if we can do that. Share screen. Let's see here what I can do. This. No, that's not working. Okay, hold on. Let's see, present. Okay, maybe you can help me out, Tim. I got.
Is that?
Yeah, that's it right there.
Okay.
So you should see the video playing. And you'll see the whole thing move together. Now, I think we sent you a preview of this last week. And what's going on here, this is on an air bearing, and there's some light, basically the cables that bring in the power, they're acting as little like soft springs to bring it back. Because if you leave this air bearing, it just floats around. You have to have at least something kind of centering it. So that's where you get that motion. But you can see that there's a clear push. And so there's an air bearing, so there's no, like on the torsion balance, there's no, nonlinear effects, so to speak, going on other than the cable itself that like push it, kind of pulls it back and recenters it after the motion happens. So I will say that early on we kind of we initially had a false positive where it actually kicked off the Philtech sensor, which is the one that little metal rod on the right, which is creating that red trace, and we identified that right away. So that was good. But it looks like on the linear experiment we're actually getting. I'll play that again. We're still getting the motions that we expect. So that's pretty much the update. Now on the theory side, I have made some big progress, and I'm working on a paper. And it's very exciting. So I'm hoping to give a presentation on that once I get it published. But there's a lot going on. I'm very busy lately.
Yeah, Curtis, this is incredible progress. You guys are doing amazing stuff. I posted the earlier video with Jim's permission, and people got really excited about it online. So it is wonderful. It's wonderful that you guys are getting recognition for doing the work and getting the results. And people see it happening, and they're getting excited.
Yep. Yeah, and we're talking about, how we're going to set things up in the future, because we need to keep this going, right? So we do have an interested partner, and so I'm going to be going up and presenting in May for them. And Jim and I have been talking about maybe doing some crowdfunding to facilitate us continuing this work. So it's really exciting, and I'm really excited about getting the magnetic bearing. Although that bearing is really heavy, this setup right here. What Michelle has on there with the air bearing is about 300 grams for maybe the balance of the system. So maybe like half a kilogram for the entire thing or something like that. Whereas that magnetic bearing itself is 1 kilogram. So we're going to need a lot more push to get it moving. But I am looking at the Mach Lorentz thruster and other. So I'm looking at magnetorestrictive materials, which are not easy to get. So I'm looking at other ways of doing the same effect and getting a lot more energy in there. So there's a lot of work to do. I'll stop presenting here.
Awesome. Okay. Well, so I think let's go into open discussion. We'll go until 6. How does that sound? That's about 40 minutes from now.
Yeah.
Sounds good.
Yeah.
I have a question for Curtis.
Yes.
So in that last video you showed, the gold plunger part of the thing.
That's brass. Yes.
Yeah. Sorry, the brass part. So the observation that I had was it compresses the spring and it moves, and then as it's coming back, it seems like there's a secondary compression in the retraction of that thing. Why is it dampen that retraction?
So when the thing is, because it's on these ears and there are bearings, and in this particular experiment, there's only bearings on the top rod. So when those supports are vibrating like this, sometimes you'll get a stick slip action where they bind and they start walking and kind of pulling. Yeah.
So the second compression is the stick slip.
Probably if you see like a fast action like this where one goes left and one goes right, that's the stick slip. But the overall center of mass won't be changed much, so it'll still continue.
Gotcha.
And that's one of the things we're trying to, we can only do what we can with bearings. So that was one of the improvements that I actually contributed, is getting composite bearings in there, because they used to have those ball bearings, the steel ball bearings on steel rods. And with this thing vibrating at 20 kilohertz and all that vibration, you would get like scorched channels in the steel, and the thing wasn't repeatable. So you see now it's a repeatable thing that you can like do over and over. So there are better bearings I'd like to use, but they're larger. So right here, this rod is 2 millimeters, and so to get a better technology, we'd have to go to a 8 millimeter rod. And so, I mean, the thing itself is like only 19 millimeters across. So it'd be kind of silly. So we do have, I think I showed a picture of like what Jim calls the big ears, which is a bearing that has like the ability to kind of move, even though the ears are vibrating like this. It's in a ball inside this outer part, so that if that's moving, it has that degree of freedom. So those bind less, but they're bigger, and they kind of change the dynamics of things. So we're still kind of trying to figure out what's good for this. But either way, even with stick slip in there, it is a kind of a mechanical noise. But again, stick slip won't change your center of mass.
Also, Robert, did you want to plug your YouTube channel there?
Okay, sure. I started a YouTube channel called the UFO UAP Experimental Physics Channel. Basically, I'm ripping off the components of the ARV. My main focus will be on the electromagnetic coil around its circumference, which I think was for inertia reduction, as well as shielding from charged particles, radiation in space. And then the capacitor array. I've figured out how to, like for example, Mark McCandlish discussed how he thought the capacitor array was 4 parallel plate capacitors layered on top of each other with a negative, positive, negative, positive, negative, positive. And I was doing some research and bouncing some ideas off of things. And I came away with the idea of using a 4.2 megavolt Tesla coil. And by routing the Tesla coil's voltage through an inductor into a plate, then out of that plate through another inductor, and then that inductor to another plate all the way down, that you could apply, say you're at the bottom and that's ground voltage, 0 volts. The next one's 600. The next plate's 1.2 million. Next plate's 1.8 million. All the way up. So instead of having 4 parallel plate capacitors, that in that traditional scheme that you wouldn't even be able to use 4 at one time, this would give you 7 capacitors, and you'd be able to use them all at the same time. That's what that was a major reveal in that video.
I saw there was a question in chat. Did we use gallium in the? No, there's no gallium They're composite bearings.
Oh, and maybe I should have said my YouTube channel is just youtube.com/@Robert Francis Jr. That's it. That's how you can find me.
I have a half-cocked, half-baked idea that I would be willing to share. Just gonna share it with Curtis here after we get done, but we have some downtime here. So let's see if I can present. I want to do this one. So I just randomly happened to notice that there's some relationships to the golden ratio that seems like when you compare the masses of certain particles. And I love Clearwin's quantum gravity group and their idea that like there's some higher dimensional quasi-crystal from which all particles like pop out of this thing, right? So plus the golden ratio shows up at all these different scales of creation, right? So if it's showing up with particles and it also happens to be showing up at the, normal scale of biology and life, and it may also show up with regards to black holes, maybe this is a scaling algorithm used throughout all of creation. Maybe it's worthwhile to investigate. So it turns out that when you try to see the ratio between the Planck mass, which is like 10 to the negative 8 kilograms, when you compare the mass of the muon to the Planck mass and the mass of the neutrino to the Planck mass, and you look at how many powers of the golden ratio apart those are, some numbers just fall out with surprising accuracy. So the muon is, if you take the mass of the muon times phi to the 96th power, it comes out to the mass of the Planck mass with, sub 0.001% accuracy. When you do it for the neutrino, which is much, much smaller than the muon, neutrino is like one of the smallest things we got, and you do phi to the 144th power, it comes out to 0.02% accuracy. Like I don't know, that's interesting. So then I mapped it all out for all of the elementary particles out there. So what's in each of those boxes is like phi to the what number apart each of those are, and then the color of those is what percentage off from the empirical mass versus the predicted with this phi scaling thing. What percentage off is it? So like some of these, like the super red ones, that say like
you can't see your screen, by the way. Just letting you know.
Oh my god! This whole time I've been sharing this stuff and it wasn't. Yeah, so probably need Tim to let me share screen. That's unfortunate.
Yeah, I think Tim needs to.
And he walked away.
What if you click on the present button and then just select?
Yeah, you can do that, but it won't do it unless Tim lets me share it.
I'm here, man. I'm here. There
we
QC
go.
theory.
So there's QC theory. Phi shows up everywhere. Quantum gravity research through Clearwind says that there's some quasi-crystal that's higher dimensional. Quasi-crystals have the golden ratio built into them. There are the percent errors, like I was saying, for the muon to Planck mass and neutrino to Planck mass, where it's like phi to the 96th power times the mass of the muon is within sub 0.001% of the predicted value for the empirical value of the Planck mass. And for the neutrino, once again, it comes out to sub 0.0x% when you do neutrino as well. Also, the numerologist in me just absolutely loves that the neutrino is phi to the 144th power of the Planck mass. Like I can't get over that. Anyway, so here's the. So yeah, there's ranges for the neutrinos, right? It's the lightest
there's three neutrinos.
Yeah. So the lightest neutrino is like 0.0001 eV. And
I think all we know is the difference between the masses of the neutrinos through mass flavor oscillations. I didn't know we knew the exact mass of the neutrinos.
There's a predicted mass, right? So when you look at the range for the predicted mass or the constraints on the predicted mass, it's anywhere from 0.0001 eV, 1.1 milli eV, all the way up to like all the way up to like 1.2 eV or something like that. Anyway, so you take that whole range. I didn't include that slide on here, but when you take that whole range for the N tiers with phi to the N, so that range of mass for the neutrinos would be from like 139 up to 153, phi to the 139 to phi to the 153 for that range of mass that I just gave you. And it just so happens that when you look at in that range, which phi value comes closest to which phi value ends up being like one of the best predicting ones. It happens to be 144. I wish I included that slide in here, but oh well. I'll just keep going here though. The heat map that I made here, this is where what's in each of these boxes, that's like phi to this power, right? So the neutrino to the Planck mass is 144 there, right? Versus the electron to the proton was another interesting one, which is 16. And the colors that you see there is how off these things are in their predictive value, right? So then I made another heat map. It's even harder to see, but now we have combined the two together. So now you can see percentage off value with actual numerical versus in value. Here I have highlighted all the ones that are divisible by 8 because 8 is a magic number in this quasi-crystal world. Mapped them out like this to try to show how they might be clustering together in certain in value numbers. And I don't know, you could try to draw some correlations out of this. But I think it's a little too early because, like I said, this is half-baked. Here I've clustered them in a little different way so you can kind of see maybe we have some patterns emerging, maybe. The darker the hexagon, the fewer of these there are there. The lighter it is, the more of them there are. So you can see in the lower right-hand side, we've got a bunch of little X's there. So in the lower right-hand side here, that yellow one, we've got a bunch over there. Anyways, like I said, it's half-baked. The value of the ratio from the Planck mass to the muon and the Planck mass to the neutrinos, as well as the ratio of the electron to the proton and neutron, all seem to be maybe somewhat related to this gold ratio scaling value. Now, this is, like I said, very half-baked. This is like a week old. So massive bucket of salt here. But if there is some predictive value here, especially if we can identify what's causing some of these percentage differences, for example, the offset of the neutrino prediction is right around in the same ballpark as the cosmic microwave background energy level. It's like cosmic microwave background, I think it's around 8 micro electron volts, and the difference that I had for mine is 2.2 micro electron volts. I don't know. It's a half-baked thing.
Thanks, Jared.
Yeah, thank you, man. We're starting to wind down. Okay. Well, we did pretty good. I think we pulled it together for this conference. We haven't been lynched by the audience yet, although the night is still young.
Tim, one quick note. Out on Next Big Future, they did another expose of Dr. Charles Bueller. You know, all his cool stuff that he dropped on them a couple of weeks ago, it all worked magically. So that he has a working EDS, which is the basic core of the same basic technology as our warp drive. So
okay.
They did a really cool write-up, and worth looking at.
Well, how are we doing? Oops. There we go. How are we doing, guys? Should we wrap things up early? I think everybody kind of came to a... Okay, let's do that. Well, guys, thank you, everyone. This has been APEC for April 12th, 2025. This has been one heck of a presentation, and this conference session is going to be followed up in May, right? In just about a month. And I've already got that booked out, and that's going to be equally amazing. So thank you. Thank you to everybody watching. Thank you to you guys. We are continuing to make history.